we begin this course with a quick overview of the DA-100 certification exam, which tests your ability to analyze data with Power BI. This is just to get you oriented towards the exam before diving into the course material. To begin, let's take a look at how exactly Power BI can be described. Well, this has been developed by Microsoft, and you can think of it as a business analytics tool. Business analytics encapsulates features such as data visualizations, business intelligence, as well as the ability to create reports out of underlying sources of data. The goal of these reports is to enable viewers to extract meaningful insights from the data just by looking at them. So what are some of the salient points of the DA-100 certification exam? Well, we can start off with what exactly it tests for. If you pass the exam, it pretty much validates the fact that you have the skills to perform data analysis tasks using Power BI. So you can rightfully call yourself a data analyst, and more importantly, you will know what data analysis involves. This is an exam which can be given in person across various testing centers all over the world, or if you prefer, you could also give it online. We will in fact cover the online test in a little more detail just a little later in this video. If you do pass the exam, well, the certification is valid for 2 years. So if you'd like to keep your data analysis skills up to date, it makes sense for you to repeat the exam every couple of years, since many things may have changed within Power BI. One thing to note that this exam is not merely about rote memorization and remembering specific features of Power BI for the tests. You will in fact be tested on your ability to create complex formulas, and will also need to go through a few case studies to make sure that you truly understand what data analysis involves. And with that, let's now explore some of the skills which are tested for in the DA-100 certification exam. Well, one of the categories of skills is under preparing data for analysis, which makes up about 25% of the points awarded for the exam. This focuses on getting data from a variety of sources into Power BI, transforming them into a form which is suitable for analysis, and so on. Next comes modeling the data for visualization. This will involve setting up the right relationships between data scattered across multiple tables. If you have worked with relational databases before, well, there will be a lot of overlap with designing a model for relational databases, and this section also makes up about 25% of the questions for the test. And then there is the part which you might most closely associate with Power BI, which is building visualizations. This will involve picking the right chart to convey the right type of information. And the questions from this category make up about 20% of the points awarded for the certification. A collection of visualizations can be put together in order to create a report, and it is the ability to analyze the data in such reports which is also tested in the exam. The weightage for this section is about 15%. And then the last category of questions falls under the deployment and maintenance of Power BI assets. This can range from datasets to workspaces containing your reports, and about 10 to 15% of the questions will fall under this category. All in all, you get the idea that this certification is meant to test you across a wide range of skills, from fine-grained transformations of data to understanding the big picture conveyed by the data. Next, let's quickly take a look at some useful resources when it comes to preparing for the exam. First of all, there is the homepage, which is available at this URL on docs.microsoft.com. This will help you keep up to date with any changes in the pattern of the exam or the contents, and also includes a free tutorial to help you prepare for the test. Then, in order to register for the DA-100 certification exam, you could navigate to this URL. As touched upon earlier, you could schedule your test to be in person or even online. And if you do choose the latter option, you will end up signing on with the company which conducts the tests on behalf of Microsoft, and at the time of this recording, it is Pearson VUE. To get a summary of the requirements for the online test, you can navigate to this URL. However, we will discuss some of the important points for the online test in the next video. So now that you have some idea of the DA-100 certification exam, well, let's quickly summarize some of the steps involved in taking the test. This starts with preparing for the test, which includes watching this course. If you haven't done so already, you will need to register for the exam, and once that is done and you're all set with your preparation, well, there are things which you do need to set up before you give the test online. These include some setup work conducted the day before the exam, and then some additional work just about 30 minutes prior to it. And then, of course, you will take the test. Let's now zoom in on each of these steps in a little more detail, starting with test preparation. So, as touched upon, there are some free tutorials available in the exam homepage. There is also a paid course which you can take up, which is linked in the official documentation. And of course, there are a number of other online resources, including this course, which covers all of the concepts you do need to be familiar with when preparing for the exam. The DA-100 certification test does include many questions related to the DAX formula language. DAX is short for Data Analysis Expressions, and this is a language which is used to construct formulas to be applied on your data. DAX will be covered in depth in the Learning Path Design Data Models in Power BI, which is part of this journey. And at this URL, you will find the official documentation for this formula language. While we have covered the tutorials specific to the DA-100 exam, there are also more generic Power BI tutorials which are available and can help you get more familiarity with this data analysis tool. The official English language guide to Power BI is available at powerbi.microsoft.com/enus/learning. All in all, to truly understand Power BI and the concepts surrounding it, which you will be tested on, you should look into test-specific as well as more general Power BI resources. Then you may move on to registering for the test. At the time of this recording, Microsoft does not proctor the exams on its own, but partners with another firm which specializes in conducting tests. In any case, you will require a Microsoft account in order to register. Also keep in mind that the name on your Microsoft account should match the name on the ID which you will present at the time of your exam. So make sure that there are no spelling variations or any mismatch in terms of the use of middle name and so on. Once you sign up for the test, you will be sent over an email with detailed instructions for how you can sign in to give your test. This will include some instructions for how to set up your computer, the physical environment where you will be giving the test, and a lot of other information as well. Now, there is always the possibility that for some reason you may need to reschedule the test. This is something which can be done. You will need to head over to the certification dashboard. The link to this will be part of the post-registration email, but keep in mind that if you do decide to reschedule, you may need to pay a fee unless there was some kind of technical glitch on the side of the organization conducting the test. If this were to happen, you will be given a voucher which you can use in order to pay for the re-registration, and this will be valid for 1 year. So once you're done with preparing for the test and also registering for it, well, the day before the test, or maybe even a couple of days before it, you can set up your computer and your overall environment in order to give the exam. One of the resources pointed to in the email sent after registration will allow you to test your system and perform any setup work so that you can give the exam online. This will include tests for the performance of your hardware and your internet connection. And then you will also have an access code which you can use to download and install a piece of software called OnView. It is this software which you will need to use in order to give the exam. Furthermore, OnView will also include tests for your microphone, the speakers on your machine, webcam, and your internet connection to make sure that the test itself goes through quite smoothly. And then, well, on the day before your exam, you should ideally prepare the testing space and then keep an ID handy. As touched upon earlier, the name on your ID should match the name in your Microsoft account. If you'd like additional information on what is needed in order to set things up before the test, you can navigate to this Pearson View webpage. So we have now covered all the preparation work which you need to put in the days leading up to the test and up to the day before the test, which takes us along to what you need to do on the day of the exam. Starting with your physical space, presumably you will be giving the exam sitting on a desk, in which case keep this desk clean without any clutter. This is not just to keep you free of distractions, but it's also to satisfy the proctor of your exam that there is nothing there which could potentially be used for cheating. Now, in many cases, it is possible for you to keep your mobile phone in the same room as where you give the test, since you may require this for communication and for some emergencies. However, you should not keep this on the desk where you plan to give the exam. Furthermore, it is recommended that you check in for the exam a little over 30 minutes before it is set to begin. You will need this time in order to perform some of the pre-test tasks which we will now cover. This includes uploading a copy of your ID with your cell phone. This is one of the reasons why you will need to keep your phone close by, though not on your desk, and you can make use of a link which will be supplied to you to upload the ID. Note that when you check in for the online test, you will be doing so using the OnView software, which you should have downloaded in the days before the exam. Once you have checked in, at some point you should expect a proctor to come online, who will be the one person you can communicate with during the exam. Initially, the proctor will inspect the room and will make sure that you don't have anything in there which you could use for reference during the test. While you will still have your computer turned on, of course, the OnView software which you will install on it will ensure that all other applications are disabled. This will include any browser app which you have and any other utilities such as note-taking software, ensuring that all you can really do on your machine is give the exam. And once all of this is done, well, all you need to do is take the test and hopefully breeze through it. But then, there are a few things you need to be mindful of when giving the test itself. First of all, there will be a total of 40 to 60 questions, but many of these questions involve the selection of several correct answers, with 1 point for each correct answer. In the end, your score will be adjusted to a score out of 1000 points, so that a percentage score is easier to compute. The total time you will be allocated for the test is 3 hours, and in order to pass, you will require a score of 700 points out of 1000. Now, whether or not you have passed will be communicated to you within a few minutes of you completing the test. This will include a breakdown of your score across each of the different categories you are tested on. So with this high-level view of the tests, let's dig a little deeper into the mechanics. So each time you have a question, you will select one or more correct answers and then hit submit. Once again, I will emphasize that there may be multiple correct answers. In many cases, they will be explicit about how many correct solutions you need to choose. For example, out of 4 choices, they may say that you need to select 2 correct answers. You may also be asked to combine many of the choices in order to construct your answer. For instance, you may be asked to construct a formula to calculate a specific value, including the name of the function to use, along with the arguments. And you may have multiple choices for each of these. Now, of course, you may not immediately know the answers to each and every question, in which case, it is possible for you to mark a question as orange or something to come back to later on. This is where you may make a selection for the correct answer, but you won't hit submit. Now you don't need to keep track of precisely which question you left in such a state, since they will show up at the end of each section. So a potential strategy may be for you to go through the questions and only answer those which you're entirely confident of before revisiting the ones which you're not as sure about. One thing to keep in mind is that your exam may be halted by the proctor at any point during the test. For example, they may just seek some clarification from you or may even assist you in case of a technical glitch. However, if the proctor does pause the test, keep in mind that you won't be able to answer any question at this point until the proctor explicitly resumes the test. While your test is on pause, it is not possible for you to take any screenshots, and generally speaking, during the exam itself, it's best not to worry about anything other than actually answering everything correctly. Now, in case you do encounter some technical issue, you can initiate a chat with the proctor. This is using the OnView software which is provided. Furthermore, a proctor is well within their rights to ask to view the room at any time during the test, even if they interrupt you for it. So once again, it is best just to avoid any kind of clutter or include anything in your room which might arouse suspicion. And then, once you have submitted all of the answers or the 3 hours have elapsed, well, your score will be available within a few minutes. This will include a breakdown of your score across the 5 different sections which we discussed earlier on. And then an email will also be sent with all of your details about your test performance. And of course, for anyone giving a certification exam, a rather important matter is the certificate itself. This is something which will be available in your Microsoft dashboard and will be available there for the entire 2 years where the certification is valid. So this covers the brief overview of the DA-100 certification exam, and from the next video, we will dive into data analysis. Previously in this course, we have discussed the fact that the DA-100 certification exam aims to test your ability to perform data analysis. And now we will examine what exactly is meant by the term data analysis and the variety of tasks this entails. First, let's revisit the definition of Power BI we explored just previously, and now we will also zoom in on specific aspects of this definition. So Power BI is a business analytics tool which allows you to build reports telling stories about data by using data visualizations and business intelligence tools. The goal of these reports is to enable users to extract meaningful insights from the underlying data. So the important factors to keep in mind here are the fact that Power BI is a business analytics tool. So this is to help organizations analyze their own past data to make business decisions which will carry them into the future. Importantly, Power BI is built and maintained by the Microsoft Corporation, and in fact, it shares a lot of similarities with other Microsoft tools such as Excel and integrates with Microsoft technologies such as SQL Server and the Azure Cloud Platform. And then comes the part about how exactly business analytics can be performed. So in this regard, we can make use of data visualizations, which are essentially charts constructed out of data. There are business intelligence tools, which can help with transforming some data into visualizations, and all of these can be used in order to build reports which tell a story about the data. And all of this, of course, is meant for businesses to extract meaningful insights and drive decisions which will influence their future. With that said, let's dig a little deeper into what exactly is meant by the term business analytics. Now, like most such terms, this does not have a definition which is black and white, and different people may use this term differently. Generally speaking, however, this alludes to looking at the past data about a business with the goal of gaining insights from the data, and these insights can be used to drive decisions which take a business forward. For example, you may analyze the sales of cell phones over a 4-year period across various geographical regions in order to decide where the latest models of a company's cell phones should be launched and marketed. With that said, what exactly is the role of Power BI when it comes to business analytics? Well, of course, this involves the study of past data. This data will typically be available in some kind of tabular form and may contain thousands, if not millions of rows of data. In which case, looking at the raw data itself does not really tell us anything meaningful, and it's nearly impossible to get a big picture view of what the data conveys. However, tools such as Power BI allow us to produce interactive visualizations out of this raw data, which does give us the big picture view. For example, a pie chart may point out that a specific model of cell phone is purchased predominantly in Eastern Europe. Now, a number of such visualizations can be combined together in order to form a report. A report, if constructed properly, may in fact convey a meaningful story about how the business has done in the past And the insights extracted from those stories from the past may decide the course of action which can propel a business into the future. So, Power BI helps us translate raw data into visualizations and reports which can drive business decisions. However, the journey from data to decisions involves several different steps, as you can easily imagine. First of all, you will need to identify where exactly the data which you need can be sourced. So you will need to figure out specific data sources, whether they are in files, in database systems, or maybe even a combination of two or more sources. You will then need to transform that data into a form which can be used in visualizations. Then you'll need to create and configure the visualizations themselves, compose them into reports, and so on. And Power BI will assist you in each step of this journey. And crucially, for a lot of people, it'll allow you to do this without having to write a single line of code. Well, at least in the sense of a programming language, though you will need to know how to write DAX formulas. What this translates to is that data analysts can focus on the big picture more and more. That is, telling a story with data rather than have to worry about the nitty-gritty, which are encapsulated by this second point. Whereas traditionally, you may have been required to write scripts or use some other programming language in order to accomplish data source connections, cleaning and transformation of data, and so on. Now, all you really need to do is to learn how to use Power BI's rather intuitive user interface. In fact, in the overall universe of business analytics, it is these steps which encompass data analysis. So once again, this is a term which has different definitions in many different contexts. However, generally speaking, the process of having to inspect, clean, transform, and model data is termed as data analysis. And the goal of this analysis is to be able to create visualizations which can be used to gather insights, and then in turn, those can be used to make business decisions. Given how many different tasks data analysis encompasses, this becomes a crucial component of business analytics. Now you may be wondering, where exactly does data analysis end? That is, what separates data analysis from the other steps in business analytics? Well, data analysis pretty much covers all of the steps from the identification of data sources, which can be used to build visuals, to the generating of reports containing those visuals. What data analysis does not entail is the interpreting of the data in order to make the decisions. So, as a data analyst, you can think of your role as having to do everything in your control to help the leaders of your organization make the best possible decisions from data. So, the role of a data analyst is more data focused, and this is closely associated with the role of business analysis, which is a little more business focused, though this does share a lot in common with data analysis. So, what exactly are some of these data focused tasks which fall under the umbrella of data analysis? Well, you can think of this process as encompassing multiple phases, starting with the gathering of requirements for data. For example, if your goal is to produce reports which convey details about sales across the world, you will need to worry about where exactly this information can be sourced from, whether the sales number should be expressed in US dollars, euros, or Indian rupees, and also how up to date the data should be, whether it needs to be near real time or perhaps even a month old. Once these requirements are in place, well, you can identify potentially multiple data sources. Maybe the sales numbers in one region are available in CSV files, and in another region, you will need to dig into a relational database. Then you may need permissions in order to connect to these sources, and as a data analyst, you will need to be familiar with this process, even if it is not your primary job. Once the data is available and you have connected to it, well, this may require some cleaning. A good practice, which I will repeat every now and then throughout this learning path, is to remove any unnecessary data. So, if you're only concerned with the annual sales numbers, the specific store, or the exact date and time where an individual sale was recorded, may not really be relevant. And if this is included in your data source, well, you may be best served to filter it out. A smaller data set will ensure better performance of your visualizations and can also be easier to maintain. And then there is the rather broad phase of data processing. This is where you might structure your data in an optimal form, perhaps separating data into multiple related tables rather than work with a single table. You may also transform individual columns in your data, for example, to convert prices expressed in US dollars to euros, and you may also perform aggregations on your data. While in many cases, these encompass the primary tasks of a data analyst, in many organizations, you may even have to go a little further. For example, you may perform exploratory data analysis as well in order to get a better understanding of what kind of data you're working with. So you can think of this as zooming out a little bit from data cleaning and data processing and looking at what exactly the data is meant to convey. Here, you may apply a lot of statistical operations on the data. For example, to figure out what the average cell phone sales are in each region in the world. And this analysis can also be aided by generating some visualizations. And once you have constructed these visualizations, you can combine them into reports which tell a story and then communicate these reports over to the decision makers in your organization. With Power BI, this could be as simple as sharing a link. So we have now broadly covered the different phases involved in data analysis. But while we have covered data analytics and business analytics, it also helps to understand some of the other types of analytics. Note that a lot of these will have significant overlaps with data analytics, but it's best to know what exactly these terms mean. For example, descriptive analytics usually involves calculating statistics which describes the current status of your organization. For example, the total sales recorded in the previous year, the total number of employees in each region of the world, the market share in various segments, and so on. Then there is diagnostic analysis. This is primarily used to get to the underlying reason behind certain events. For instance, you can analyze fraudulent card transactions in order to identify some commonalities between all of them. And such data can be used to block off potential fraud transactions in the future. The term predictive analytics is used when data analysis is performed in order to make predictions about the future. For instance, a meteorological department may use information about rainfall in the past years alongside the current climate conditions to predict the rainfall for the coming year, while an airline may use this data to predict the sales of flight tickets for the coming season. And then there is cognitive analytics. This is where a hypothesis can be made with a certain degree of confidence. For example, there is a 60% chance that an increase in crop yield is due to a specific fertilizer. And then there is prescriptive analytics, which can map actions to outcomes. For example, if we double our social media advertising in Southern Africa, our revenues there will quadruple. In the previous video, we got a glimpse into what exactly data analysis is. Mainly, that it is a rather broad field which encompasses a wide variety of tasks. We will now cover some of the more specific roles in the broad umbrella of data analysis and take a look at what exactly their scopes are. First of all, when it comes to data analysis and the people involved in this field, it helps for us to reinforce the idea that data analysis encompasses a wide variety of tasks ranging from gathering the requirements for data to generating reports from the data. When it comes to large organizations, well, they may just be way too much data for a single person to work with. So an entire data analysis team will need to be created. When this happens, each team member may be cast into a specialized role where the scopes will be limited to specific aspects of data analysis. And that is what we are now about to look into in detail. Now keep in mind that depending on the organization, the specific definition and scopes of the roles we are about to discuss will vary. In some cases, a single role may in fact be split up into further specialized sub-roles. Some of the roles may be combined, or there may be significant overlaps between the different roles. In any case, it does help to have some framework in order to understand what exactly these roles relate to. So with that said, let's move on and take a look at the different data analysis roles we will now explore, starting with a data analyst, and you can think of this as the broadest roles we will cover. Then there is a business analyst, who is very similar to a data analyst, but maybe a little more business focused. Then there is a data engineer, who is a little more closely aligned with the data and potentially will see a little less of the business end of things. A data scientist will have a slightly bigger picture in mind and will perform some analysis of the data. And then there are database administrators, whose roles are highly specialized and involve the complex tasks of building and maintaining a database system. Now, to recognize the scopes for each of these data analysis roles, it helps for us to identify the different phases in data analysis, which we covered just a little earlier. And then we will discuss which of these phases each of the roles will cover. The first phase we looked into was gathering the requirements as far as data is concerned. So figuring out what information we really need, in what format, and so on. Then we will need to identify the specific sources where the data can be obtained and then managing them. Then that data will need to be cleaned and processed to get it into a form which can be used in visualizations. Following which, we may perform some exploratory data analysis in order to figure out exactly what the data contains and what visualizations will do the best job in conveying a story about the data. And then there is the building of reports and conveying those reports to the decision makers in the organization and potentially external stakeholders. So from these 5 phases of data analysis, what exactly falls under the scope of a data analyst? Well, you can think of a data analyst in this context as being a jack of all trades. They may play a role in pretty much every single phase, and the role could be hands-on in many phases and a little more supervisory in others. And for you as a data analyst, it is best to assume that you need to be familiar with every single task, from data cleaning and transformations to building reports. And it goes without saying that to help you in these tasks, you can make use of tools such as Power BI. And everything can be accomplished without having to write one line of code. Now, a data analyst in some cases may also need to work as a project manager, where they will sit down with stakeholders, figure out where in the pipeline things are getting slowed down, and then fix these bottlenecks. In essence, a data analyst may need to optimize the entire pipeline. A data analyst may also be required to play a role in securing the data, and this could be done at multiple levels. Perhaps data sources themselves can be secured, or it is the visualizations which can be modified so that only specific users have access to certain types of data. So all in all, you can think of a data analyst as playing some role in each and every phase of the different data analysis tasks we talked about. And then from a data analyst, we'll now move along to the role of a business analyst. In many organizations, there is really no distinction between the two roles. However, typically a business analyst will work in the data requirements and gathering phase, but will not get too involved when it comes to working directly with the data. However, a business analyst may play a significant role when it comes to exploratory data analysis and communication with the stakeholders, closer to the business end of things. So to summarize the role of a business analyst, there is a lot of overlap with the tasks of a data analyst. However, rather than working more closely with the data, they tend to work more closely with the business. For instance, they may play a role in generating visualizations and configuring them and assembling them together into reports. They may also play a role in extracting insights from the data using the visualizations and reports. However, they will still fall short of actually making the decisions from the data. However, the business analyst will work closely with the real decision makers and other significant stakeholders in any data analysis project. When there are distinct business and data analysts, it is the business analyst who will work very closely with the data analyst to ensure that the business requirements are met. And then there is the data engineer role. Out of the 5 phases, their involvement will be significant in the data source management as well as data cleaning and processing. So they are very much hands-on when it comes to preparing data for analysis. Digging a little deeper into this role, the primary focus of a data engineer is with hosting and managing the data out of which visualizations are built and then assembled into reports. So this may involve setting up either cloud-based or on-premises sources for data and the use of services to transform the data. Such services can once again be either on-premises or hosted on the cloud. Data engineers will also need to ensure that the data can be transmitted between the various stages in the pipeline. For example, the data may be stored on one host in the cloud, and then it is copied over to another host on premises in order to apply some transformations. A data engineer will ensure that this process is smooth. Furthermore, a data engineer may work together with data analysts to ensure that the data is stored and transformed correctly and in an optimal manner. Moving along then to the role of a data scientist. So the focus of such an individual would be on cleaning and processing the data so that it can be used in visualizations, and then on deciding exactly what those visualizations should convey, in which case they will perform some exploratory data analysis. Now you will already see that though there are a number of different roles, there is some overlap between them and certain areas of specialization. Taking a closer look at a data scientist, once the data has been prepared, they may analyze it to figure out where exactly there is meaningful information out of which insights can be extracted. Going back to the mobile phone sales, well, a data scientist may determine whether the median sale price or the average sale price should be used in order to build visualizations. They may also determine whether a chart should represent the sales by region, sales by a customer's age group, or a combination of the two. To help with this, they may perform a variety of descriptive, predictive, as well as cognitive analysis. If the cognitive analysis reveals that there is a 90% likelihood of the sales of a particular cell phone being primarily driven by the age group of the customer, well, a visualization portraying the sales by customer's age group will be generated. So these points cover the exploratory data analysis tasks. However, a data scientist may also play a role in data transformations, perhaps in the final phases of the transformations before visualizations are generated, and in this regard, they will have to work closely with data analysts and potentially data engineers as well. And finally, there is the role of the database administrator. As touched upon earlier, this is perhaps the role where the scope is most clearly defined. They will mainly get involved in managing the different data sources along with the machines and tools which help host them. For instance, an administrator here may make sure that the data is constantly available. In this regard, they will need to plan and implement viable backup strategies and ensure that all of the hardware and software tools which are used are configured in an optimal manner. So, in this context, the role is not strictly to manage databases, but any tool or service which hosts data. This management can also encompass the security around the data, including ensuring that only specific users or applications can access it in the first place. So now that we have covered each of the roles and their scopes in depth, let's quickly summarize some of the important points. So all of the different scopes and responsibilities which we just talked about are not really set in stone. Each organization may interpret these roles a little differently, and in fact, even different teams within the same organization may have a different view on the roles. So while a general understanding of the roles may be required for the exam, in real life, things might work just a little differently. This includes the fact that you as a data analyst may be given a rather specific role with limited scope. However, it is still crucial for you to understand all of the steps involved in the full data analysis workflow, which is why the DA-100 certification exam covers all of the different tasks across all of the phases which we've discussed. And of course, a tool such as Power BI can greatly simplify each of these tasks and phases, which is why it is such an important technology to know in and out to be an effective data analyst. And with this in mind, we will head over into the next video where we zoom in on the specific tasks of a data analyst. In the previous video, we covered a variety of different roles which broadly fall under the umbrella of data analysis and also how they apply to the different phases of data analysis. We will now zoom in a little further on specific data analysis tasks. To begin, let's revisit the different phases of data analysis which we previously covered. We can think of the requirement gathering phase as the first step in data analysis, where we figure out what data we need and in what form. We then identify the different sources of data which can give us data in the required format and also ensure that we can manage this data. For instance, ensuring that the data is always available and that new data is generated reliably. Then comes the phase of cleaning and processing the data, where we might transform it to a form which can be used directly in visualizations. And then comes the phase where we explore the data available to us to figure out what exactly should be conveyed in the visualizations. And finally, we will generate the charts and graphs, combine them into reports, and communicate them to the stakeholders. So while this does cover the sequence of different phases and encompasses many of the data analysis tasks, it can often help if we were to look at these tasks in a slightly different manner, more specifically by breaking them down into categories of operations. And in this regard, there are 5 different categories which we will now discuss. The first of these is data preparation. There is also the modeling of data, where we might define relationships between different tables. Then there is data visualization, where we convey meaningful information present in our data. Then there is the task of interpreting the visualizations to gather meaningful insights. And finally, there is the management of the data itself. So unlike the different phases we discussed, all of these are not exactly in sequential order, but to get an understanding of them, let's zoom in on each of these one at a time, starting with data preparation. This is where we take the raw data which comes to us and then transform it to a form which can be plugged into visualizations, out of which reports can be assembled. So this is essentially setting things up for visualizations. And the specific tasks here may involve cleaning the data in order to remove unnecessary columns and maybe rows which contain errors. We could also transform the data into a form which is useful for our visualizations. For example, translating values from euros to dollars, and also anonymizing the data. For example, hiding any information which might point to a specific customer, such as a customer ID, a date of birth, and so on. One category of tasks which might go on in parallel with data preparation is data modeling. If you have designed relational database schemas before, you should be familiar with this. This is where you identify and then implement relationships in the underlying data, which might be spread across multiple tables. There may be multiple end goals when you perform this kind of modeling. For example, you may wish to reduce complexity as well as redundancy in data, which is often the case with database schema design. So the right type of modeling can ensure that data is not duplicated across multiple tables or even in the same table. And another crucial goal of data modeling is to improve the overall performance of the visualizations. Power BI visualizations are interactive in nature, and a poorly designed model can significantly reduce the overall performance, where a chart might take a few seconds to reload after you have clicked on it. And speaking of interactive charts, well, another category of data analysis tasks is data visualization. This is where different types of charts can be constructed using the underlying data. For example, you may use a pie chart in order to convey the share of profits from different types of mobile phones. Or you could draw a line chart to convey how sales have varied over a period of time. In fact, this is a crucial skill under data visualization, where you need to pick the right kind of chart to convey a specific piece of information. And to further assist you in extracting meaningful insights, well, Power BI includes a variety of AI tools as well as insight features which can generate interesting visualizations for you or augment your already created visualizations. And from visualizing data, we can take a look at the category of data interpretation. This is where you will look at a variety of charts and reports and then extract meaningful inferences which can then be used to drive business decisions. While a data analyst may not have a direct part to play when it comes to making these decisions, the quality of their visualizations and reports will certainly have some role to play in the final course of action. While data interpretation may seem like something which is best left to a human mind, Power BI can in fact play a role here as well. There are utilities here which can help you identify some underlying patterns in the data which may not be readily discernible to a human being. And then there are the analysis tasks which fall under the umbrella of data management. Now, if you are working in an organization of any reasonable size, it is likely that your data will not come from just a single source, but there will be multiple sources, and the data itself may come in several formats, and these in turn could be hosted on the cloud or on premises. So all in all, there are just a lot of different pieces which must come together and be managed properly. This management can include hardware management. This may involve regular upgrades of on-premises hardware as well as networking equipment to ensure that the data can be stored and transferred optimally. Maintenance of software can also play a role here, and also any security attached to the data. And of course, within data management, and in fact, within any of the different categories of tasks we have discussed, there is the rather important task of managing the people involved. So the big picture view is that data analysis encompasses a wide variety of steps and can get very complex. And it is important to understand this big picture before diving into the specifics of Power BI, which is precisely what we'll do starting from the next video. So far in this course, we have looked at data analysis from a variety of different angles, and I have mentioned a few times that Power BI can simplify a lot of the steps in data analysis, and we will now take a closer look at Power BI's features and components which make this happen. To begin, however, let's quickly recap some of the concepts which we covered earlier to understand where exactly Power BI fits in. So we discussed that data analysis involves inspecting, cleaning, transforming, as well as modeling data with the goal of extracting meaningful insights that can drive business decisions, and that this is a crucial part of business analytics. This involves a number of different steps, all the way from identifying the correct sources of data to building reports out of them. However, data analysis does not mean interpreting and making decisions from the data, and instead, the goal is to help the decision makers. And of course, Power BI can make a lot of the different steps involved a whole lot easier. As for the different phases of data analysis and where Power BI fits in, well, it does not quite enter the picture as far as data requirement gathering is concerned. However, it plays a huge role when it comes to managing data sources, also when it comes to cleaning and processing the data. Exploratory data analysis is made much simpler with Power BI, since performing statistical operations and also building visualizations can be accomplished with just a handful of clicks. And then, communicating information as well as visualizations and reports can also be simplified with Power BI. So in short, outside of data requirement gathering, Power BI has a role to play in each of the other phases of data analysis. And with this in mind, well, another look at the Power BI definition may make a little more sense. So this is a business analytics service maintained by Microsoft, and it allows us to create visualizations and use business intelligence in order to build reports which can then be used to extract insights from data. So with the revision done, let's take a look at the specific features of Power BI which make all of this happen. Well, first of all, when it comes to data source management, Power BI allows us to connect to a variety of different data sources, from CSV files and XML flat files to relational and NoSQL databases, and in fact, we can also source data from HTML tables on a web page. Power BI will maintain connections to these data sources and can also periodically perform a refresh to load new data from those sources. Furthermore, it includes a very intuitive UI, and there is also a query language called M, which can be used to combine data from multiple sources, clean that data if required, and also transform it to a form, which makes things easier when building visualizations. From the point of view of the DA-100 exam and also the demos of this learning path, our focus will be on using the UI, though we will visit the M language. When it comes to transforming data and also modeling data, we will need to make use of Power BI's DAX language. DAX is short for Data Analysis Expression, and if you're familiar with Microsoft Excel, well, this is similar to the formula language used in that tool with a number of additional features catered towards data analysis. So we can connect to different data sources, transform that data using the M language or the UI, and then perform some computations using the DAX language, and all of this can be fed in to visualizations with the aim to convey specific kinds of information. So a bar chart can convey sales across different categories, a line chart can convey sales over a period of time. Visualizations can be assembled together to form reports as well as dashboards, and these can be published over to the cloud. And then Power BI makes it easier for us to share these reports and dashboards with other team members and significant stakeholders. So now that we have discussed some of the specific features, well, let's zoom out a little bit and take a look at how exactly different individuals might use Power BI. And in this regard, we will explore the different components of Power BI. The first of these is Power BI Desktop. As implied by the name, this is a desktop application. As a data analyst, this is where you will end up spending most of your time in order to work with data and assemble visualizations and reports. Once that is done, they can be published over to the Power BI service. This can be a cloud-based service where it is possible to share and collaborate with other team members as well as stakeholders, which includes the ultimate decision makers in your organization. Now, the Power BI service makes it easy to view visualizations and reports from a laptop or a desktop. However, there are also Power BI apps which can be used to view the reports from a cell phone. This is of course for individuals who are on the go and may not have immediate access to a laptop. And in fact, some visualizations may be easy enough to interpret from a mobile app. So now that we have covered the three different components, let's see exactly how these are used. To begin, a data analyst may connect to a variety of data sources and load the data into Power BI Desktop, and then they will clean and transform the data to build visualizations and reports. At this stage, the reports can then be published to the Power BI service. You can think of this as a software as a service, which is available on the cloud, though it is possible for you to host the Power BI service within your own organization's premises. This is where most users are expected to view and interact with the visuals. The Power BI service is also where a data analyst may create dashboards for the end users. Now, much of what is published to the Power BI service can also be accessed from the Power BI mobile apps. So, end users might spend a lot of time here. However, as a data analyst, you may just use mobile apps to test that your visuals perform well on such a platform. Now, we previously discussed a variety of different roles under the umbrella of data analysis. So, let's see how exactly these different roles map to the different components of Power BI. So when it comes to Power BI Desktop, it is expected that data analysts will spend a lot of time here, as will data engineers, data scientists, and to a great degree also business analysts, who may use Power BI Desktop to perform exploratory data analysis and also to build visualizations. Then there is the Power BI service, which is targeted at the consumers of the reports. These could be the decision makers in your organization and other stakeholders, but since business analysts are meant to look at things from their point of view, they may also spend some time in here. And as far as the mobile apps are concerned, well, once again, it is the decision makers and other stakeholders who are expected to use this, but mainly when they don't have a laptop or desktop handy. For detailed analysis, including complex interactions, they may still wish to use the Power BI service. So we now have an overview of the different features and components of Power BI. And in the next video, we will dig a little deeper into some of the crucial building blocks of this tool. Having examined some of the high-level components of Power BI, it's now time for us to look at the fundamental ingredients of this tool, which simplify the tasks of data analysis. The first of these ingredients is the dataset, and Power BI allows us to connect to a wide variety of these datasets. Datasets can be cleaned and transformed and then used to generate visualizations, and then the visualizations can be put together into reports. A report may also be comprised of one or more dashboards, and a single visualization in a report or a dashboard is referred to as a tile. Each of these have their own set of features, and we will quickly get a glance into each of them. Let's start off by taking a look at the datasets. So, as touched upon, Power BI can connect to a variety of different data sources, and a dataset can be created from each of them. In fact, datasets can also be created by combining two or more sources. Another crucial building block in Power BI is the visualization. These are the charts and tables which can be used to convey information based out of the underlying data, and there are different types of visualizations which can be used to convey different types of information, ranging from the standard bar charts and pie charts to more specialized visualizations such as map charts. So datasets can be used to build visualizations, and visualizations in turn can be put together to create a report. The goal of a report is to use visualizations to tell a story. So sticking with our example, for the sales of cell phones across various regions in the world, you may have one visualization which conveys the sales across different age groups of customers, and another one may convey the sales over time in different geographical regions. Together, the charts may indicate that a company should target their marketing campaigns towards teenagers in Latin America. Now, a report can comprise several pages, and a single page in a report may include a number of related charts which can be used to form a dashboard, where an interaction with a single visual in a dashboard can affect all of the others. And within a dashboard, each individual visualization can be termed a tile. Tiles themselves can be individually configured for their aesthetics and also for the information they convey. So you can think of each of these ingredients we have now discussed as the fundamental building blocks of Power BI. And all of these come together to tell a story which can drive business decisions. And now let's take a closer look at one more crucial ingredient in Power BI, which is the Data Analysis Expression Language, also known as DAX. Now, DAX is not exclusive to Power BI. It is also available in Excel's Power Pivot and also Microsoft's analysis services. What is common here is that DAX is used for data analysis. As touched upon previously, DAX is quite similar to formulas in Microsoft Excel. However, it includes a whole host of functions as well as operators which are specifically catered towards data analysis. So much like with Excel formulas, DAX can be used to create calculated columns, but you could also create calculated tables. Furthermore, DAX is the best way to create something known as measures in Power BI. You can think of measures as simply computed values which can be referenced as variables. So these values may be computed by filtering the contents of a dataset and then performing an aggregation of the values which remain, for example. So in a dataset of cell phone sales, you may have a measure which gives you the total volume of sales in the country of France. Now DAX is extremely powerful, and some of the formulas are also a tad complex, which means that to get things right, you will probably need to play around with the formulas a little bit. So it helps to keep the DAX reference page handy. Now we have discussed that data in Power BI can be sourced from a variety of different sources, and in fact, these sources may be located either on premises or even in the cloud. In fact, you may have some data sources on premises while others reside on the cloud, and all of the hosts in here may be connected by some virtual network. So you may have some kind of hybrid network in here. All of this is not a problem at all for Power BI. So it can work with both on-premises and cloud data, and as you might expect with a Microsoft product, it integrates rather seamlessly with the Azure cloud platform. So the big takeaway here is that Power BI can work with data sources which are either on-premises or on the cloud, in which case it helps to know that there is something called the on-premises data gateway. To understand this, let's take the example of a company or an industry which is subject to regulations which require that the organization has to maintain its data within its own premises. So if you are in the medical or financial field, this may be a regulation which you need to ensure compliance with. However, the data which is stored on premises may still need to be accessed from a cloud-hosted service such as the Power BI service. So the data will be hosted on premises. However, it needs to be accessible from a cloud-hosted service so that analysis can be performed. And for this to happen, well, an on-premises data gateway can be used. This effectively works as a bridge between your on-premises data and the cloud-based Power BI service. Much like the DAX language, the on-premises data gateway is not exclusive to Power BI and can also work with other Microsoft services. With that said, we can quickly cover the different types of data gateways. The first of these is personal mode, which allows a single user to connect to the on-premises data, whereas the full-fledged on-premises data gateway allows multiple connections. This can be accomplished with the installation of a single gateway, and then there is also the virtual network data gateway, where no installation is needed and you can still have multiple users connect to a variety of different sources. We can now also quickly discuss the connection between Microsoft's Azure Cloud Platform and Power BI. As you might expect, Power BI integrates rather seamlessly with Azure services. For example, the source of your data which is loaded into Power BI could be an Azure SQL database. It could also be Azure's big data offering of HD Insight, and you could also get your data from the Azure Storage Service. Data can also be streamed into Power BI from Azure's Stream Analytics and Event Hubs. And while these cover the sources of data, once you have built your Power BI visualizations and reports, well, these can be embedded into applications using APIs and SDKs. So for instance, you could write a Python application which references a Power BI dashboard. And let's wrap things up with a quick discussion of the different storage modes in Power BI. So the storage mode effectively determines where exactly the data underlying the visualization is stored. More precisely, whether the data is cached in memory or whether the visualization queries the underlying data source for the latest data. As you can imagine, caching might give you better overall performance for your visualizations, since all of the data can be available with a simple memory reference. However, like with any cache, there is the risk that the data has gone stale, where a value in the original data source may have changed, but that change has not been pushed through to the cache. When it comes to performing data analysis, you may not really need data which is near real time, in which case you may as well optimize for performance and cache the data. So broadly speaking, the storage modes in Power BI determine whether data is cached or not. And in this regard, there are three different storage modes on offer. The first of these is import mode, where an entire table is cached, and any queries against the data, and this includes references to the data from a visualization, will go against the data in memory. This is as opposed to the direct query mode, where the data is not cached and any references to the data will in effect run a query against the underlying data source. Keep in mind that the direct query mode is not available for all data sources. For example, it is available for a variety of relational databases, but not for flat files. Now, if you'd like a hybrid of these two approaches, Power BI also supports a dual storage mode. This is where some data is cached and the rest is not. The goal of this course was to orient you towards the DA-100 certification exam, introduce you to data analysis and the role of Power BI in this process. You kick things off with a brief overview of the DA-100 certification test, including how you can sign up and prepare for the test, as well as some of the exam-related mechanics. You got an idea of what skills you will be tested on, and also how you can set things up for an online exam. You then began a deep dive into data analysis. Here you covered the different types of tasks which data analysis involves, the different roles within data analysis, and their respective scopes in the entire process. You delved into steps such as identifying data sources, cleaning and transforming data, building visualizations, and combining them into reports. You also covered the scopes of roles such as business analyst and data scientist, including how these relate to a data analyst. Finally, you covered the role of Power BI in the entire data analysis pipeline. This included its components, namely Power BI Desktop, the Power BI Service, and Power BI mobile apps. You also got a glimpse into the essential building blocks and features of Power BI, which simplify a lot of the tasks involved in transforming raw data into insightful reports, which can then be used to drive business decisions. Now that you have come to the end of this course, you have a clear theoretical understanding of what data analysis is, how Power BI makes this process very smooth, and significantly, the type of skills you will be tested on for the DA-100 certification for data analysis. This has set you up to move on to hands-on courses which cover the preparation of data for analysis in Power BI. We now begin with the demos of this learning path on Power BI. And as you might expect, the first thing we will do is to install Power BI, more precisely, Power BI Desktop. And for this, I have just brought up my browser, and one simple way to find the download page is to just search for Download Microsoft Power BI Desktop. Before we proceed, however, I'd like to point out that at least at the time of this recording, Power BI Desktop is only available for Windows and is not an option for macOS. So, I am assuming that you are running on a Windows machine, in which case, we can continue with the search. The first result should point you to a Power BI page, and you can see that this is available at powerbi.microsoft.com/the language and region/downloads. I'm just going to click on this link, and you can see the full URL in the browser now, along with a quick overview of Power BI Desktop. You will recall that in the life cycle of a Power BI report, things start off with the Power BI Desktop, where we can connect to data sources, apply transformations on the data, and then use it in order to build reports. The reports can then be moved into the Power BI service, which is a cloud-based service available on the Power BI website. Reports can also then be accessed from Power BI Mobile, and you can see from this page that the app is available for different mobile platforms. If you'd like to keep all of your data on premises for compliance reasons, well, you could make use of the Microsoft On-Premises Data Gateway, as well as host a Power BI report server within your own organization. There is also the Power BI Report Builder utility, and you can think of this as a limited version of Power BI Desktop, which is focused on building paginated reports. Alright then, now that we have some idea of the Power BI universe, let's just move along and head over to the Power BI Desktop main page. And then from here, well, there is the link to download it. However, if you'd like any additional information about Power BI, feel free to scroll over this page and refer to it anytime. However, for now, let's just move ahead with the download. So I'm going to scroll back up and then click on this download link. And you will notice that this is not a way for us to download the installer directly, but will in fact direct us over to the Microsoft Store. So let's just choose to open it within the store itself. And sure enough, we are taken over to the Power BI Desktop page within the store. You can, of course, scroll along to get additional details about Power BI Desktop here, including the system requirements, reviews, and so on. We will, however, proceed with the download by clicking on the Get button. And at this point, well, there are a couple of options available to you. You'll see that in my case, I'm signing in with a Microsoft account created out of a personal Gmail account, which I have created specifically for the demos in this learning path. This is the easiest way to work with the free version of Power BI Desktop. And if you do use a corporate account, well, there are a few additional steps which are beyond the scope of this learning path. So let's just proceed with a Microsoft account then. And as with many downloads from the Microsoft Store, we'll be prompted for a password. So I'll just provide my Microsoft password. And then, in a few seconds, we should have the link available in order to install Power BI Desktop. So I'll just choose this option, at which point the installer gets downloaded, and then there is the option to launch. So I'll just go ahead and click. And this is where Power BI Desktop should open up on your machine. I'm just going to go ahead and close this welcome screen. And this is the main dashboard of Power BI Desktop. Let's now take a few moments to get ourselves oriented with this particular dashboard. So you can see that the look is very similar to a lot of Microsoft utilities. So we have the ribbon at the top, where we are currently in the home menu, and this includes a lot of ways to import data into Power BI Desktop. So you can see a Get Data button. There is also Excel Workbook in order to load data into Power BI from a Microsoft Excel file. And we can also load data by connecting to a SQL Server instance. We will explore these in depth a little later in this path. You'll also observe that there is an option to transform data, which is something we will also work with. And then there are also ribbons for insert, modeling, view, and help. And then towards the right, you will see that there are menus, including ones for visualizations, and there are a number of different options here. These are the different visualizations or charts which we can build out of the data which is loaded into Power BI. There is also the filters menu where we can apply filters on the loaded data. And once the data has been loaded into Power BI desktop, they will be transformed into tables which can be accessed from this fields menu. And sure enough, there is no data in Power BI desktop just yet. Before we do in fact load data, we need to explore three of the crucial buttons within Power BI desktop. These are the three buttons which appear along a vertical line towards the left of this page. The top one is for the reports pane, which is where we can construct Power BI reports with visualizations. And in fact, this is where we are right now, since the visualizations panel is available here. And towards the bottom of the page, you will see that this is page 1 of a report. So it is possible for us to create reports with multiple pages. Moving along then, the next menu item here is for the data pane. This is where we can view any data which is loaded into Power BI desktop in tabular format and also apply some form of transformations on that data, such as creating calculated columns. And then there is the model view of the data. This is where we can define the relationships between the different tables loaded into Power BI desktop. Furthermore, we can also view the relationships here and make sure that everything has been modeled correctly. So now that you have some idea of how Power BI desktop is set up, I'll just give you a quick example of how it is used. We will typically load data from one or more sources. We can model the data from this view, take a look at the data from the data view, and then build reports from the reports view. All of this will be done soon enough, of course. And in the next video, we will kick things off by loading data into Power BI from various sources. Having downloaded and installed Power BI Desktop on our machines, it's now time for us to continue working our way towards building a Power BI report. And the next step is for us to load data into Power BI Desktop. Before we get to that, however, even though we haven't really done anything within Power BI Desktop yet, let's just save things down so that we have a file where all of our work within Power BI Desktop will be saved. So we can head over to the File menu and choose the option to save as. And then within our file system, we can save down a PBIX file. This is a special Power BI file, and this includes connections to data sources, any transformations applied on the data, as well as any reports created from the data. So let's just create this PBIX file. And of course, as with any file or report, it is good practice to periodically save things down so that any changes are not lost. Alright then, it's now time for us to bring data into Power BI Desktop. And the first kind of file which we will load data from is a Microsoft Excel file. Before connecting it to Power BI Desktop, let me show you the file itself. So the name of this Excel file is Amazon Books, and as you can see, it contains details about various books which were available on sale on Amazon.com. And while this dataset is part of the course materials, you could also download it from this URL on Kaggle.com. For the purposes of this demo, however, what exactly this dataset contains is not quite as relevant as the types of data present here. You'll observe that there are a total of 7 columns. The first 2 of these contain text values, and then we have 4 columns containing numeric values. Once we load the data into Power BI, we can take a look at exactly how Power BI treats each of these columns and whether it automatically detects the types. Alright then, so now that we have an idea of what the data looks like, I'll point out the fact that this dataset contains 600 rows of data, beyond the header. Alright then, it's now time for us to load it into Power BI, for which we switch back over to Power BI Desktop. And then, while we could use the shortcut in order to load data from an Excel workbook, let's instead take a look at the Get Data menu, where you immediately get a taste for the different types of data sources we can connect to from Power BI Desktop. So you'll observe that beyond the shortcuts we have already covered, there is also the option for text/CSV to load data from a flat file. We will cover that a little later. There is also the option to connect to a web source. For example, we could load an HTML table into Power BI. And while this does seem like a diverse set of sources to which to connect, this is in fact just a small subset. In order to view the full set, we choose the More option. And this is where we can navigate to the different types of data which can be loaded into Power BI. And given that there are so many different types of sources we can connect to, these in fact have been categorized into files, databases, Azure services, and so on. In the All menu, right at the top, you will observe Excel workbooks, text or CSV files, XML, and JSON files are right at the top. And this is because these are typically the most common data sources from which data is imported into Power BI Desktop. In fact, there may even be questions in the DA-100 certification exam with regards to these data sources. And while we could scroll through all of these in here, let's just quickly take a look at each of the menus, or at least the important ones, starting with File, where you'll observe that in addition to the file formats we already discussed, we can also load data from a PDF file. In the Database menu, right at the top are the two Microsoft-related databases, SQL Server as well as Microsoft Access. Other popular relational databases can also be connected to, including Oracle, MySQL, and Postgres. There are also cloud-based databases such as Amazon Redshift, which we can use to load data into Power BI. And scrolling further along, well, as you might expect, there are a whole host of databases here. When connecting to relational databases, keep in mind that it is possible for us to make use of the DirectQuery storage model, where the data is not cached by Power BI, but each time data is requested, it is directly queried from the original data source. Moving along then to Power Platform. It is possible for us to create a hybrid between a direct query storage model and an import storage model where all of the data is cached. This data can be stored in the form of a Power BI dataset, and we could connect to it from a Power BI desktop report. And as you might expect, there are a whole host of Azure services which we can load data from. Azure SQL is a relational database. We can also connect to Azure's offering of PostgreSQL, for example, but we're not just restricted to relational databases here. Azure's Cosmos DB is a NoSQL database which we can also load data from. And then there is also Azure HD Insight, which is a big data platform on Azure. And while the options we have covered so far can be considered traditional data sources, when you head over to online services, you'll observe that the sheer variety of data sources which Power BI Desktop can connect to is in fact quite vast. We can load data from SharePoint as well, and also Google Analytics, making it quite easy to build reports from these sources and analyze the data. Let's move along then to the last of the menu options, which covers other data sources, which cannot be easily categorized. At the top, there is a web source where we can connect to HTML tables available on a particular web page and analyze the data in such a table. If we happen to have R or Python scripts which generate datasets, well, we could also connect to those from within Power BI. Alright then, now that you have an idea of how exactly we can load data into Power BI, and in fact recognize that there are a whole host of sources, let's return our focus once again to the Excel workbook source, since that is the type of data we now wish to load into Power BI. So once this selection is made, on our file systems, let's navigate over to the location where the Amazon Books dataset is located, and keep in mind that this dataset is part of the course materials, so you can just download it from there. to give you an idea of the different Excel formats which are supported, we can load data from Excel, XLSX, or XLSM files, and even the old XLS format is supported. Alright then, let's move on and open up this Excel data source in Power BI Desktop. And at this point, we will have the option to select the worksheets from within the Excel file which we want loaded into Power BI. In the case of our data source, however, there is just a single sheet called Sheet 1. So I'm just going to select that. And here we can take a look at the same 7 columns which we did just moments ago. And scrolling along, you can see that the data has in fact been truncated so that we just get a preview of the available data. And now we have the option to hit the load button, in which case the dataset will be loaded using all of the default settings. However, if you'd like to apply some transformations before the data is loaded, well, we can choose the transform data option. And once we do that, well, it is Power BI's Power Query Editor which pops up. If you have used Microsoft Excel before, it is possible that you have performed data analysis using Power Query within Excel. It is in fact the same Power Query which is available in Power BI as well, and this allows us to manage and manipulate any data which is loaded into Power BI. There will be many occasions where the data set which we are connecting to will not have the data in the exact same format which we need for our Power BI reports, and we will need to transform the data in order to work with it. As you can imagine, there are innumerable number of transformations which can be applied to data, but we will cover most of the important ones later on in this learning path. For now, however, let's stick to the basics. In the query settings menu on the right, we can set a name to this dataset. So I'm just going to call this Amazon Books. And just below that, you can see all of the different steps which have been applied to load and transform this data source. The first of these is to connect to the source itself, which involves navigation to a file in the file system. And then there are 2 transformations which have been automatically applied. The first step was to promote the headers, and this is where line number 1 of the dataset was considered a header row, which is why in the data grid, you'll observe that name, author, user rating appear as headers rather than as data directly. So the promotion of the first row to a header is something which happens by default and is something you can undo for a dataset by clicking the cancel button next to the applied step. That button is visible for the last of the applied steps, which is changed type, and this is where the types were automatically detected by Power BI, or more precisely Power Query, and applied to each of the columns. You'll observe that there is a symbol ABC which appears next to the name and author columns, pointing to the fact that these are treated as strings, and then there is the symbol 1.2 next to user rating, pointing to the fact that this column is treated as one having decimal numbers. Scrolling along, you will see that the reviews and price columns contain whole numbers, and this is denoted by the symbol 123. And in fact, the year column is also treated as a whole number here. And then the genre, of course, is treated as text. If these automatically detected and applied types don't work for you, you can cancel this change type step in Power Query Editor. Alright then, once you've confirmed what the data looks like, let's head over to the Close and Apply menu option here so that we can accept all of the transformations and loading which has been automatically applied. And once we do that, well, soon enough, the data will be available within Power BI Desktop. Keep in mind that the storage mode which has been applied when loading an Excel file is import. DirectQuery is not available when it comes to Excel files, which means that all of the data which we just loaded is automatically cached. And now that we are in the reports view of Power BI Desktop, well, in the fields menu on the right, you can see the Amazon Books data which we just loaded. You can also see the 7 different fields within that dataset which can be accessed here. And then there are summation signs next to the numeric fields of price, reviews, user rating, and year, since that data can be aggregated. Moving along then from the report view over to the data view, where the raw data is available for us to take a look at. And we can scroll down and take a look at all of the 600 rows of data. And finally, there is the model view. Given that there is just a single table, there is not much of a model at the moment, but we will of course explore this in depth later on in this path. In the previous video, we loaded data from a Microsoft Excel file into Power BI Desktop. This was done in import mode, which means that all of the data within that file will be cached in Power BI, and this is the only option available for an Excel file, and that is also the case with flat files. Speaking of which, we will now focus on loading data from a CSV flat file. For which, let me first head over to the report view and then switch windows over to the CSV file which I have opened up in Microsoft Excel. So let's quickly take a look at what exactly this file contains. It includes statistics with regards to the production of honey across various states in the United States for a handful of years. Again, the exact contents of the dataset is not important at the moment, beyond the structure and the type of data. So out of these 8 columns, it is just the first one which contains string data. All the others are numeric. While most of the columns contain whole numbers, column F, containing the price per pound, contains a decimal value. Furthermore, you'll observe that row number 1 in the CSV file contains a header. So let's see whether this is automatically promoted to a header by Power Query when we load this into Power BI. So let's just scroll along and confirm that there are a total of a little over 600 rows of data. Again, this file is part of the course materials, or alternatively, you can download it from this URL on kaggle.com. And once again, given that this is a flat file, the data will be loaded into Power BI in import mode. Switching back over to Power BI Desktop then, let's expand the Get Data menu and choose the option for text or CSV file. And then we navigate over on our file systems over to this honey production dataset. And towards the bottom right, you can see that the text files supported include .txt, .csv, and .prn. Let's just choose to open up this honey production.csv file. And at this point, well, we are given a preview of the data itself, where we can configure some of the details of the data source. First of all, we can set the file origin, which by default has been selected as Western European Windows in my case. We can also explicitly specify the delimiter. So this has automatically detected that it is a comma which serves as a delimiter, but in case you have tab delimited file for instance, well, you can specify it right here. Once again, Power BI will try its best to automatically detect the types based on the contents of the columns. Here, you can specify whether the type detection should be based on the first 200 rows, which is the default selection. You could also consider the entire dataset in case it's not too large in order to slow things down. Or alternatively, you could choose to explicitly set the types yourself, in which case you'll choose not to detect the data types. This time, rather than applying any transformations via Power Query Editor, let's choose to load with the default settings. And then in a few seconds, well, the data will be available in Power BI Desktop. And in fact, you can see in the right, in the Fields menu, that alongside the Amazon Books dataset, the honey production data is also available for us. At this point, I will bring your attention to the naming convention which is typically adopted when working with data in Power BI. So you'll observe that the honey production data is available in a table called honey production in all lowercase, and this is because it is the name of the CSV file which has been automatically adopted to name the table. It is the convention adopted for the Amazon Books table, which is more standard when it comes to Power BI. So in order to rename this table, I'm just going to click on the ellipsis here and then choose the option to rename and then set a name of honey production, where honey and production are two separate names and the first letters in each word are capitalized. So once again, this is a general naming convention for Power BI tables, but there is no rule around what the format should be. Once this naming has taken effect, let's just expand this particular table and take a look at the different columns. You can see that aside from the state column, each of the others can be summarized since they're all numeric. Let's move along then to the data view. So in here, once again, we have Amazon Books and Honey Production, which can be accessed. And by default, it is Amazon Books, which is on view. Let's just click on Honey Production from this right menu in order to bring up that data set. And now we can scroll along over this data and take a look at what exactly it contains. Next though, let's head over to the model view. And we now have two different tables, Amazon Books and Honey Production. And given that these are two entirely independent data sets with no possible connection between them, well, we cannot really use this model view in order to set up a relationship. In fact, we won't really be focusing on relationships in this learning path and will instead turn our attention towards the different types of data sources which can be loaded into Power BI and the transformations which can be applied. Let's head over then back to the Report tab, and having successfully loaded data from an Excel file and then a CSV file into Microsoft's Power BI, let's focus on one more type of file, and this is an XML file. So I just brought this up in a text editor on my machine, and you'll observe that it contains information about a lot of laptops available for sale on some e-commerce platform. While this is part of your source material, you can also download it from this location on kaggle.com. Taking a quick look at this file, you'll observe that it contains a number of row elements within a top-level root element. Each row element represents a specific laptop, and each of these is described by a number of different fields, a total of 13 to be precise. These include a number of string fields such as the name of the company, the product name, as well as the CPU and GPU. And then there is the price in euros field, which is a numeric value. The challenge for Power BI is to transform this XML data into a tabular structure, and you can see from the structure here that each row element can in fact be transformed into a row in a table. You can just scroll along to take a look at each of the elements in this file. But now let's switch back over to Power BI, expand the Get Data menu, and then in order to access an XML file, we will need to choose the More option and then choose the option of XML. When we hit Connect, we'll need to navigate over on our file systems to the XML file. So I'll just head over to laptops.xml, and when brought up in Power BI, well, at first, we will need to decide exactly which of the elements will be imported. Given that there are a number of row elements, I'm just going to make this selection, and you can see that each row has automatically been transformed into a row in a table. Moreover, the names of each of the fields in each row element have been converted to column headers. These include the GPU, operating system, weight, and price in euros fields. Once we have taken a look at the data, well, we could choose to load with the default transformations. However, let's pull up the Power Query editor by choosing to transform the data. And sure enough, this pulls up the Power Query editor. And at this point, we will make some transformations, though nothing too complex. You'll observe in the Applied Steps menu on the right that the types for the different columns have been adjusted. And in fact, you can see that the column field 1 on the left is a numeric value, and then each of the other three columns in view, company, product, and type name, are of type string. First, however, let's give a more meaningful name to this particular data set. I'm just going to call this laptop details. And then looking at the field 1 column, well, you could say that this doesn't really make sense including it in our data set. This is because this is effectively a serial number into the rows of our data, and if this is not really required, well, it is best to do away with it. One of the reasons for this is to keep things simple. One of the best practices when it comes to working with Power BI is to make sure that we only include the data which we need and eliminate any unnecessary columns or rows. So I'm just going to right click and then choose to delete this column, which gives us a slightly trimmed version of the dataset. And you can see in the Applied Steps menu on the right that a removed column step has now been included. Again, this step can be undone by hitting the Cancel button right next to the step. Another benefit of having fewer columns to work with is that it means there is less space occupied in memory. Once again, this XML file has been loaded in import mode, which means that it is cached in our system's memory and will also be cached by the Power BI service once we move this report over to it. By eliminating unnecessary data, we ensure that only the required data is loaded into memory, and thus more memory is available for other purposes. Let's move along then and apply the changes we have made by clicking on the Close and Apply button here. And soon enough, Laptop Details is now loaded into Power BI Desktop. By expanding it, we can confirm that there are just two numeric fields here, inches and the price in euros. Let's quickly take a look at the data view. So it is the honey production data set which has been selected. And by choosing Laptop Details, we can take a look at the data which is present in here. So scrolling along, we can see that even though the RAM as well as weight columns convey numeric values, the fact that the units of GB and kg are included here mean that they have to be treated as strings. There are transformations which can be applied in order to separate the numbers from the units, but for now, that is not what we will focus on. Once we have taken a look at all of the data, well, let's head over to the model view, and along with Amazon Books and the unrelated honey production, we also have the completely unrelated laptop details. So there is no work to be done in the model view. But now that we have successfully loaded CSV and XML data into Power BI Desktop, in the next video, we will focus on connecting to a JSON data source. Previously in this course, we have successfully loaded data from a Microsoft Excel file into Power BI. So this is in the Amazon Books table. And then we loaded data from a CSV file into the honey production table. And then there is the laptop details table containing data sourced from an XML file. We will now load information from a JSON file. And we will see that there are a few additional steps which we'll need to perform in order to get that data into a Power BI table. First, I'll give you a glimpse of the JSON file itself. So this is one called USA Cars Dataset.json, and it contains information about various cars which are put up for sale in the United States. The dataset can be downloaded from this location on kaggle.com, and it is also part of the course materials. So overall, you can see that the structure is not very different from the XML file which we just took a look at. So right at the top level, there is the JSON array indicated by the opening square bracket on line number 1. And this is followed by a number of elements which are defined as JSON objects. The first one, defined between lines 2 and 16, represents a specific vehicle, that is a Toyota Cruiser, which has been put up for sale in the state of New Jersey. The goal is for this JSON object to be transformed into a row in a table, and each of the fields will be represented as separate columns. You'll observe that there are a few numeric fields in here, including the price, year, and mileage, and a number of different text fields. Scrolling further along, well, there are hundreds of cars in this dataset, but now let's switch over back to Power BI and choose to load the JSON data. Once again, we head to Get Data and then More. And then from the All menu, well, option number 4 is that of a JSON file. Let's make that selection to connect to the JSON file. We can then locate the USA Cars dataset on our file system and then pull it up. And automatically, it is the Power Query editor which comes up. And this is where things are a little different with regards to the other data sources which we have explored. In the applied steps, you'll observe that all we have really done is to connect to the data source. And then as for the data itself, as of now, we only have a list column, and this is in fact a list of different records. Each record in here represents a single JSON object in the original data source, and we can scroll along and confirm that each of these records is in fact clickable. I'm just going to click on the first of these, and what comes up is the first JSON object within our JSON file, representing the Toyota Cruiser which is up for sale in New Jersey. Now, the clicking on this record has been recorded as an applied step, specifically a navigation. However, this is not a step we wish to include in the final transformation. So we need to undo this. And for that, I'll just head back over to the source step, where we're once again back to a list of records, and then choose the option to cancel the navigation step. So that has been eliminated. But you see that if you were to click on one more record, well, this pulls up one more vehicle object represented in the form of a table in here. So let's just head back over to the source step, cancel the most recent navigation step, and let's focus on converting this into a table. And for that, well, conveniently enough, there is this to table option in the top left. And once we hit it, well, we can define how exactly this JSON structure needs to be transformed into a table. You'll observe that this to table transformation is available for any kind of structure containing a list of values, and we could specify a delimiter which has been set to none in this case. While there are a few options available, let's just stick with the default, and then there is also the option to decide how exactly we will handle extra columns. This is something which can come into play. For example, if the different objects in a JSON array have different sets of fields. While we could truncate extra columns in order to only retain those which are common to all objects, well, let's choose to mark extra columns as errors. Then when we hit OK, well, some transformation has been applied. Along the right, we can see that the structure has been converted to a table rather than a list. However, you'll observe that there is an option to expand this table. When we click on this expand button, well, within that there are a number of different columns which have already been picked from the fields in our JSON objects. This is because the table in its current form is in fact a table of tables, where each JSON object is treated as a separate one, but now we have the option to expand it into a flattened table. Let's see exactly how this expansion occurs. First, however, we can uncheck the box in order to use the original names of the columns as a prefix. And then when we hit OK, well, this is what we end up with. So we have the index column at the very left, along with the price, brand, model, and then year columns. And you'll notice that the icon pointing to the type in each of these columns says ABC123, which in fact represents alphanumeric columns. Now the price column contains purely numeric data. However, in the applied steps pane, you'll observe that there is no data conversion which has been applied. So this is something we will need to perform explicitly. Scrolling further along, you can see that all of the fields have been marked as alphanumeric. Alright then, how exactly can we set the numeric fields to a numeric type? Well, one way to make use of the built-in data transformer available in Power Query is to first head over to the transform menu, and then, well, we can just make use of the automatic type detector by hitting the detect data type button. And you'll immediately see that the change type step has appeared in the applied steps pane, and significantly, you'll observe that the symbol 123 appears next to the index and price columns. So Power Query has picked up on the fact that there are just numbers in these columns. You will notice that the brand and model columns have slightly different types. In the case of the brand column, this is purely alphabetic, given that just ABC appears as the symbol. And in the case of the model, since this can be just numbers or even text, well, this is alphanumeric in nature. And then as we scroll along, we can confirm the types as well as the contents of each of the other columns as well. And with that, our JSON data file is now ready to be loaded into Power BI. For that to happen, let's just hit close and apply. And in a few seconds, sure enough, the USA cars dataset is available as a table. Expanding it, well, we can see that some of the columns in here, such as the mileage and the year, can be summarized since these are purely numeric. Let's just go ahead and rename this data table. we'll just give it a name of Cars USA to stick with the naming convention we have used so far. Let's quickly head over to the data view, where we can navigate over to Cars USA and confirm the contents of this data table. So we have now successfully loaded the contents of a JSON file into Power BI. And keep in mind some of the steps which we executed, since related questions may appear in the certification exam. Now let's move along and then take a look at some of the individual columns in this data table. When choosing the brand table, take a look at some of the information which appears in the top menu. Here we can rename the table. So this has a name of brand right now. We can also select a data type to be applied from the data type menu. So this has been set as text right now. And we can also specify a format. This is especially useful for numbers, where we can set percentage symbols or currency symbols to appear. Heading over to the price column, well, you can see that the data type here is whole number. This is as opposed to decimal numbers, which can apply to certain fields. Furthermore, you can see under the property submenu that the default summarization for this particular column is set to sum. This means that when we aggregate based on price in our visualization, by default, the prices will be summed up. If you find that the average price is a better representation of how the price column needs to be used, well, you could apply that summarization instead. We will get to all of that later on. Next, when we take a look at the mileage column, well, this is broadly similar to the price column. You'll also notice that there is a data category setting which we can adjust, and this will allow us to categorize the data based on the contents of this column. Let's head over to the model view then. So just to confirm, there is the Cars USA table which appears. And of course, none of these tables are related. Alright then, heading back over to the Reports tab, having covered the loading of JSON data into Power BI, next, we will focus on connecting to a SQL Server instance. So far in this course, we have focused on loading data into Power BI from a variety of different file sources. Now, however, we will connect to a SQL Server instance, and you'll observe that the steps involved are a little different from what we have covered so far. So from Power BI Desktop, we can import data from SQL Server. However, before we do that, let me just pull up a SQL Server instance which I have running on my own local machine. If you do have access to SQL Server, well, I recommend that you do try to connect to it and follow along with me in this demo. In any case, let's take a look at what exactly is present within the SQL Server. Expanding it, well, I'll just also open up the Databases menu, and you'll notice that there is one called SalesDB which is present here. This is a database which I have already created in the background, and this includes a handful of tables that have already been loaded with data. Expanding the tables, you will notice that there are 3 different tables in here. There is one called PS4 game sales, another one for video game sales, and then Xbox One game sales. Keep in mind that this database is available as part of your course materials. Alternatively, you could download the data from this location on kaggle.com. Before we load this data into Power BI Desktop, let's quickly take a look at the contents of the tables in here. For that to happen, I'm just going to right-click on the database server and then choose New Query. This will pop up a query editor, where I'll just go ahead and paste in a rather simple query to select information from the video game sales database table. First, I'm going to run the command use salesdb so that it becomes the current database, and then we'll simply run select star from dbo.videogamesales. When we hit the execute button, well, all of the contents of the video game sales table shows up in the query results section, and you can confirm that this includes data about the sales of video games in a number of different regions in the world. Given that this information is already in a tabular format, well, loading it into Power BI Desktop should not really prove that complicated. However, there are a few steps which we will need to follow. First, we will need the server at which this database is hosted, and this is possible for us to retrieve from a query. So I'm just going to run select at server name, and at least in my case, since this is running on my local machine, this is the result which is returned. From the results, I'll just right click and choose to copy this. And now we can plug it into Power BI in order to import data from this database server. Heading back over to Power BI desktop then, and then choosing to load data from SQL Server. In the form which comes up, well, in the server section, let's just paste in the server name which we retrieved from SQL Server. And following that, well, we could optionally leave the database portion blank, in which case all of the different database schemas present on the database server instance will be loaded into Power BI. However, a best practice when it comes to loading information into Power BI is for us to only retrieve what we really need. This makes data easier to handle within Power BI, and beyond that, it can also improve performance if we happen to load data in import mode. And you can see that this is the default data connectivity mode in here. More on that just a little later. First, I will make sure that we only pull in the tables from the SalesDB database schema. And then, well, there are two options available to us as far as the storage mode is concerned. You will recall that import mode is where all of the data in the data source will be cached by Power BI. This generally results in better performance since all of the data can be pulled in from memory. However, this does come at the cost of data potentially being a little stale. Furthermore, if there is a lot of data to pull in, well, a lot of memory resources will be consumed potentially unnecessarily. The alternative, of course, is DirectQuery. This is where the data is not cached by Power BI, and instead, each time the information is needed, a query will be sent to the underlying data source. For now, however, let's just stick with the import mode and instead take a look at the advanced options. And this is where we can be a little more specific about the data we wish to load from the SQL Server source we are connecting to. For example, in the SQL statement section, we can specify a SQL query so that only specific columns from specific tables in the schema we're connecting to will be loaded into Power BI. Once again, this is one way to limit the size of the data we bring into the Power BI system, and this is an option you should make use of if you don't need all of the data in the connected database schema. Furthermore, you will observe that there is an option for us to specify a command timeout, and we can also choose to include all of the columns required to establish relationships between the tables. To keep things simple for now, however, let's just collapse the advanced options and choose to hit OK so that we pull in all of the data from the SalesDB database residing on the SQL Server instance, and we will do this in import mode. And in a few moments, well, this navigator pane should pop up, and this is where we can specify exactly what we want loaded into Power BI desktop. So there are three different tables available in the schema which we pointed to, and we can still choose which ones we want loaded into Power BI. Sure enough, we can preview all of the data here, and this is what we have in the PS4 game sales table. Heading over to Xbox One game sales, again you can see that there is just a lot of information about various Xbox games, and then there is the video game sales table, which we already checked out within the SQL Server. And in fact, this is the only database table which we will load into Power BI, and we will do so with the default settings. So I'm just going to hit the load button here. And in a few moments, towards the right, you can see video game sales now appears. I'll just collapse the Cars USA table here, and then expanding video game sales. Sure enough, all of the columns are available here. And then heading over to the data view, and then over to the newly loaded data table. Well, this is what video game sales looks like inside of Power BI. So we now know how to connect to a relational database from within Power BI, and we also know that with such sources, it is possible for us to connect in DirectQuery mode. We will explore DirectQuery in a little more depth later on in this learning path, but now that we have covered a variety of different data sources which can be connected to and then pulled into Power BI desktop, well, starting from the next video, we will focus on transforming this data. So far in this course, our focus has been on connecting to a variety of different data sources from Power BI, but now we will turn our attention towards transforming data. However, we will continue looking at new sources which we can connect to. In fact, we will now pull data from an HTML data source, more precisely an HTML table. For that, I'm just going to pull up my web browser and then navigate over to this URL on espn.com. This is the page which will give us the medal counts from the 2008 Summer Olympics held in China. And this is what the medal counts looks like. More than the contents itself, let's focus on the structure of this information. So we have here an HTML table, which includes two different country columns, one containing the image of a flag and the other one the name of the country. And then there are four different columns pointing to the medal counts, one each for gold, silver, bronze, and the sum of all medals. Scrolling further down, we can see that this includes a rather large set of countries. So this data is not unlike any of the other data which we have seen loaded into Power BI in the form of a table. However, of course, there are a few complications in here. There is, of course, the image contained in one column, and when working with HTML data, there might just be some formatting information which creeps in which case, to work with the data in Power BI, we will need to apply some transformations, and that is what we will focus on. In this example though, we are dealing with a rather static data set, since it is highly unlikely that the medal counts from the 2008 Olympics are going to change anytime. However, it is possible that if you are working with an HTML source in your Power BI reports, you will be pointing to a table which gets updated dynamically. In any case, to connect to the table, we will need to copy over the URL. So once that is done, let's head back over to Power BI and then from the Get Data menu, choose the option of Web. And in the form which comes up, this is where we can specify the URL, and in the basic configuration, we will load the data with the default settings. Alternatively, we can pull up the advanced settings, and here we can specify a command timeout when loading the data from the web source. However, keep in mind that the data will be loaded in import mode. We won't really be using the advanced settings, and instead heading back over to the basic configuration, we can just paste in the URL to the Summer Olympics medals tally from 2008, and then let's hit OK. As long as your internet connection is fine, well, you should see a single table detected by Power BI, and you may also see one or more suggested tables. First, let's take a look at table 1 which has been picked up, and you can see that this is in fact the same medals tally table which we observed on the web page. Furthermore, you will notice that this table is not quite ready to use just yet. There are no column headers, and we just have the names of column 1, column 2, and so on. And scrolling along, we can see that what should serve as the column headers appear along with the data. So the big takeaway here is that there is work for us to do. Alright then, now that we have taken a look at this data, let's view the suggested table in here. And you'll observe that this is a reoriented medals tally table. So we do have the country name in column 1 along with the gold, silver, and bronze counts and the total count in the next 4 columns. But scrolling along to the side, we see that the data for some more countries and their medals tallies can be viewed here. Now let's just say we are not quite happy with this suggestion, and we would like to define how exactly this information should be presented in Power BI. So let's just select table 1 and then choose to work with this rather than accept it as is. So rather than hitting the load button, let's choose to transform data in the Power Query editor, and soon enough, well, Power Query does pop up and we can take a look at the medals tally in here. In the applied steps, we can see that once we have connected to the source, the data was extracted from the HTML table. However, there is a lot of formatting work which we need to apply in here. Alright then, to begin, rather than call this table table 1, we'll give it a more descriptive name of Olympics medals tally. Next, let's trim our table, especially given that what now appears as column 1 does not contain any real data. In the original HTML file, this is where the country flags were rendered as images. However, that is not something we can work with in Power BI, and this has been loaded as an empty column in effect. So we can just go ahead, right-click and choose to remove this column. And with a trim data set in place, well, our data is looking just a little bit cleaner. Next, you'll observe that the top row at the moment just says total medals by country. This was in effect a super header for the column, but we don't really need this within a Power BI desktop. So let's just go ahead and remove this column, which we can do by heading over to the Reduce Rows menu, and then under Remove Rows, choose the option to remove the top rows. The menu which pops up allows us to specify how many of the top rows need to go, but in our case, we'll just get rid of the first one by setting a value of 1 in here, since the next row can be used as the headers. So when we hit OK, well, there is one fewer row for us to work with. And now to set what currently shows up as row number 1 as the headers for this table, there is a rather simple option. There is this menu option which allows us to promote row number 1 as the header or do the reverse. So let's just choose the former. And now we have what seem to be valid column headers, starting with country, followed by the medal types of gold, silver, and bronze, and finally a total column. Significantly, you will notice that each of the steps which we have performed have been recorded in the applied steps section. So we removed the first column, removed the top row, and then promoted a row as the header. You will notice that this data is not quite ready for use just yet, given that each of the medal counts are treated as strings and not numeric values. This is something we will address a little later, but for now, let's choose to close and apply the transformations. And soon enough, we can confirm that the Olympics medal tally is available in Power BI Desktop. Heading over to the Data tab, and then pulling up the recently loaded table. And here we have it. The medal count is now available, all the way from an HTML page over to Power BI Desktop. So we have now covered some of the transformations which can be applied to data, which is especially relevant when pulling in information from an HTML table. However, in the next video, we will focus on transforming the data types available in our Power BI tables. In the previous video, our focus was on trimming the data from a data source in order to make sure that we only load in the data which we really need into Power BI. We will now focus on modifying some of the columns in the data sets which we have loaded into Power BI. Well, for that, if you are in the Reports tab, well, from the Home menu, you can pull up the Transform Data option and then choose to transform data. This will pull up the Power Query editor, and then from the left, you can select which of the tables which you have loaded you want to apply some transformations to. So let's just say it is the laptop details table which we wish to modify, and once the selection is made, well, sure enough, you can see that the applied steps for the transformations already applied show up in the right. This will allow us to view the data as it was at each stage in the transformations. So for example, when we click on the source, which was the first transformation, well, we can see that it was a row instance which was available as a table. You will recall that this data was loaded from an XML data structure. The next step in the transformation was navigation, and this is where a table was constructed from the XML. At this stage, you will observe that the first of the columns with the header of field 1 was alphabetic in nature. However, the next step changed the type to numeric. This was all done automatically, and this included the change of the type for the price euros column. And then the last of these transformations is something which we did on our own. This is where we removed the field 1 column. Alright then, so this is what the laptop details data looks like at the moment. But now let's focus on transforming one of the columns, specifically the price underscore euros column, which is now set to be a decimal number. But let's just say, for the sake of our reports, we don't really care how many decimal units such prices go into, and we're fine working with whole numbers. In fact, that may even be the preferred option in a lot of reports. Well, for that, we can just right-click on the column header, and then from the Change Type menu, well, there are a number of options available. We could set this to be expressed in percentages. This could also be a fixed decimal number, but let's choose the option of whole number. And straight away, well, the decimal places have disappeared. So now that we have whole numbers in this column, well, consider the fact that it was possible for us to transform decimal numbers into whole numbers. Transformations which are a little trickier, and in fact may not even happen, are when we try to change the contents of a text column such as weight, which is text mainly because it includes kg right next to every number. Well, let's just try to convert this into some numeric form. One more way to apply such a transformation is to head over to the data type menu, and this is where we can choose what data this needs to be transformed to. Let's see what happens if you were to select whole number from here. Well, as you might expect, there are numerous errors which show up. So this is something you need to be mindful of when applying transformations. Make sure that those are valid transformations for the given data. Let's just revert to text data for this weight column then, and at this point, there is the option to either add a new data conversion or simply replace the current conversion which resulted in errors. I'll choose replace current, and we're back to text data, which is a lot more readable. Alright, once we have confirmed that the data has been restored, let's head over to the transform menu, and here there are a number of different options. We will explore some of these. However, I'll just mention a couple of options towards the right where we can point to Python or R scripts in order to apply the transformations. We won't go down that route, however, and instead, let's just expand the honey production dataset. So this includes details about the production of honey across a number of different years in various states in the United States. The last column points to the year in which the information was recorded. And given that this is not quite a number in the sense that some of the other columns are numbers, such as the price per pound, let's see what transformations are available. From right-clicking and then choosing Change Type, let's see what happens if you were to treat this as a date time field instead. So note that the current values are all 1998, at least the rows which are visible, and we are now pointed to the fact that a change of type for this column has already been applied. This was done in the Change Type step available in Applied Steps, and this is where the types for the different columns in this data were automatically modified by Power Query. However, let's see what happens if we were to add this additional step as a transformation of this number over to a date time field. And while what we end up with is a date time, it does not quite point to 1998. Well, it does not even point to the 1st of January of that year, and in fact, it points to a date which is 1998 days into the 20th century. So the 1st of January 1900 is treated as day 1, and when transforming to a date time field, we are effectively meant to specify the number of days from that period. So while this may be perfectly valid in the case of some numeric transformations to date time, this does not quite work for our dataset. So in order to undo this particular change, we need to remove this change type one step. Well, we could just right click and choose to delete, and we are back to having a more readable year. Alright then, let's move along and explore some other transformations. First, let's select the state column, and then we head over to the transform menu and choose to transpose the table, where effectively each row becomes a column in the transform table and each column a row. So when we apply this to this table, well, what was previously the first row pointing to honey production in the state of Alabama in 1998 appears as a new column. And scrolling along, we can confirm that there are now as many columns in this dataset as there were rows in the untransposed version. This of course can be rather hard to read, so let's just cancel or delete this particular step in the transformations. and we're back to our previous data set. So while these transformations may not really work for this data, keep these in mind because these may apply to some of the case studies which will show up in your data analysis certification exam. One more detail to note about this particular dataset is that it is ordered in a specific manner. Specifically, it is ordered by year and by state in ascending order. However, if you'd like to reverse the order, well, you can just choose the reverse rows option. Well, we now have the data sorted in descending order of year and state. We can just scroll along to confirm this, and then let's move along and reverse rows once again so that we're back to the original order, and you'll observe that we are back to the data set as it was before, but there are now two additional steps in the applied steps field. Of course, the more optimum way to do this would be to delete each of those reversed row steps. However, for now, let's focus on the transformations themselves, and in this case, let's simply perform a count rows operation. All this does is to effectively summarize the entire dataset for us and point to us the number of rows which are present. So there are a total of 626 rows. This, of course, is a transformation you will only perform if all you really need is a count of the number of rows and you don't really need any specific details from the data. For now, however, let's continue on with our transformations, first by eliminating the counted row step and then switching our data table over to the laptop details table. This time we will focus on the product column. You will notice that each of the product names which appears here is effectively made up of two words. For example, in the first row we have MacBook Pro, and you can say that MacBook points to a brand name and Pro is the specific model. And similarly on the next line, MacBook is the brand name and Air is the specific type of laptop. Now, what if we wanted to split this column in order to separate the brand name from the model? Well, with the Power Query editor, it is possible for us to perform this separation based on the fact that there is a space separating the two terms. And for that to apply, well, we can head over to the Transform menu, and then from here, choose the option to split a column. You'll observe that there are a number of different ways in which this split can be applied. We can do it by the number of characters, by specific positions, or by a delimiter. Let's just select the delimiter option since we wish to separate using the space character. And then we can specify exactly how the split needs to occur. So we can specify the delimiter itself at first. So this has been automatically selected as space, but you'll observe that there are a few additional options available as well. We can also choose to perform a single split using either the leftmost or rightmost space, or we can split into multiple columns for each space. And this is what I'm going to stick with for now. Taking a look at the advanced options, well, we can split into a number of different columns or even a number of rows if you would like. We can also explicitly define the number of columns we would like to split into. So I'm going to leave this as the default of 2. And let's just keep all of these default settings and choose OK. And you can see that the product column has now been split into two, product.1 and product.2. And the split has been done on the space character. So each of these transformations help work with data which is not quite in the required format at the original data source. For now, however, let's just undo the change which we just applied and then work on the type name column. So depending on exactly what data you're working with, you may need to apply some kind of case conversion. So in the case of type name, let's just say we want everything in uppercase. We can just head over to the format option under the transform menu and choose uppercase. You will notice that the other options available here are lowercase, trim, and we can also add a prefix or suffix. So now that we have transformed this to uppercase, well, let's just confirm that this has indeed taken place and then apply one more transformation. This time to capitalize each individual word in this column, and this is the result. While the single words have been capitalized, well, scrolling along, we can confirm that even the C in convertible for the 2-in-1 convertible laptops has been uppercased. In the previous video, we focused on a number of different transformations which can be applied to the columns of a table and also summarize the dataset as a whole. We will now continue in that vein. First, let's select the company column and will now summarize every element in this column rather than view its raw data by counting the number of characters in each cell. For that, we can head over to the Extract menu, and you can see here that one of the options here is to extract the length of each value in the column. Alternatively, we could also choose to extract the first or the last few characters and also specific text based on delimiters. Before we apply this transformation, let's take a look at what exactly we might expect. For the first two rows containing the text apple, we should expect a value of 5 and the number 2 for HP in row number 3. And sure enough, that is exactly what we see. So, such a transformation can be useful in specific circumstances. For example, if you'd like to know the average length of a name, well, the names themselves don't matter as much as the number of characters they contain. Alright then, let's move along and undo the most recent change which we have applied. So, the step for calculating the text length can be deleted, and then following that, let's continue working with the Extract menu. This time, let's extract the first character from the company column. So when we make this selection, we can specify the number of characters for us to get out of it. So by selecting 1, well, as you might expect, we have A for Apple, H representing HP, and scrolling further down, we also have an L for Lenovo. In the applied steps, you'll observe that extracted first characters now shows up. However, unlike the previous few steps, there is a little gear symbol to its right. When we click on it, you'll see that it is possible for us to modify this particular step. So in this case, let's just say instead of 1 character, we want to extract the first 2. So we just make that change. And sure enough, it is the first 2 characters of each company name which now appears in the company column. Alright, let's just go ahead and delete that most recent transformation. And now, let's see what we can do to combine 2 columns into one. Specifically, let's merge the product and type name columns, since both of these together give a more detailed description of the product itself. So once you select one column, you'll need to use the Control key on your keyboard in order to select the other, and then choose the option to merge. When doing so, well, you can define exactly how this merge needs to take place. You can choose a separator, which could be a comma, it could be a space, a tab, and so on. And then you can also set a name for the newly merged column. I'm just going to call this product name. So the text in each of these columns will now be combined and then separated by a comma in a new column called product name. So let's just go ahead and see this in effect. And focusing on row number 1, you can see that we have MacBook Pro followed by a comma, followed by what used to be the type name, that is Ultrabook. We can just scroll along further and then confirm that this has been applied to each of the rows. And then if you'd like to edit this particular merging, we just click on the gear symbol which now appears. And then instead of a comma, let's just say we would like the separator to be a space instead. You will notice that a custom separator is also a possible option. Alright then, let's see that this space separator also works. And sure enough, it does. So we have now seen how it is possible for us to combine the contents of 2 different columns using Power Query. And if you're satisfied with these changes, well, we can just head over to the Home menu and choose to close Power Query and apply these transformations. And with this complete, well, we have now covered different ways to load data into Power BI and also a variety of different transformations which can be applied. You have now completed this purely hands-on course which got you familiar with the different types of data sources which Power BI can connect to and the types of transformations which can be applied on the data. You started off by downloading and installing Power BI Desktop. which is where data is loaded and transformed, and then used to build visualizations and reports. As a data analyst, it is likely that you will spend most of your time working with Power BI Desktop. You then load data from a variety of sources, from flat files such as CSV to structured data like XML and JSON, and also a relational database such as SQL Server. While doing so, you got introduced to the use of Power Query within Power BI, how this can be used to apply transformations, and also how some modifications, such as promoting the first rows in source files to table headers, are done automatically. You then covered some of the basics of transformations, which are crucial to build meaningful, responsive, and informative visualizations from data, such as trimming out unnecessary data, setting the right data type for columns, and merging columns containing related information. Having completed this course, you are well on your way to becoming a data analysis expert with Power BI. You now recognize what data preparation skills you will be tested on in the DA-100 certification and have laid the foundation to move on to more advanced topics related to the exam. Coming up next in this learning path is a course which focuses on some of the transformation steps which can be applied just prior to building visualizations in Power BI, including joining related tables and aggregating data. So far in this learning path, we have loaded a number of different data sets into our Power BI desktop. From the menu on the right, you can see that there are a total of 6 tables which we have created. However, each of these are entirely independent of the other. Now, however, we will focus on loading tables which are related to one another and then work our way towards merging them into a single table. First, let's take a look at the contents of the first table which we will load into Power BI, and this is a CSV file which has been sourced from this location on kaggle.com. It has the next CSV file which we will load, which also happens to be related to this file. In this case, we will need to focus on and understand to some degree exactly what data is stored in these files. Order details in here contains information, as you would expect, of a number of different orders for various products on an e-commerce platform. The first row contains the headers, and then you will observe that there are a number of different orders identified by an order ID. However, the order ID is not unique in this particular table, and in fact, there is a separate row for each line item in a specific order. For example, rows 2 through 4 contain the details for order ID 25601, but each of these 3 lines points to a different product within that order. So, for example, the first of these points to furniture, as alluded to in the category column. The next one points to some articles of clothing, and then the third line item points to some electronic item purchased within this order. You'll also observe that for each of these line items, the total amount of the order as well as the profit made by the platform on this order is available, as the quantity of the items ordered, along with the category, subcategory, and the date. So, each of the fields is not quite as important as understanding that for each order, there are multiple rows present in this data set. And this is because we will be combining this later on with another table which also contains order information, but where there is just a single row for each order. Let's just scroll along and confirm that there are over 1000 rows present in this particular data set. And following that, well, let's now focus on pulling this into Power BI. So from Power BI Desktop, we can now head over to the Get Data option. And since it is the contents of a CSV file which we need to load, let's select text/CSV. And then we can navigate over on our file system over to the order details file, and then choose to open it up. And then, of course, we will be presented with the options to preview the data and then specify the delimiter. However, I'm happy with the default settings in order to load the file, so we'll just hit load. And soon enough, order details has been loaded into our Power BI desktop. We can confirm that the amount, profit, and quantity columns have been treated as numeric values since there is the option to summarize these columns. And then for a quick sanity check to make sure that the data has been pulled in, we head over to the data section, and sure enough, all of the order details are visible here. A total of 1045 rows, in fact. Okay, so one of these tables has now been created. It's now time for us to pull in the other related table into Power BI. So heading back over to the Reports tab first, I'll now switch over to Microsoft Excel where the other CSV file called List of Orders has been opened up, and this is where there is other order specific information, more precisely the customer associated with each order. Focusing on the first of these orders on row number 2, so the order ID in here is B25601, which is the order represented as 3 line items in the order details file. There is an order date field in this data file as well, and then there is customer specific information, starting with the customer name. In the case of the first order, the name is Bharat, and then we also have the state and the city where this customer is located. So this is in the city of Ahmedabad in the state of Gujarat, located in India. What is different about this data set as opposed to the order details is that there is just a single row for each order. If you're familiar with relational databases, you can think of as the order ID as the primary key of the table represented by this file. Our goal is to combine the order details and the list of orders so that we can view the order information along with the customer specific details within a single table in Power BI. Of course, there are plenty of steps for us to go through before that can be done. And the first of these, of course, is for us to quickly glance over this data set and ensure that it does in fact contain just a single line item for each order ID. And then switching over to Power BI, again, we choose Get Data and then select Text/CSV. So let's select List of Orders from the file system. When we open it up, in a few moments, the menu will pop up, allowing us to load the data into Power BI or apply our own transformations. I'll just stick with the default settings. And in a few moments, alongside order details, well, we also have list of orders. You will notice that the headers don't seem to be automatically detected, since in this case, we have column 1, column 2, and so on showing up as the column names. So clearly, there is some transformation which we will need to apply on our own. And then to check that the data has been loaded, we head over to the data view and then select list of orders. So it looks like all of the data is in here. However, we do need to specify the headers. To do that and to focus on other transformations, let's switch over to the Report tab and then under Queries, select the Transform Data option and then Transform Data once again. This of course pulls up the Power Query editor where we can head over first to the Order Details table. Here we can confirm that a lot of the transformations which we need have already been performed. So the top row in the CSV file has been promoted to a header, as we can see in applied steps. And then the type changes for the columns have also been done. So we can see, for example, that the amount column contains numbers, as do the profit and quantity columns, but order ID and category contain text. Heading over to the transform menu, we can quickly confirm the size of this data set by counting the rows. And there are a total of 1045 rows in here. Let's just undo this particular transformation. And now we switch our attention over to the list of orders table. And this is where some additional work needs to be done. So we can see here that a type change has been applied. However, given that row number 1 in this case contains what should be the headers, this is not quite exactly in line with what we need. So the next step is for us to promote row 1 as the header row. So we can just hit this button for that to occur. And now we do have valid headers in the list of orders table. Next, let's just head over to the transform menu and summarize the number of rows in this data set. So we have a total of 500 orders in here, as opposed to a little over 1000 rows in the order details table. So we can conclude that there are a little over 2 line items per order on average in the order details table. Alright then, let's just delete this transformation. And now, let's focus on the fact that the order date column present here is not really necessary, given that there is also an order date column in the order details table. If you have modeled relational databases before, you will know that having redundant information can lead to problems, especially when it is across different tables. So in this case, let's choose to select order date. I'm just going to right click and choose to remove this altogether. So we'll no longer have order date in the list of orders table, but we will have that column in order details. In the next video, we will focus our attention on profiling the contents of columns in a table in order to get an idea of the kind of values which are present in there and how they are distributed. In the previous video, we loaded the contents of 2 different CSV files into Power BI Desktop, and we are working our way towards combining those 2 files into a single table. Whether or not we are combining data, it often helps for us to perform a preliminary analysis of the data we're bringing into Power BI, which can help us identify the kind of transformations which we need to apply. Next, let's focus on some data analysis within Power Query itself, just for us to get an idea of what exactly the data is like. So we can head over to the View tab for that. And then from here, well, first of all, we can change the appearance of the text by setting it to be monospaced. But if you're not happy with it, well, you can just uncheck this box. But now, let's check exactly how data is distributed in each of the columns, and also get an idea of the number of empty values as well as any potential errors. And for this, we can just check the column quality option here. And once this is done, well, between the header and row number 1, you get a summary for the column quality. So in the case of the first column for order ID, we can see that 100% of the values are valid. So all of these adhere to the type associated with the column. There are no errors and there is no empty data. While these same characteristics also apply to the other columns in view, this does convey rather important information. And it is possible that questions related to column quality will show up in the data analysis certification exam. So if you were to hover over one of these column quality summaries, well, we get the same information, but some more specific details may be available if there are errors or empty values. Previously in the transforming data types video, we did cover the fact that when we try to apply a transformation to a column which is not valid for all of the rows, we will encounter errors. Furthermore, a lot of data sets which get loaded into Power BI may contain empty values which can throw off analysis performed on the data. And the column quality feature will point us towards empty values, and we can then decide exactly what tactic to adopt to address them. Next, let's take a look at the column distribution feature. This tells us how exactly data is distributed across the column in question, and you can see a quick summary of the distribution just below the data quality information. And hovering over this, well, we can see that there are a total of 416 distinct values for order ID and a total of 192 unique values. What exactly is the difference between distinct and unique? Well, a certain order ID which makes at least one appearance in this column will be marked as distinct. However, if there are multiple rows with that same order ID, it will not be considered unique. So when you take a look at row number 12, for example, with the order ID of B25604, there is just a single row containing this order ID. So this is a distinct value in this column, but it also happens to be unique. And then right above it, there is the order ID B25603. This is also a distinct value. However, given that there are multiple rows with that same order ID, this is not unique in this column. This is why you will find that the number of distinct values will always be greater than or equal to the number of unique ones. Moving on then to the amount column distribution. So there are a total of 506 distinct values and 307 unique ones. In the case of a numeric column such as amount, however, the count of distinct and unique values is not quite important. What is more interesting, of course, is the histogram which appears just above to show the distribution of amount values. So there are more amounts in the lower end of this range, as indicated by the taller bars towards the left. So this is an example of a slightly right-skewed distribution, where the median value is likely towards the left of the mean. Let's quickly take a look at the distribution for the other columns. For the category column, we can see that there are just a total of 3 distinct categories here and a total of 14 distinct subcategories. At this point, however, I'll draw your attention to the text at the bottom of the window, which tells us that this column profiling is only based on the top 1000 rows, so it does not consider the entire data set. Next, let's head over to the column profile feature. This gives us much more detailed information about each of the columns. So this gives us a count, and note that this is only based on the first 1000 rows, so unsurprisingly this is 1000 here. We can see the errors, the empty values, distinct and unique values, empty string values, along with the minimum and maximum values, which are of course more applicable to numeric fields, but for a text field, this can be done on alphanumeric order. And then there is the value distribution histogram along the right, and this is a vertical histogram. Let's move along then from each of these profiles, and I'm just going to undo the column profile first, and then uncheck the box for column distribution as well. At this point, let's just right-click on Order ID and pick the option to remove duplicates. When we do that, well, a number of different rows have been removed from this dataset, since the Order ID column was not one which contained just unique values. We can see, for instance, that row number 1 points to Order ID 25601, which previously had 3 rows represented, but now there is just a single row for this particular order. More precisely, it is the first of the 3 rows which previously existed, which has now been retained, while the other 2 have been dropped. Such an operation can be useful if you really require just one record of a particular type, or for a particular order in this case, in order to perform your analysis. Now, to confirm that all the duplicates have been dropped, let's take a look at the column distribution once again. And for Order ID, we can confirm that the number of distinct values matches the number of unique ones at 433. So clearly there are no duplicates now. Let's enable column profile, and we now have a rather different profile given the removal of duplicates. Now there are a total of 433 orders represented here. But with this in mind, let's now disable the column profile and head over instead to the list of orders table. Here, with column distribution and column quality metrics enabled, we can see that there are a total of 500 distinct as well as unique orders. So this can confirm to us that the order ID does in fact effectively serve as a primary key. So in list of orders, there are no duplicates to remove, at least from the order ID column. We can confirm when we enable column profile, and the length of each of these bars is exactly the same, pointing to the fact that there are equal number of occurrences of each value. Turning off column profile and then heading back over to order details, well, removing the duplicates in here does not really serve a purpose, given that the order details which were removed do in fact convey meaningful information. So let's just undo the step where we remove the duplicates, and we're back to 416 distinct and 192 unique values, at least in the first 1000 rows of this dataset. And with that done, well, we are almost ready to merge the order details and list of orders tables. So the goal here is to include all the details available in list of orders, such as the customer name, state, and city, alongside the order details, even if the information is duplicated within the same table. We will discuss some of the benefits and drawbacks of this approach in the next video, where we carry out the merge. Having loaded and then applied some transformations and profiled the order details and list of orders tables, in this video, we will explore the steps involved in merging the contents of these two tables into a single unit. First, however, we will explore some other transformations. For that, we head over to the Home menu, and then from there, let's see how exactly we can reduce the number of rows in the dataset. There will be occasions where you just need to trim down the entire dataset and just load in a few specific rows. For instance, if there is a dataset which contains one row per day and it contains the data for a number of different years, well, you could consider extracting just the first 365 rows so that you have exactly 1 year's worth of data, especially if the data from 1 year does not vary much from that of other years. For that, you could use the reduce rows option here, and you can either choose to keep specific rows in the dataset or remove specific rows. Let's choose the first of these options, and from the menu which pops up, we can choose to keep the first 200 of the rows in the list of orders. And once this is done, well, we are down from a total of 500 orders to 200. To confirm this is the case, let's head over to Transform and select the Count Rows option. And yes, there are just 200 rows in here. So this is an option you can select if you feel that the first 200 rows in the list of orders is representative of the entire dataset, and whatever analysis needs to be done can be done sufficiently with these 200 orders. So we undo the count rows transformation, and then heading over to the order details, where we will cut down the size of this table as well. In order to demonstrate the merging of tables, we don't really need every single row. So heading over to reduce rows and choosing the keep rows option, and specifically to keep the top rows, again we'll set a value of 200 in here. And then to confirm that we now have just 200 rows in this table, let's head over to Transform and Count Rows once again, where we can see that the order details has also been compressed to 200 rows. Undoing this last change, well, we are now ready to perform a merge. This can be accomplished by heading over to the Combine menu, and then under Merge Queries, pick the Merge Queries option. This will bring up a form where we can specify exactly what tables need to be merged and how. So you'll observe that by default, Order Details has appeared as the first of the tables, and then we can select the second one. And when it comes to merging tables, well, this is very similar to a join operation which we perform in relational databases, which is why there is a join kind property which we can set here. So the default option in this case is a left outer join, and the left table is the one which appears on top. So it is the order details as things are. You'll observe that there is also an option to use fuzzy matching in order to perform the join rather than an exact match, which is the default. Alright, so we have now specified that it is the order details which is the first table, or more precisely the left table in the join. As for the table on the right, we can select from this menu where all of the tables which we have created in this Power BI report are available. Of course, it is just the list of orders which we can merge with order details. So let's just make that selection, and we have now decided the two tables which need to be merged. We have order details on the left and list of orders on the right. We have also set the join kind to left outer for now, which means that every order present in order details will have an entry in the combined table, even if there is no corresponding match in the right side table, that is list of orders. Furthermore, the rows in list of orders which do not have a match in the order details table will be removed from the merge table. However, we do need to specify the column or columns which will be used for this join operation, and of course, to match order details with one from the list of orders, well, this has to be done on the order ID column. So we make that selection first in order details and then in list of orders. Expanding the join kind menu, we can see that there are a whole host of joins which can be done, with inner join and left outer join usually being the most common options. Expanding the fuzzy matching options, you'll see how exactly this can be configured. There is a similarity threshold which can be set. We can make sure that the joins are case insensitive by ignoring case, and a handful of other options as well. However, let's just minimize this because we will not be performing a fuzzy match. Furthermore, the message at the bottom conveys that each of the 200 rows in the left table or the first table has a corresponding match in the list of orders, which means that the left outer join which we are about to perform will produce the same results as an inner join. Alright then, let's just go ahead and hit OK. And in a few moments, you'll observe that there is now a list of orders column at the right of the order details table. The contents of this particular column is a collection of tables. So there is some additional transformation we will need to apply in order to view the contents of the matched rows in list of orders. First, let's just click on one of these table elements. So this should point us to the specific row or specific rows in the list of orders table which match this particular row in order details. The reason there is a table which corresponds to this row is because there could potentially be multiple matches in the list of orders. However, by clicking on it, we know that there is just a single row which it matches to. This is because in list of orders, the order ID is unique. Now in the merge table, you could say that it is a little awkward having a single row from order details match a table in list of orders. However, what we really want is to be able to view the customer name, state, and city alongside the order details in the merge table. For that to happen, well, first of all, let's just cancel this step so that we exit this view. And then we will need to expand the list of orders table for each row. When looking at the list of orders header, we can see that this expansion is possible. So let's just click on it. And then from the options available, we can choose exactly which of the columns we would like to include in the expansion. I'm just going to eliminate the order ID since this will become a redundant column and stick with the customer name, city, and state. We'll also disable the option to use the original column name as prefix. But before we perform this expansion, I'll draw your attention to the fact that there is also an option to aggregate the data in this table. In our example, this is not really a valid option given that there is just a single row which each order detail matches to. However, in the case where a merge generates multiple matches in the right side table, we will need to perform an aggregation so that all of the matching rows are combined into a single aggregate row. Alright then, let's proceed with our own example where there is just a single match and choose OK. And then, well, we now have 3 additional columns in order details. So we can see the customer name, state, and city for each of the line items in order details here. And of course, given that there are multiple occurrences of many orders, there are multiple occurrences of the same customer details. For example, the name Bharat appears for the first 3 orders. And in fact, to get an idea of how many orders have been placed by each customer, let's just head over to the view pane and select column profile. And now, rather than order ID, we can actually see the names of the customers who have placed the orders. So the customer with the name of Farah is at the top of the list, conveying that she has ordered the most number of items. And then there is Anurag. Scrolling along, at the bottom are presumably the customers who have just ordered a single item. Let's scroll back to the top and hovering over the bar for Farah, we can see that there are a total of 8 occurrences of this name in this particular dataset, pointing to a total of 4% of the 200 rows. Furthermore, the column statistics point to the 84 distinct and 40 unique names within this column, and we can confirm that the min and max operations perform an alphabetical order sort. Let's disable the column profile and focus on one last transformation in this merge table. So, we will now move the customer name column over to the beginning of this dataset. So for that, we can right click, head over to the move menu, and then choose to move to the beginning. And sure enough, customer name appears to the left of order ID, making it easier for us to map the customers with the orders. So with these transformations now applied, we have all of this combined data in a single table. So what are the benefits of this kind of merge? Well, in order to get all of the order specific information as well as the customer specific details, we just need to look up a single table. This will be especially useful in visualizations where, for example, we may need to view the name of the customer along with the total value of the orders they have placed, in which case we will need access to the customer name and amount fields. With this merge table, we only need to perform a lookup in one table. However, without this merge, two tables will need to be combined on the fly in order to view that data. However, a drawback of such merged queries is the fact that there is duplicate information within the table. For instance, there are multiple occurrences of the name Jahan in the name column, and this is not the most space efficient way to store data. Alright then, now that we are done with all of the transformations, let's just close everything and apply the changes. And with that done, well, in the order details table, we now have access not only to the original field from order details, but also the customer name, state, and city. And as always, for a sanity check, let's head over to the data view, pull up order details, which now has the list of orders information merged into it. And sure enough, we can see those columns at the very end. We will now continue looking at loading data into Power BI Desktop, but we will now look at loading multiple files at once, all of which are located in the same directory and share the same schema. That is, they have the same set of columns. Power BI allows us to load such files in a single go and then combine them into a single table. To see how that is done, make sure Power BI Desktop is up and running. And before we load any of the files, let me just bring up the directory where they are located. So you can see that this is one called Sales by City, which I have on my file system. And there are three different files in here. These are all CSV files containing sales data for supermarkets in the country of Myanmar. More precisely, across three of the prominent cities in the country, Mandalay, Naypyidaw, and Yangon. These files are available as part of the course material and can also be downloaded from this URL on kaggle.com. As always, before we load the data into Power BI, let's open up the files to get a quick preview. So I'll just pop up Mandalay City Sales first, and we can see exactly what the CSV file contains. There are a total of 17 columns in here. A lot of these are text values such as the city and the customer type, and then there are numeric values such as the unit price and total. There is also a date column. Each line in this file represents the sale of a specific type of item to a specific customer. And then we can just scroll along and confirm that there are a little over 300 line items, that is 300 rows, in the Mandalay sales dataset. Moving along then, let's just close out of this file and open up the second CSV file in this folder. So Naypyidaw sales, well, this also has 17 columns, and you'll observe that this has the same set of 17 columns as the Mandalay sales dataset. This means that the two datasets can be combined into a single table containing the same 17 columns, and the rows of one dataset will simply be added below the rows of the other. That is, a simple append operation is possible between these two datasets we have come across. And in fact, even the third dataset in our folder can be added to create a single sales table containing the sales from three different cities. So before we move over to the Yangon sales data as well, let's quickly scroll along and confirm that the Naypyidaw sales dataset also contains a little over 300 rows. And then when we close out, let's pull up the last of these three CSV files. So yes, this also contains a total of 17 columns containing information about the sales from Yangon, which means that this can also be combined with the other two files to create a single sales table. Now, if you are familiar with union operations in relational databases, you will know that it can only be performed when the sets of data being combined contain the exact same schema, when they have the same set of columns in the exact same order and contain the same types of data. And this is also required in order for us to append data sets together to form a single table in Power BI. So let's just quickly scroll along the Yangon sales data. And we now know that this also contains a little over 300 rows. So all in all, we will have close to 1000 rows of data in the combined dataset. So to create that, let's head over back to Power BI and then choose to get data. The option for the data source which we're looking for is to pull in data from a single folder, for which we need to head over to More, and then there is the folder option. Once that is selected and we choose to connect, we will need to navigate over in the file system to the directory containing the 3 CSV files which we just explored. Now we can use the browse option in order to locate the folder, but I'll just fast forward to the point where the directory has already been selected and then hit the OK button. Well, at this point, the 3 different files in the directory have been picked up by Power BI, and we get a quick preview of the files themselves. So we have the second column pointing to the names of each of the files, and then the extensions have been marked as CSV. So we have 3 different CSV files containing the same schema located in a single folder, which we would like to combine into one table. This is a situation you may have come across previously in your professional life, where data coming in from multiple sources is copied over to a single folder, and for analysis or for any other purpose, you would like to merge them into a single unit. While doing so, it does help to get a quick preview where you can get information such as the dates at which the file was created and modified, and then finally towards the right, we have the exact location on the file system where the file is located. So if all of this looks good, well, we could choose to combine the files using the default settings, or to manipulate the data using Power Query Editor and define some of the transformations on our own. Well, we can choose the Transform Data option. When we do that, well, you'll observe that Sales by City appears as a separate data source along the left. This is, of course, the name of the folder where I had placed the files. And now you can see that this only contains a total of 3 rows of data, the same information which we saw in the preview. I'll draw your attention now to the content column on the left, where each the values are pointed to as binaries. You will also observe that this binary text is not regular text and is something we can click on to view the entire CSV data. We will get to that in just a little bit. First, however, I'll get to the View tab, and at least for this folder preview, we'll choose to disable the column distribution view and also turn off column quality. Once that is done, well, we have a more compressed view to work with. And before we combine the files into a single unit, well, for a quick preview of the individual files within Power BI, let's click on one of these binary texts. In the case of the Mandalay dataset, it is the contents of that entire CSV file which appears now as a table. In the Applied Steps menu on the right, you will observe that a number of transformations have already been applied, treating this as a regular CSV file. And this is one which is simply embedded within Sales by City. You'll observe that the unit price is treated as a decimal number, quantity as a whole number, and scrolling along, you can confirm the types of the other columns as well, which have all been automatically detected by Power BI. Once we have previewed this entire dataset, we can just click on Source to go back to the view containing just the file names, and for a sanity check, we will view the binary contents of the next file, and sure enough, this contains the data for Naipitao sales. The types have been automatically detected here as well, and significantly, they match what we saw in Mandalay sales. Heading back to the source view, and let's just assume that the Yangon city sales have the same schema and have been loaded just as the other 2 CSV files have, in which case we are ready to combine these 3 files into a single unit. To do that, we can just head over to the content column, and you'll notice that there is this little combine button which appears. Let's just click on it, and this pops up a combine files dialog where we get a preview for each of the files. So this is familiar to us based on the files we have already loaded into Power BI Desktop. So once we are taking a quick look, from this drop-down menu, we can navigate from this preview of the first file and then select each of the files individually. So Mandalay City Sales, of course, is the first file itself. So selecting that will produce the same preview. Next, when we take a look at the sales from the city of Naipitao, we confirm that this is also in line with what we expect. So things do look fine in here. So now, in order to finally perform the combine, let's head over to the first file view, and since everything looks okay in here, we just hit OK. In a few moments, the files will be combined into a single table, and the name sales by city will be retained, and we now have the combined file. So let's just scroll along and confirm that each of the 17 columns in the original CSV file are still here. And then once we move over back to the left, you will notice that there is a new 18th column. This is called source.name and points to the name of the file from which the data was sourced. More precisely, the name of the file where the specific row came from. And if we scroll further along, we can confirm that the rows from the Naipitau city sales as well as Yangon sales are present here. While this can be useful information, let's just say for our own analysis, we don't really care what file each of the rows came from, since we can already gather from the city column the name of the city where the sale was recorded, in which case we can just proceed to remove the source.name column. And with that done, well, we now have our combined data with all of the columns which we need. Before we save down our transformations, let's just sort this data set by invoice ID. So we can click on this little menu item here, and then from the available options, choose to sort in ascending order. And then once the ascending order sort is performed, I'll just quickly rename this table to sales by city, where the words are separated by spaces. And then to have these changes applied, let's just close and apply. And sure enough, in a few moments, sales by city has been loaded into Power BI Desktop with all of the changes defined in Power Query. Once we expand this, we can confirm that all of the numeric columns can be aggregated, and each of the other columns are present here as well. And of course, for our last sanity check, let's just head over to the data view, and then pulling up sales by city, we can confirm that this data set does contain all of the data from the 3 separate CSV files. And right at the bottom, you can see that there are a total of 1000 rows in here. So far in this learning path, we have covered a handful of transformations which can be applied to data, which is pulled into Power BI from a variety of data sources. Continuing on with transformations, we will now explore how it is possible for us to aggregate some of the data which has been pulled in. Since aggregations also represent a type of transformation, we can head over to the Transform Data menu and then choose to transform data. This will pull up the Power Query editor. Now, out of all of the different tables which we have in our Power BI desktop, the one we will perform aggregations on now is the laptop details table. So let's select that first and then consider exactly what type of aggregations can be performed and why we might perform them. So this particular table has over 1000 rows of data. The first column represents the company which has manufactured the laptop, and then we have various other columns including the size of the laptop in inches, and then we also have the price of the laptop in euros. While all of this is useful information, what we might really wish to gather from this data set may be something which is at a higher level. So if you think of this particular table as representing an inventory of laptops, maybe what we really wish to know is how many laptops are available from each company. In such a case, it really doesn't matter what the size or price of each laptop is or how much memory it has. All we really want is the name of the company alongside the number of laptops available from that company. And this is where aggregations come into picture. If you have worked with relational databases before, well, you will know that this can be performed with a group by operation. And in fact, this also applies when working with Power BI. So if we head over to the group by button available in the home menu, well, a dialog pops up, and this is where we can define how exactly we want to group the data in our table. So you'll observe that by default, the selected column from our table, namely company, has been selected as the grouping column. This means that our aggregated table will contain a single line item for each distinct value of company, and then alongside that, we can have one or more aggregated values. So what exactly is the aggregation being performed here? Well, one has been set by default, and in fact, this is what we will use. So the operation in question here is to count rows. This means that for each distinct company name in our table, all of the rows containing that company name will be collapsed into a single value representing the count of the rows. So if we have 27 rows in our table where the company name is Lenovo, there will be a single row in our aggregated table with the name Lenovo, and alongside it, a column with the value of 27. And a similar operation will be performed for each of the different companies in this table. So if this is all abstract, well, things should become a little clearer when we proceed with the aggregation. You can see that by default, the basic settings for aggregations are available. However, when we switch over to advanced, well, there are a few additional options. For example, we can aggregate based not just on the contents of a single column, but on many different columns in the table. And we can have more than just a single aggregated value as well. For now, however, let's keep things simple and switch back to the basic view. So just to summarize, we will be aggregating values based on the company column, and the aggregation operation is to count the number of rows corresponding to each company. And this new column will be called count. Just to give you an idea of how these aggregations can be performed, you can see that we can in fact aggregate by any of the columns available in our dataset. Keep in mind though that aggregation is really just meaningful when we perform it based on the contents of a categorical column rather than a numeric one. So company is a good fit in this case. We can define the name for the new column containing the aggregated value, and then the operation to be performed for the aggregation. Well, there are a handful of other options here. Since this operation works on a collection of rows, well, there are different operations which are possible. Perhaps the simplest being the count of the number of rows, and then there are a number of other operations which can be performed on individual columns of the data table. For example, we can sum up the values in a specific column, compute the average in a column, and so on. Now for the count rows operation, there is no column selection possible since this does not operate on individual columns. But if you were to perform, say, a count or mean calculation, this will apply to specific columns, and we could select that from this drop-down menu. For our count rows aggregation, however, well, let's just keep the settings as they are and then hit OK. And soon enough, we have our aggregated table. So there are a total of 19 rows in here, which represents the fact that there are a total of 19 distinct values for company. And then let's focus on row number 3 representing Acer laptops. The value of 103 in the count column right next to it points to the fact that there were a total of 103 rows in the original table where the company name was Acer. So we had a total of 103 Acer laptops in the inventory. So a question you might pose is, why exactly would we perform such an aggregation? Well, consider the fact that the only useful piece of information for you from the laptop details table is how many laptops are available from each company. In such a case, it really doesn't make sense to hold all of the 1000 plus rows in the original dataset, especially since in import mode, they will all be held in memory. In such a case, it does help to compress the dataset to exactly what you really need. And this aggregated table containing just 2 columns and 19 rows represents the relevant data. At this point, I'll also draw your attention to the applied steps pane towards the right, where right at the bottom, our latest transformation of grouping together the rows has been recorded. Moving on to our next transformation, well, when we have performed an aggregation of this sort, it often helps to draw a user's attention to the counts with the highest values. Well, in such a case, we can choose to sort the data by the counts, and for that, we can just open up the menu next to the count column and then choose to sort in descending order. Well, in this case, the laptops with the highest representation in the dataset appear at the top. So Dell and Lenovo with nearly 300 laptops in the inventory appear at the top, followed closely by HP. Now, if you have worked with Power BI visualizations before, you will have an idea that it is possible for us to perform such grouping and even sorting in descending order using some of the visualizations themselves. However, a best practice is to leave the visualizations to merely present the data rather than perform any operations such as aggregations, and instead perform this kind of transformation earlier in the process. All in all, this will result in better performance for your visualizations. Let's move along then from a single aggregation to multiple aggregated values. And for that, let's just delete this latest transformation so that we're back to the original laptop details table. Now we will once again perform an aggregation based on the company column, but we will include not one, but two aggregated columns. For that, we can head over to group by once again. This time, however, let's choose the advanced grouping operation. So when it comes to the grouping column, while all of the others are available in here, we will retain the default selected value. And following that, let's move on to the columns representing the aggregated values. In the first column, let's compute the average price of the laptops from each company. So we start off by giving a representative name to the column. Let's call this average price. And for the operation, well, let's expand the menu and choose average. When we do this, well, we will need to define a column on which this aggregation will be performed. So for each company, what is the average we wish to calculate? Well, out of all of the columns, it is price underscore euros, which will give us the average price. Keep in mind that aggregation operations such as average and sum can really just be performed on numeric data. So we cannot choose to perform an average operation on, say, the operating system column. So once we have made the selection of this numeric column for the average calculation, well, we want our new aggregated table to contain two aggregated values. In addition to the average price, let's go ahead and add a second aggregation. And this is where we will add back the product counts for each company. So we will now give a representative name of prod count for the column, and the operation will remain as count rows. And of course, we cannot select a column for this particular operation. So we just proceed by hitting OK. And in a few seconds, we have our new aggregated laptop details table. So it contains three columns in all: the company name, which is of course the key, and then two aggregated values, the average price and product counts. So for example, for HP laptops, we can see that the average price, at least for the laptops in our dataset, is about 1067 euros over the 274 laptops on offer. Laptops from the company Razer do seem to be rather pricey with an average price tag of nearly 3350 euros, though there are a total of just 7 laptops offered by this company. And then the laptops offered by the company Vero are rather economical at an average of just over 200 euros. Now with this much more compressed data set, any visualizations which are built out of this will perform much better than had they operated on the entire data set. This is because the visualizations now can just focus on presenting this data rather than having to perform aggregations on their own. In fact, if you have the option to generate such aggregated results within the source files themselves, that would be an even better option, since less data will need to be imported into Power BI and one less transformation will need to be carried out. This video serves as a quick introduction to the mQuery language used in Power Query. Before we get to that, however, we will apply a handful of other transformations to the sales by city table, where we have the details of various retail sales recorded in the country of Myanmar. While we have covered some of the analysis which can be performed on individual columns, we will now continue in that mold and take a look at some of the statistics which can be computed. For example, the total column in this particular table gives us the total value of the sale recorded in each row. And of course, if you'd like to get the total sales recorded across all stores and all cities, we will need to sum up the values in this table. Well, to get that sum value, we can head over to the transform menu and then over to the statistics option, where different statistics can be computed from the contents of this column. So we can compute the median, average, minimum, or maximum values from this column. But to get the gross revenues across all of the stores, well, we will need to perform a sum operation. This will return to us a single value pointing to revenues of just about 323,000 currency units. So why exactly might we perform such a sum operation? Well, in some instances, perhaps this is all the information you really need from a data set. You don't care what the individual sales transactions are and which city they originated in. All you really want is how much revenue was generated by all of the sales together. In which case, we can just compute this sum operation and then present this value in a visualization later on. Alternatively, we might compute a sum just to get an idea of the scale of values we're working with in our dataset. One more detail you will notice here is that the sum of total sale values goes into several decimal places. If we don't really require such precision, we can consider rounding some of the values this statistic is computed out of, and we will get to that in just a moment. Alright then, let's just say we have performed our analysis. We can just delete this latest transformation and explore some additional transformations in the sales by city dataset. So, sticking with the transform menu, let's scroll along to the column which conveys the unit price of each item. Now these go into two decimal places, and if we assume that we don't really require this degree of precision when it comes to building our visualizations out of this data, well, there are a few options available. Let's quickly summarize some of the transformations which can be applied to this numeric data. Now, if you'd like to explore some of the standard math operations which can be done, well, the standard menu here will allow us to perform addition, division, modulus operations, and so on the contents of this column. The scientific menu allows us to perform exponential or logarithmic operations. Some of these transformations may be required depending on what exactly you need to present to the end users of your visualization. So for example, if you want to plot a line chart which uses a logarithmic scale, well, you can just generate the log values right here using Power Query. You'll observe that from this menu, other complex math operations can also be performed on the data. There are also trigonometric operations which can be done. And what we will work on now is to round this data. Here we can choose to round up to the nearest integer or round down to an integer. Alternatively, there is another round option where we can define the degree of precision required for the round operation. For now, however, let's just stick with round up, and we are down to just integer values for the unit price. Alright then, once we confirm this rounding operation, let's just cancel this recently performed step. And in this menu, you'll observe that there have been a number of transformations which are recorded, and all of these have been through our actions in the Power Query user interface. Now, however, let's just switch over to the Amazon Books table, where a total of 4 transformations have been recorded. One is to connect to the data source, there is the navigation step, and then the promoted header step in order to cast the first row in the original dataset to headers. A change type step was also performed in order to set the types for the different columns in the dataset. Now, each of these steps have been triggered by our actions in the Power Query UI, and for most use cases, this may be more than good enough. However, there may be some instances where you may apply a number of transformations to a particular data source, and then over time, the types of transformations which you apply may be subject to change, in which case, you will want to keep track of the changes recorded for the transformations. Furthermore, if you are a coder, you may just be more comfortable defining the transformations in a programmatic manner rather than view it in the UI in this form. Well, for that, we can make use of the M formula or M query language for Power Query. And this is what we will now explore. So when you take a look at the year column, we can see that the year of publication for the different books in this dataset cover a wide number of years. Now, we may want to sort this information based on the year of publication. So for that, well, let's just select this column first head over to the home menu. And while we have seen how we can sort data using the menu available from the column header, well, in this case, to perform an ascending order sort, we can also make use of this sort ascending button here. The button immediately below allows us to perform a descending order sort. However, once the ascending sort has been performed, well, we can confirm that the earliest books in this table are from 2009. Then we have books from 2010 and so on. And significantly, there is now a sorted row step which is available in applied steps. So now let's take a look at how exactly Power Query implements these transformations using the M formula language. To view all of these steps in the M language form, we just head over to the advanced editor for Power Query, and this brings up each of the steps which have been carried out. All of this, of course, is in the M formula language, and to get the full documentation for this language, you can visit this page on docs.microsoft.com. So let's preview exactly how the steps have been recorded. So at the top, there is a let expression. This includes the let keyword followed by a block of code which encapsulates the different transformations which we want to apply on the data. Then there is the in keyword, which references a data source. Now, the vast array of commands in the M language is not quite important for the DA-100 certification. However, it is important to know that this language exists and very detailed configurations can be done here. So I won't spend too much time delving on the syntax and instead give you a high-level overview of the steps. So right after the let keyword, we have the source definition, which points to the Excel workbook from which the data has been loaded. The next is the navigation step, where a specific sheet in the Excel workbook is pointed to. Then to transform the first line in the Excel worksheet to headers, well, there is a table.promote header step which is carried out. So there is a table object in the M language, and then there is a promote headers operation which can be invoked. This is a function, and if you have used, say, Visual Basic for applications before, you will be familiar with the syntax, where Pascal case is applied for functions. You will observe that what is returned is referenced by a hash or pound symbol, followed by promoted headers in quotes. This in fact represents a record, which you can think of as a collection of different fields. So the name of this record is promoted headers. The next step represents the changing of the data type for each of the columns. So the function here is table.transform column types, and you can see that this has been applied to each of the columns in the dataset. And then finally, we have a sorted row step. This is where the function table.sort is applied to our table. The arguments which are supplied here include the change type record, and then the second argument points to the column which needs to be sorted and the type of sorting which needs to be done. So it is the year column which is being sorted, and the type of sorting is order.ascending. In order to change this to a descending order sort, we can simply edit this order and change it to order.descending. And of course, while this step can easily be performed using the UI for Power Query, if you happen to use the M language, all of these steps can be recorded in a version control system, and you can keep track of the changes applied to the transformations over time. This concludes the transformation, so we can close out the let block, and then the in keyword is followed by the final set of records. So now that we're done editing the transformations using the M formula language, let's just hit done. And you can see now that in the year column, a descending order sort has been applied. The latest books available in this dataset are from 2020, which appear right at the top. And scrolling along, we see books from 2019 and 2018 and so on. So now that you have an idea of what the M language is capable of, let's just use it to perform one more transformation. So clicking on the name column, let's see how we can rename this using the M language. So I'm just going to first demonstrate how this is done with the UI. So we right click and then choose rename, and let's just call this column name of book instead of book name. Sure enough, in the applied steps column, we can see renamed columns now shows up. Pulling up the advanced editor then, In the bottom of the let block, we can confirm the invocation of table.rename columns. So now that we know what exactly needs to be done in the M language in order to perform a rename, well, let's just edit this step by renaming the column which was originally named to book name. And then when we hit the done button, sure enough, the column name change has been successfully applied. Previously in this learning path, we have covered how unnecessary columns can be removed from a dataset when defining tables in Power BI. Now we will see how rows which are not required can be filtered out. For this, we will be working with the laptop details dataset. Having worked with it previously, we know that there are over 1,000 rows of data representing 1,000 different laptop models. Now let's just say for our own analysis, we don't really need all of this information. There are just specific laptops which we would like to analyze based on one or more conditions. For example, there is the company column for each laptop, and we only need to analyze the data of laptops from specific companies rather than all of them. In other words, we would like to restrict the size of the data we're working with based on a condition applied on the company column. So now let's see how we can apply such a filter on this column. Well, there are a number of different ways this can be done, but let's start with something which is the most intuitive. And for this, we just expand the menu next to the company column header. And then, well, there are a few options here. We have already covered some of the sorting options before, but you will observe that there are a number of different selections which can be made based on the value in this column. So each of the distinct values which are present for the company name are present in this list. And by default, all of them are selected. However, if you would like to restrict our analysis to specific companies, well, we can just uncheck the select all box here and then check the ones corresponding to the companies we are interested in analyzing. For now, let's just say it is the Dell laptop we want to analyze. We can just check that and then hit OK. So with this filter, well, our dataset is now down to 297 rows, containing only the Dell laptops. To consider why we might need to apply such a filter, well, realistically, there may be a lot of sources which generate the data which you load into Power BI, and you may not have control over the nature of the data which they generate or the format. In such a case, there will be a lot of transformations which you will need to apply from within Power BI, and this may include the filtering out of unnecessary data. So, for example, if you wish to analyze Dell laptops, your only source of information may in fact generate information for multiple brands of laptops, in which case, the best option may be to pull in all of the information in the dataset into Power BI and then apply a filter for Dell laptops as we have done in here. Of course, the filter which is required may be a little different. Just pulling it up again. Well, given that these are checkboxes, we can in fact make multiple selections. And if there are too many distinct values, rather than scroll through each of them, you can just make use of the search box in here. So in order to search for the brand Vero, I just type in VE, and sure enough, that brand shows up. And then when we hit OK, the 4 laptops which are manufactured by the company Vero now show up here. So this is how rows from a dataset can be filtered through or filtered out based on the contents of a specific column. In this most recent example, however, we were dealing with the company column which only had a few discrete values. Realistically, you may need to apply the filter based on not one column, but a combination of different columns in the dataset, and some of these may not be categorical. That is, the values in the columns may not be discrete, but in fact can be continuous. In such a case, a more sophisticated filter will need to be applied. So to demonstrate that, let's just delete this latest filtering step. Now that we're back to a full dataset, we will once again work on the company column by bringing up the menu. And then given that this column contains text, there are a variety of text filters which can be applied. So this menu gives us a handful of different options. If you have performed any kind of string search before, well, all of these should be familiar to you. we can check whether a string happens to be equal to a particular value or is not equal to a specified value. We can filter rows based on whether the string in the company column begins with or ends with a specific substring, and so on. To get an idea of how this filter can be applied, we can just start off with an equals operation, and this brings up a dialog for filter rows. This is where we can define, using a number of different operations, how exactly we would like to filter the contents of our table. So by default, a basic filter can be applied based on two different conditions, and we can apply either the AND or OR operator to them. We will explore this in more detail just a little later. For now though, when we take a look at the advanced settings, well, this is much the same, but it allows us to specify more than just two filtering conditions. Let's head back over to the basic view, and for the first condition, we can see that automatically this will apply to the company column, since the message says keep rows where company, and then we apply the operator. So the operators here include equals, not equals, ends with, and so on. And this is followed by a value to be compared. So if we wanted to create a filter which ensures that only those rows are kept where the company name equals Apple, well, this is what we can set. The column being operated on is company, the operator is equals, and the value being compared to is Apple. So when we hit OK, we should only have the Apple laptops on display. And sure enough, it is the 21 Apple laptops which are the ones visible. We can scroll along and confirm that all of the Apple laptop details are available here. And once we have this confirmation, well, we now know that a filter can be applied using a variety of different operators for a column. Let's just undo the latest filter and experiment with the filters a little more. So now we will go beyond just the equals operator by pulling up the menu, heading back over to text filters, and then choosing the option of begins with. So we will restrict our dataset to only those laptops where the name of the company which manufactures it begins with a specific substring. So once the dialog pops up, well, the column in question is company, the operator which we wish to apply is begins with, and to filter our table so that we only have laptops where the company name begins with A, well, we set A as the argument here. So in our data set, we have Apple, Acer, and Asus among others. So when we hit OK, it's just those three brands which are now represented in our filtered data set. So we have now successfully applied the equals operator as well as begins with for a string column in our data set. So now, in order to proceed to the next filter operation, I'll just cancel out this latest step, and then pulling up the menu for the company column once again, we'll head over to text filters and we'll choose equals once again. However, right after that, we'll switch from the basic view to the advanced filters. And this is because we are now going to focus on defining filters based on multiple conditions and not just on the contents of a single column. So while in the basic view, we had to perform a filtering operation on the company column since that is the one which was selected. In this case, we have a little more of a free rein. The first condition does not need to be in the company column, and we can in fact switch to a different one in our data table. However, let's stick with company. And in fact, for the operator as well, we will stick with equals because the first condition we set is for the company name to be equal to a specific value. When we expand the menu, all of the distinct values in the company column shows up, and we can make a selection from here. So I'll just select Apple, and then we can go on to specify the next condition. When two or more conditions are specified, we will need to set what type of conjunction operator we wish to apply, and the options here are AND and OR. Sticking with the AND operator, well, for the next condition, we will work with the inches column, which points to the size of the laptop. And if you would like to restrict our data set to Apple laptops which are greater than a specified size, well, the operator needs to change from equals to is greater than. Then we'll of course need to specify a value, and this is something we can just type in. So I'll just set a value of 15 in here. And all in all, the conditions which we have set here are that our dataset should be restricted to laptops manufactured by the company Apple, whose size is greater than 15 inches. Now when we hit OK, well, out of the total 21 Apple laptops, there are just 4 which fulfill our conditions. Scrolling along, we can see that all 4 of these have a size of 15.4 inches. And of course, all of the other details are also present here. Scrolling all the way to the right over to the price column, you will observe that all of these are upwards of 2000 euros. However, there are just 2 which are less than 2500 euros. Now, what if we wanted to restrict our dataset even further? So in addition to the 2 conditions we have already set, what if we only want to analyze those laptops which cost less than 2500 euros? Well, there is a third filter which we can apply, for which we can click on this gear icon next to the filtered row step in order to edit this step. And of course, this brings up the same advanced configurations for the filter, and we can choose to add in a new clause. This will also be combined by means of the AND operator. Since we wish to apply a new filter based on the price, for the column, let's change this from company over to price underscore euros. Since our filter is for laptops which cost less than 2500 euros, the operator needs to change over to is less than. And following that selection, we specify the value. So the laptops should cost less than 2500 euros. So just to summarize, the conditions here say that we want to filter our dataset to only Apple laptops which are greater than 15 inches in size and less than 2500 euros in price. And now that we have 2 rows in this dataset, we can confirm that the company name is indeed Apple. The number of inches are greater than 15 in both cases, and the price in both cases again is less than 2500 euros. And while we have successfully covered how filtering operations can be performed within Power BI using Power Query, I'll again mention that as far as possible, such filtering should be done outside of Power BI. If we can get access to datasets which have already filtered all of the rows for us, well, there is less data we need to load into the memory when we load data in import mode, and overall, the performance will also be optimized since there will be fewer transformations which need to be carried out. So far in this course, we have covered a number of different ways in which data can be loaded into Power BI and then prepared for analysis, where we performed a number of different transformations. And now it's time for us to get a glimpse into visualizing data, where we will generate a bar chart using one of the data sets which we have loaded into a table, specifically the video game sales dataset. So just a quick note, we are currently in the report view of Power BI desktop. On the right in the fields pane, we can access the different fields from the different tables which we have loaded. And then there are a collection of visualizations which we can create out of the contents of the tables. We can also apply filters to the visualizations. But now, let's just expand the video game sales table. And this of course contains a number of different fields. Just as a quick reminder, this contains sales information for a number of different video games. So for each video game, we have the genre of the game along with details such as the amount of sales recorded in different regions of the world. We have the sales in the European Union or EU, Japan, North America, and the rest of the world. Our goal is to generate a visualization which will allow us to analyze the aggregate sales across the different genres represented in this dataset. And to be precise, we will make use of a bar graph to visualize this data. Among the visualizations, well, you should see this little icon with 2 vertical bars, and this represents a vertical bar chart, and this is precisely what we need. If we just click on it, well, a little area pops up within the reports view. You can treat this region as a canvas where one or more visualizations can be added and then configured. As for this one, well, we can just drag it along the corners in order to expand this bar chart. And of course, as of now, there is no data which is mapped to it which is why it appears as a shadow of bars. As mentioned earlier, the goal for us is to visualize the aggregate sales of the video games over the different genres. So we would like one vertical bar per genre, and the height of each of these bars will represent the aggregate sale for that genre. And in this regard, I'll draw your attention to the configurations with regard to the visualization. So make sure that the bar graph area has been selected in the reports view. We then have an access section where we can drop one or more fields, and these are the different categories for which the bars will be generated. For our visualization, we would like the categories to be determined by the values in the genre column. So we can just either select that from the field section, or we could drag and drop it into the access section. So based on what we have so far, a different bar will be plotted for each distinct value in the genre column of the video game sales table. However, the heights of each of these bars are effectively zero, so they don't really appear in our visualization, and we need to specify the values from which the heights of the bars will be derived. Well, if we wish to view the global sales, that is, the sales across all of the regions in the world for each genre, we could either select that or drag and drop it into the value section. And there we have it, our first bar chart in Power BI. So you'll notice that there are a total of 11 bars, and each bar points to a distinct genre in the dataset. And from the reducing height of the bars, it is clear that these have been sorted in the descending values of the global sales. The labels associated with each bar are not quite visible in this view, but if you hover over the first bar, well, the details become clearer. So this bar represents the genre of shooter games, and the aggregate global sales is $257.56 million. So a question you might ask is, how exactly is this the aggregate of global sales? Well, I'll draw your attention to the fact that in the fields menu, global sales has a sigma sign next to it, and this represents the fact that by default, when global sales is used in a chart, a summarization will be performed based on the axis specified. In this visualization, the axis points to the genre field, which means that the values will be aggregated for each individual genre. When it comes to summarizing a particular field, well, there are in fact different aggregate operations which can be defined. For example, we could have it point to the average sales rather than the absolute sum, but the default aggregation is a sum. So the height of this bar represents 257 millions worth of sales. And then moving over to the next bar, well, this represents the genre of platform games, where the aggregate sales stand at just a shade under 251 million. Racing games had aggregate sales of about 147 million. And then right at the bottom, there are adventure games whose overall sales stood at a relatively meager 11 million. Now you have seen that if you hover over the individual bars in this chart, additional details can be made available. So this box which shows all of this information is referred to as a tooltip. It is often used to convey additional information about the details conveyed in a chart, and in fact this is something which can be configured to convey even more information. While we won't get into tooltip configurations in this demo, we can explore some of the other configurations which are possible for visualizations in Power BI. So for that, under the visualization section, we can switch over to the format pane. This is where we can configure a lot of details with regards to the aesthetics of the plot. This can include the colors of the bars, along with additional information which is visible. Now let's just say we would like to view the aggregate sales data associated with each genre, not by hovering over the individual bars, but by simply glancing at the chart itself. Well, this is something which can be accomplished by turning on data labels, which was switched off by default. You'll already notice that some numbers are now available right on top of each bar. However, in this view, the text is not quite visible. I'll just minimize this filters pane so that the graph becomes a little bigger. And while the text is a little bigger now, it may not quite be visible yet in the video. If you are following along with me and then repeating your steps in your own Power BI desktop, well, you should be able to view the text more clearly. But significantly, this is a setting which can be adjusted. That is, the size of the font for the data labels can be increased or even decreased. Now, as we hover over each of the bars, well, we still get all of the tooltip information, and all of this in fact represents the interactive nature of Power BI visualizations. Not only can we hover over them to get additional details, it is also possible for us to click on the charts in order to zoom in on specific categories. Alright then, we now have an idea of how a visualization can be generated by mapping it to fields in our datasets. And then we have also got a glimpse into the formatting available for the charts. Next, let's focus on visualizing additional details within the chart itself. Now that we have the global sales recorded, what if we also wanted to view the aggregate sales in a specific region? Let's just say we wanted to also visualize the sales recorded from Japan alongside the global sales. Well, for that, we can just head over to the Fields menu and then drag and drop the JP_sales field into the value section. And what we have here is a stacked bar chart. So from the legend in the top left, you can see that the light blue bars represent the global sales, while the dark blue ones represent the sales in Japan. And the dark blue bars are stacked on top of the light blue ones. Now this works if we are comparing two values which are independent of one another but related to one another, such as the sales in North America and the sales in Japan, for example. However, in this example, global sales does encompass the sales in Japan. So in effect, the total heights of each of the bars represent a double counting of the Japanese sales. So the stacked bar chart, which we have been working with so far, is not quite the best fit for what we're trying to visualize. However, using the same settings, it is possible for us to switch over to a different visualization. So if you want to switch over from a regular vertical bar chart to a clustered column chart, we can just click this, and we now have separate bars for global sales and Japanese sales. And this does give us some interesting details to analyze. For example, when it comes to shooter games, these are vastly popular all over the world given the very high global sales, but these also happen to be some of the least popular games in Japan, with just 4 million recorded in total sales. Overall in Japan though, it is role-playing games which seem the most popular, representing a significant chunk of the global sales. So this is how a clustered column chart can allow us to compare values across different categories, but also different values across the same categories. Now, if we just throw in the North America sales into the value section and then the sales in the European Union, well, we can now clearly see not only how sales are split across the different genres, but how the sales in each different region compares to the other. In nearly all of the genres, the orange bars representing the North America sales are the highest, pointing to the fact that this is the region which has recorded the most sales across the video games in our dataset. And even with a clustered column chart, well, the graph still remains interactive and we can access the tooltip when we hover over the details. Now focusing once again on the visualization settings, in the value section, there are 4 different aggregations which are being performed for the global sales and the sales in Japan, North America, and EU. But given that the global sales encompass the sales in the 3 different regions, what if we wanted to disregard the global sales and take it out of the chart? Well, we can just hit the cancel button next to this particular field in the value section. And we're down to 3 bars per genre. So we have now successfully built out our first visualizations in Power BI. So this was just to give you a glimpse of how the data which you have loaded into Power BI can be used for analysis using visualizations. And while visualizations will be covered in depth later on in this journey, In the path Visualize and Interpret Data in Power BI, when preparing data for analysis, it always helps to know what the end goal is. Now to wrap things up, let's just set a name for this page in the report. So we can click on the default page 1 and give a more relevant name of sales details. Having covered a lot of data preparation so far in this learning path, and also having implemented a basic visualization, it's now a good time for us to revisit a concept which we had touched upon previously, but did not explore in depth, specifically the direct query storage mode. From the Fields menu on the right, you'll observe that the video game's sales data is no longer loaded in my Power BI instance. This is because I have deleted it and will now load it again using DirectQuery, whereas previously it was loaded in import mode. Furthermore, you'll observe that in the sales details page of the report, I have also deleted the previous bar chart which we had generated. This is to start off with a clean slate and then rebuild the bar chart once we bring back the video game sales data using DirectQuery. You will recollect that the video game sales information was available in a database table in a SQL Server instance. I'll just pull up my SQL Server client, and you might recall how exactly we pulled in data from this database instance in the video connecting to a SQL Server instance in the previous course in this learning path. On the SQL Server, well, within the databases directory, I have a database called SalesDB. Now I recognize that you may not have your own SQL Server instance. However, DirectQuery can be used to pull data into Power BI from a variety of different sources. The full list of this is available at this page on docs.microsoft.com. Here you will see, for instance, that DirectQuery can be used to get data from a Postgres database, an Oracle database, and a handful of other databases as well. So, if you don't have access to a SQL Server instance, feel free to connect to any other kind of database which is compatible with DirectQuery, keeping in mind that the specific steps which I will now demonstrate will just be a little different from what you will need if you are working with a different database. Alright then, our goal now is to connect to this SalesDB database, and upon expanding this, and furthermore, upon expanding the tables, you'll observe that there are a total of 3 tables in here. The tables PS4 game sales and Xbox One game sales contain information specific to those consoles, and then there is the more generic video game sales, which is what we had been working with previously. Next, let's go ahead and preview the data in video game sales, and for that, I'm just going to right click on this particular SQL Server connection and choose to create a new query, and we will now run use SalesDB. So I'll just use autocomplete to fill this in. And this of course ensures that any subsequent queries will be run against the SalesDB database schema. As for the subsequent query itself, well, this is going to be a rather simple one. Select star from dbo.videogamesales, and then when we hit execute, well, we can see exactly what is present here. We have of course seen all of this before. In the name column is the name of the video game, and what we have been working with are the sales numbers across the different regions. Alright then, the goal is to get this data into Power BI using the DirectQuery storage model. Now, whether we use DirectQuery or import mode when loading data into Power BI, the types of data in the relational database will determine the types of those columns when they are operated on by Power Query. To view the types for each of these columns, I'll expand the menu corresponding to this table and then expand the columns menu. So this is where we can see not just each of the column names, but also their corresponding types. The rank column, for example, is an integer. The name and genre columns are both varchar, and then we have the different sales columns, which are all of type float. Keep all of this in mind, because when we load this data into our Power BI desktop, Power Query will try to map each of these columns to the corresponding Power BI types. For instance, each of the sales columns, which are floats here, can be mapped to decimal numbers within Power BI. Alright then, now that we have an idea of the schema of the database table we're working with, I'll give you a quick preview of how you can change the types if needed. You can just right-click on one of the columns and then choose Modify, and this will bring up a form where all of the different columns can be modified. So while I right-clicked on the rank column, all of the others can also be edited here. Alright then, now that we are familiar with the types of data we're working with, let's just exit out of this view, and then we'll also minimize the columns menu. And next, let's take a look at one value which we will update within the database, and then see whether the update can be picked up within Power BI. So I'll just replace this select query, which selects all of the data from video game sales, and then restrict it to just the adventure games by including a where clause for genre is equal to adventure. And what we can gather from the output is that there is just a single game in this genre. This is specifically Super Mario Land 2, and I'll draw your attention to the fact that the sales in Japan for this particular game was 2.69 million. Later on, we will build a visualization within Power BI which makes use of this JP sales number, and then we will see what happens if we were to modify this value within the database. Before we can get to that, however, we will need to make sure that we can connect to the database in the first place. We will need the server name in order to establish a connection to SQL Server, which can be obtained with this query, select @ server name. And then when you hit execute, well, whatever shows up in the results, you can just right-click and choose to copy. And once that is done, let's head back over to Power BI in order to connect to the SQL Server instance. This, of course, can be done by clicking on SQL Server in order to load the data from there. Then in the space for the server name, we can paste in the value copied from the SQL Server client. And while specifying the database name is optional, it is good practice to only import those schemas which we really need. So I'm just going to type in SalesDB here, and then there is the storage model, also known as the data connectivity mode. By default, this has been set to import, and I have mentioned a few times before that this means that the data which we will load will make its way to the memory on the Power BI host. This, of course, can boost performance since the required data can be accessed with a simple memory lookup rather than having to go into the database. However, this comes with the risk of the data potentially going stale, where an update may be made to the database and that update will not trickle through to the cache on the Power BI server. The alternative, of course, is to make use of the DirectQuery mode. This is where each time data is required, a query will be sent over to the underlying database, ensuring that the data is always fresh. However, this does come at a cost of performance, since the data is not available with a simple memory lookup, but requires connection to a database which may be on a remote host. So even network delays may enter the picture. In my case at least, the database is in fact on my local host, so it should not really matter too much. But let's see what happens when we choose DirectQuery as our storage mode. And then in the advanced options, well, as we have seen before, it is possible for us to make use of a SQL query to select precisely what we need from the underlying database. We won't really use that now, and instead, let's stick with the regular DirectQuery mode and then choose OK. Again, just like with import mode, we can select exactly which underlying table in the database schema we would like to load into Power BI. And while we can select all three present in SalesDB, I'm just going to stick with the video game sales data, which we have already worked with. We can just scroll along to confirm that it is the same data in fact, and then we can proceed to load the data into Power BI desktop. Since we are connecting in DirectQuery mode, we may be prompted about a potential security risk. If you do trust the location of your database server, you can just hit OK, and soon enough, the video game sales table has now been created within Power BI. When we expand this, we get additional pieces of information. First of all, the summation signs next to the different sales columns confirms that each of these are being treated as numeric data. So the float columns in the underlying database table have been transformed into some numeric form within Power BI. Before we proceed, however, I'm just going to expand more options and then choose to rename this particular table to conform with the standard adopted so far, where we have separate words beginning with capital letters. So now that we have successfully used DirectQuery mode in order to load data into Power BI, in the next video, we will turn our attention to building a visualization from that data. In the previous video, we saw how the data from a SQL Server database can be loaded into Power BI using DirectQuery. So we are currently in the report view where we can generate visualizations. But before that, let's head over to the data view and see what happens if we try to access the information in the video game sales table. So just clicking on it, well, we are given a message that since this table uses DirectQuery, the data is not available for us to view. So we will need to query for the data in order to access it. One way to do it is to build a visualization which uses the information in video game sales. So let's head over to the report view, and then from here, we will create a new visualization, which is a cluster column chart. Once that is in place, I'll just expand it so that it is a little bigger, and this visualization will have some similarities to what we built previously in that the genre column will be plotted along the x-axis. That is, each bar will represent a specific value of genre. As for the heights of each of the bars, this will represent the Japan sales. So let's just drag that field over to the values. And these are the sales in Japan for the different genres of video games. To enlarge this chart just a little more, I'm just going to hit this button here. And now we can see how the sales varied with each genre. We can start with the adventure genre, which has recorded the lowest sales at just about 2.69 million. And this, of course, is thanks to the single game, which we took a look at a little earlier. The tallest bar here represents role-playing games. So while in direct mode, we could not view the raw data in video game sales in the data view, when we generate a visualization from this data, the information is accessible. This is because when we take a look at the visualization, a query is made to the underlying database in order to retrieve the data and then generate the visual. Next, let's head over to the SQL Server database and modify the value corresponding to the Japan sales for adventure games. So we'll just hit back here and then switch over from Power BI to the SQL Server client and then run this query. Update dbo.videogamesales, set JP sales is equal to 10 where genre is equal to adventure. So when we execute this query, well, an update has been made. And to confirm this, let's rerun the select query, which we saw just moments ago. So when we take a look at the sales for adventure games, again, there is just a single row, but significantly, the JP sales column has now been updated from the previous value of 2.69 to 10. So how exactly do we get this in Power BI Desktop? Well, heading back over to it, you may notice that the adventure genre has not really been updated. Well, this is because Power BI Desktop works a little differently from the Power BI service, where your end users will be viewing the reports. Each time they load a report, well, DirectQuery will query the underlying database and retrieve the latest values. The Power BI service, however, is not something we will cover in this learning path. However, it is still important for you to know as a data analyst how you can pull in all of the latest information into Power BI Desktop, effectively forcing a refresh of the cache. Well, for that, you can just hit the refresh button, and then from the dialog which pops up, you will observe that all of the tables are now being refreshed with the latest contents. And soon enough, the graph also gets updated. While you may have missed it, I'll just hover over the adventure bar, which is now in the middle of the chart and not at the end. And sure enough, the JP sales number is the updated value of 10. Had you been on the Power BI service, well, this change will have been picked up each time the report is loaded since it performs a direct query to the database. But in the case of import mode, it may take a little longer for the update to be pushed to the local cache, in which case you may be served stale data. Alright then, we will now cover one more feature related to the different storage modes, for which we can head over to the model view. When we select video game sales from here, from the properties pane which pops up, it is possible for us to change the storage mode associated with a table. Specifically, when we expand the advanced menu, there is a single setting here for the storage mode. This of course has been set to DirectQuery for video game sales, but it is possible for us to change this to something else. Dual mode allows us to cache some data but not all of it, effectively serving as a hybrid between import and DirectQuery modes. Now, however, let's see what happens if we were to switch over from DirectQuery to pure import mode. Well, we are notified that this change will be permanent. So it is possible for us to switch from DirectQuery to import mode, but the reverse switch cannot be done. Once a dataset has been loaded into Power BI desktop in import mode, we don't have the option to switch back to DirectQuery. So make sure that this is a change you want to go through with. I'm just going to hit OK in here then, and soon enough, the change will take effect. So we now have a little more familiarity with the different storage modes available for data in Power BI. The aim of this course was to give you hands-on experience transforming raw data so that it can be set up for visualizations. You also cover the definition of a basic visualization, namely a column chart. To start off, you saw how related data can be combined into a single table in Power BI by essentially performing a join operation. While doing so, you performed some preliminary analysis of the data to understand what your dataset contains so that it is easier for you to imagine what visualizations can be created out of it. Next, you cover the steps involved in combining the data from several files into a single table, enabling you to analyze information from multiple files in one go. Essentially, you performed a union operation with CSV files. You then delved into a variety of transformations which help you focus on the specific data you need to present in a visualization, from aggregating data to filtering out unnecessary rows. Finally, you built a simple column chart from the contents of a Power BI table. While doing so, you got a glimpse into the different storage modes in Power BI and how these can affect your visuals. Having completed this course, you are now a master at preparing data for analysis with Power BI. You know how data sources can be connected to, how data can be filtered, aggregated, and modified to suit your analysis needs, and also how to build a simple visualization. This has prepared you for a crucial section in the DA-100 certification exam and has set you up to move on to other exam topics which build upon data preparation. A logical next step for you is to dive into modeling data using Power BI, where you can get hands-on with the DAX formula language, the definition of measures, as well as working with related data split across multiple tables. The goal of this learning path is to cover the different options available when building data models in Power BI. The purpose of modeling data is to ensure that data can be accurately and meaningfully represented in visualizations. And we will start off by covering various aspects around data modeling in Power BI. At a high level, we can say that data models, in effect, determine how data is represented in the first place. This can start off from the very basics like setting the types for different columns in tables and also the formatting for each of those columns, which has an effect on how that data is represented when it's used in visualizations. Now, throughout this learning path, we are going to explore various ways in which data can be modeled, and the reason for covering such a breadth of techniques is because data models can have a huge bearing on the accuracy of data which is conveyed in visualizations and reports. For instance, if you need to calculate the total expenses of various departments in an organization, you will need to correctly calculate the sum of all expenditures across all of the departments. Furthermore, modeling data also has a huge impact on the overall performance of visualizations. For instance, if you model the data correctly, this could mean that your charts load quicker and interactions with the charts are also smooth, ensuring a high quality user experience. And of course, there are various intricate details when it comes to optimizations, a lot of which will be covered in this learning path. So, from the importance of data models, let's now dive a little deeper and see what specifically modeling can involve. Well, one step will be to load the data which is required. While loading the data may fall under the purview of preparing data for analysis, the operative phrase here is data that is needed. When it comes to modeling, it is important that only the required data is selected and loaded into Power BI, since smaller datasets can lead to improved performance. Furthermore, it is also important to set the right data types for each of the fields. So once we load data into columns, we should make sure that each column is mapped to the correct data type. For example, if a specific column contains dates, we should model it as a date, which will allow us to perform a lot of time-related analysis using that column. Furthermore, the data which we load into Power BI in its raw form may not quite be sufficient when it comes to performing analysis. For instance, we may have a lot of order information which includes the quantity of certain products in the order along with their prices, and we will need to derive the value of each order by multiplying the price and quantities. So this is also part of data modeling, as is the setting of relationships between different tables which contain related data. Very often when working with Power BI, you may have related data split across multiple tables, and if you're familiar with relational databases, you will know that this is often done in order to optimize the space utilization of the data and avoid duplication. When data is split into tables, however, we need some way to combine them together when required, and this is where relationships come into the picture. So having summarized each of these steps, let's dive into each of them in a little more detail, starting with the loading of data into Power BI. So first of all, we should have a good idea of what is required to be presented in our reports, and based on that, we need to ensure that all the data which we need is loaded. Ideally, the data will be in a form where we can use it as is, but in some cases, we may need to derive additional fields from the existing data. An easy trap to fall into when loading data is bringing in a lot more than what we really need. While at first, this really won't seem to have any impact on either overall performance or the building of visualizations, over time, having just too many fields can lead to a lot of clutter, and picking the right fields for analysis becomes a little more painstaking. Beyond that, when loading data in import mode, loading more than is required will use up resources unnecessarily, even if we're not working in import mode and we have set the storage model to DirectQuery. We do need to consider that getting more data from the underlying data source will mean greater network traffic, and because of that, greater network latency. So, all of these are important factors to consider when loading data into Power BI. Another step which we looked at was setting the right data types for each column. At a very basic level, any field which contains numeric data must be modeled as some numeric field, whether a decimal number or a whole number, because this is what we will probably need to perform some aggregation on. So, for example, we cannot really perform an average calculation on text. Furthermore, the column types are also important when it comes to establishing relationships. Such relationships can only be set up when there happens to be at least one common column between two different tables, and when I say common, their values as well as types must correspond. Let's move on then to deriving data. So this is where we may need to create calculated columns within our tables by performing operations on other existing columns. So the example I cited a little earlier is where we have sales data in a table, which includes the quantity of a product ordered along with its price, and then we'll simply need to multiply those two columns to get the total sale amount. One type of data derivation which we will make extensive use of in the demos of this learning path is the creation of measures using DAX. While calculated columns give us a value for each row in a table, a DAX measure may perform a row-by-row calculation followed by some kind of aggregation. And speaking of aggregation, this can also be an important operation when it comes to deriving data. And another important operation is filtering data. In fact, we can create measures using DAX which perform some kind of filtering and also some aggregation. For instance, we may set a filter for all of the sales recorded in the region of North Africa and then aggregate them all together to get the total sales in North Africa. Moving along then to defining relationships between different tables. When it comes to modeling data, the first thing which often comes to mind is relationships. If you have any background in relational databases, you will know that data is often split across multiple tables, and this is done to avoid duplication of data and to improve performance. So when analyzing bank information, we may have one table containing customer data and another one containing the details of their bank accounts. And in order to set up a relationship, they need to have some common column. And this also has to be of the same type as discussed. When it comes to setting up relationships, it's not just the common column we need to worry about. We also need to ensure that the cardinality of the relationship is done correctly. So, if one customer can have multiple bank accounts, then the relationship should be set as one to many. Or if an account can belong to multiple customers, let's just say for a joint account, and a single customer can have multiple accounts in the same bank, the relationship is better represented as many to many. Then there is also the direction of filtering. So this is known as cross-filtering in the context of Power BI, and this can be set in either a single direction or both. So sticking with the examples of customers and bank accounts, should we be able to filter bank accounts based on customers or customers based on bank accounts? Later on in the demos of this learning path, we will see that this can have a bearing on some aggregations. So getting the relationships right in a data model is essential in order to portray accurate information in our Power BI reports and also to ensure that they perform in an optimal manner. So with all of this said, when it comes to data modeling, what are some of the tools which we can use in order to help us model our data correctly? Well, one of these is a date table. When it comes to data analysis, time is one of the crucial dimensions along which analysis can be performed. And of course, time can be expressed in various degrees of granularity. For example, if you're analyzing sales data, we may want to do this over a period of a year, maybe even a quarter or a month. So when we look at a date, we should not just look at it as a single value, but as a number of different values which can be arranged in some hierarchical form. And this is where Power BI's date tables enter the picture. So in a date table, we can not just express a date using its various dimensions such as year, quarter, and month. We can also format each of those dimensions in a manner which is suitable for our visualizations. For example, we may represent the month of February using the text February and also the number 2. Now a date table can be treated as any Power BI table and related to other tables. When it comes to the different dimensions of a date, well, we can enlist the help of the DAX formula language in order to design the table. This allows us to extract specific bits of information from a date, such as the day of the week, and can also help in the formatting of this information. And to get an idea, here is an example of a date table. So there are 4 different columns in here. The first column points to the date in the year, month, and day format. You'll see that the month column represents a month as a 3-letter string. And then we can have separate columns for the quarter and the day. Now the first column in here can be used to join the date table with any other table containing a date field. For example, the purchase date for a product. Let's move along then to another family of techniques when it comes to data modeling in Power BI. So in here, let's consider the fact that there is some data which is inherently hierarchical in nature. For example, if you have geographical data such as the country, state, and city in a particular table, these can be arranged in a hierarchical structure within Power BI, rather than treated as 3 entirely independent string columns. And the reason why this can be beneficial is because Power BI allows us to use such hierarchical data within visualizations. For example, to zoom in from a country level down to the state level and further down to a city level. As we move up and down the hierarchies, we will be able to see aggregated values across each level. So sales at a country level, at a state level, and so on. And beyond that, related data can also be cast together into a single unit. Another important consideration when modeling data is establishing row-level security. This determines the degree of access a user has in the Power BI service, and this can be done because each user can be cast into groups. And in the demos, we will see that row-level security can be set up to restrict users to just their own data. We will now take a close look at the star schema and also touch upon the related snowflake schema when it comes to modeling data for Power BI. And while doing so, we will explore the topics of fact and dimension tables. And to understand this, we will need to make use of an example. Well, for that, let's consider this table containing sales transactions for various restaurants which are part of a restaurant chain. The first column is a restaurant ID, and you'll see here that restaurants 1 and 2 each have recorded a single transaction here, but there are 2 transactions recorded for restaurant 3. The table also records the customer who made the purchase, the date of the transaction, and also the total bill amount. In a star or snowflake schema, this can be considered a fact table. So what exactly is a fact table? Well, you can think of this as one which contains data with regards to a frequently occurring event. These could be various sales recorded at a retailer, production numbers at a factory, or medical procedures at a hospital. An important feature of a fact table is that it is usually filled with a lot of numbers and dates, more precisely, information which can be aggregated in Power BI reports. So if a table contains details about the production of a certain item, this could contain the batch number, the time of production, and maybe even the weight of the produced good. One thing to keep in mind is that a fact table may not contain a unique key. Or if you're familiar with relational databases, it's one which may not contain a primary key. Well, with this in mind, let's head back over to our fact table containing restaurant sales data. So the sale amount column is something which can be aggregated, and this aggregation can be performed along various dimensions. This can be done on the basis of the sale date, a customer ID, or even the restaurant ID, or even on the basis of some category present in a related table, such as a city or state. And speaking of related tables, this brings us to the topic of dimension tables. So these give us additional bits of information about the recorded facts in a fact table. A dimension table is related to a fact table, and this could be either a direct relationship or an indirect one via another dimension table. As an example, think of a customer table which is related to the restaurant sales fact table we just took a look at, which contains customer specific information such as their names, date of birth, and so on. We could also have a restaurant table which is linked to it, containing more details about the restaurants where the sales have been recorded. When it comes to dimension tables, each row usually represents a specific entity which is unique in the table. That is, such tables can have a primary key. So in a customer table, there will just be one row for a specific customer. Given that dimension tables are related to fact tables, it is possible for us to perform aggregations on the data in the fact tables based on some of the fields in the dimension tables. For instance, we could aggregate the sales for each customer to figure out the most lucrative customers for a restaurant chain. So heading back now to our fact table, we can see that this includes a restaurant ID and a customer ID, and these can be used in order to establish a relationship with a separate restaurant table and a customer table. And of course, these will represent additional dimensions to this sales data. In fact, let's pull up each of these tables to see what these might look like. On the right, we have the sales table, and then on the left, we have a restaurant table, which contains details such as the restaurant name, city, address, and so on, along with a customer table just below that, which includes a name and a date of birth for each customer. To set up the relationships between these two tables, well, consider that the sales and restaurant tables do have a column in common. ID in restaurant maps to restaurant ID in sales. Now, in the restaurant table, the ID is unique. That is, there is just one row corresponding to a specific ID. However, this is clearly not the case in the sales table. Even in our example, there are two occurrences of the restaurant ID of 3, which means that the relationship between restaurant and sales can be thought of as one to many, given that for each restaurant, there are multiple sales transactions in the sales table. This also means that we can aggregate sales transactions for each restaurant, for example, to calculate the revenues recorded at each restaurant. And in fact, given that the restaurant table contains a city column, we could also get the aggregate sales at each city. Moving along then to the relationship between customer and sales, and this happens via customer ID in sales and ID in customer. Now in the customer table, we can consider the ID column as representing a primary key, so just one row for a specific customer ID. However, a customer may go on and record multiple transactions at the same restaurant or at multiple restaurants belonging to the same chain. This means that this relationship should also be modeled as one to many. So when we talk about a relationship as one to one, one to many, and so on, we are in fact referring to the cardinality of the relationship. Now, looking back at the restaurant table, you will see that this contains a column called category code. This category could point to various types of restaurants, for example, delivery only, pickup only, drive-through, or sit down. And for each of these categories, there may be other bits of information which doesn't make sense to store in the restaurant table. So we may have an entirely different table containing restaurant category details. Let's just expand our schema to get a sense for what the tables might look like. So we have sales at the heart of everything, and this is the fact table, and this has direct relationships with restaurant and customer. These are the dimension tables around sales. However, these are not the only ones. Restaurant and customer could be related to other tables of their own. For example, the restaurant table is linked to restaurant category, while a customer table could be associated with a loyalty program table. So while there is just a single fact table in the middle, there are various dimensions to these facts, starting from the customers and restaurants to restaurant categories and loyalty programs. This type of design is very common when it comes to Power BI and data analysis and is termed the star schema. This is when there is a single fact table in the middle and is related to a number of different dimensions around it. Strictly speaking, however, the star schema is set to apply when a fact table is directly related to a number of dimension tables. However, when the dimension tables themselves have further dimensions, as in this example, this is referred to as a snowflake schema. With that said, let's take a look at some of the features of a star schema. First of all, the fact tables which lie at their heart can be very, very large, potentially going into the millions of rows, given that they usually contain records of frequently occurring events, such as sales transactions at a retailer or the streaming of a video on a video streaming service. On the other hand, the dimension tables which surround them are usually much smaller, since they may contain unique entities. The dimension tables are typically meant to help with aggregating the data in the fact tables. In our example, we already discussed that it is possible for us to aggregate the sales for each restaurant or even each city, as long as these fields are present in the dimension tables. Furthermore, a star schema usually makes it much easier to manage large data sets. By separating the various dimensions from the facts themselves, we can avoid duplication of data. For example, by separating the customer information from the fact tables, we don't need to store the customer name for each transaction they have recorded. This usually means less storage and also improved performance overall. When it comes to designing data models in Power BI, one tool you'll need to use very often is the DAX formula language. We'll now take a closer look at what this language is and how it can help us model data. We start off with some of the salient points of the DAX or Data Analysis Expression language. First of all, this is not something which is unique to Power BI. This is available, in fact, for various Microsoft data analysis tools. Beyond Power BI, it is also available for Microsoft's analysis services as well as Power Pivot. So, if you get familiar with DAX, you can take your skills beyond just Power BI. The purpose of the DAX language is for us to be able to derive data from the existing raw information. So, we can use DAX in order to create calculated columns as well as measures. The building blocks of the DAX language are functions as well as operators. In many ways, DAX is quite similar to other programming languages, where you have functions with arguments, return values, and where it's also possible to make nested function calls. An important consideration when writing DAX formulas is that these can operate in something called a filter context. A filter context is one which is only applicable to specific rows in a table, and operations can be performed using that filtered data. This is something which will become much clearer in the demos of this learning path, and we will spend a lot of time on this topic, since it is important for the DA-100 certification. The most common use of the DAX language will probably be to create measures. So measures are essentially values which are computed over a large portion of a dataset, if not all of it. For example, what is the aggregate of all expenses for each department in a large company? Or what are the expenses for each department in the region of Europe? In many ways, measures are similar to calculated columns in that they are typically derived from raw data. However, unlike calculated columns, they don't need to operate over rows on an individual basis and can simply aggregate the contents of certain columns. In fact, measures can often be used in order to perform a row by row calculation followed by an aggregation. For example, you could multiply each of the transaction amounts for sales data by an exchange rate and then sum them up to get the total sales in a specific currency. Now, measures need not operate on the entirety of the dataset, so it is possible for us to apply filters when doing such aggregations. For example, we can only consider the sales data from Southeast Asia or for customers in the 18 to 24 age group. So now that you have some idea of what measures are, well, let's switch to a rather important topic in the context of Power BI, not just from the point of view of the DA-100 certification, but also when you need to use Power BI for advanced operations. And this has to do with how context is defined for various DAX operations. Well, for this, consider that during data analysis, values such as total sales are usually aggregated, where you may not care whether a specific customer bought a product for $25 at a specific store, but you may be interested in knowing that a specific store recorded a total of $30,000 worth of transactions in a month. Now, such aggregations can be performed on various keys. So you could aggregate sales based on a restaurant, on a specific category of restaurants, such as drive-thrus, or maybe even restaurants located in a specific city. And given that such sales can be aggregated across different dimensions, the specific value of the aggregated sales will be different for a different set of dimensions. For instance, the numbers for fast food restaurant sales in the city of London in the month of February will likely be very different from the sales recorded in all drive-through restaurants for the whole year. In other words, the value of aggregated sales depends on the context. When it comes to Power BI, such context can be determined by various filters. These filters could be set within a DAX formula explicitly, or may even be set by a user interaction in a visualization. For example, when a user clicks on a particular bar in a bar chart. An example of a filter is one which only considers sales from fast food restaurants. So this could be based on restaurant types, but other dimensions, including date dimensions such as month, quarter, and year, could also be part of the filter. Now, the reason we are focusing on the filter context is because when it comes to DAX formulas, this can play a significant role. For example, there are certain DAX functions which are meant to operate in a filter context. There is one called calculate, which will first filter the data based on the filters specified, following which it can perform operations on that data, which includes aggregations. While understanding the DAX language can be rather simple if you have any programming background, understanding the filter context may be the most difficult part. So we will spend a lot of time on it in the demos of this path. And now, let's take a quick glance at the different types of DAX functions. This will help us understand what this language is capable of and also give us a glimpse into what is possible with Power BI. So first of all, there are a variety of aggregation functions, which could take in a variety of arguments and then returns a scalar value. Examples of these include sum, which performs a simple sum operation, max, which returns a maximum value, and average x, which evaluates an expression and then returns an average. And then there are a variety of filter functions. These are functions which allow us to work on filtered data, such as calculate, filter, and lookup value, but also functions which can be set to ignore any existing filters, such as all. Beyond that, there are the regular date, time, and math functions, which should be familiar to you if you have any prior experience with Excel formulas. So the today function returns the current date, abs returns an absolute value, and numbers can be rounded to specific decimal units or to integers using the round function. And then there are functions which can be categorized as information functions. For example, is blank tells us whether there is a blank in the cell of a table, contains can be used to perform a substring search, and is number can be used to check for numeric values. Usually when using DAX, you will end up using a combination of these functions in order to create a single DAX formula. We will now discuss something which is crucial but often a neglected topic when it comes to designing data models for Power BI. Specifically, designing models which are optimal in terms of simplicity as well as performance. To start off, let's take a look at a common practice when it comes to designing models, not just for Power BI, but for any tool where data needs to be stored. Now, usually, a data analyst will need to gather a lot of data to be presented for analysis. When doing so, it is quite easy to get tempted and load in all data you have access to, regardless of whether it is really needed. You may well think, what if I need it at some point? Well, the problem with this approach is that over a period of time, this will make everything much harder to maintain. For example, you may need to change the display format for all numeric columns so that they are represented as whole numbers, which means that you will also need to apply this transformation to columns which are not referenced by any visualization, simply because you may not be sure whether it is in fact used by a visual. So, unnecessary data can lead to a lot of clutter, but significantly, they can also degrade performance. To understand this, consider that a lot of the data may be stored in import mode, in which case they will all be loaded into memory. If unnecessary data is loaded into memory, it won't be long before visualizations start performing rather slowly, which is why it helps for us to follow a rather general rule of thumb. Keep everything as simple as possible. In fact, try to follow a somewhat minimalist approach. It'll just save a lot of headaches further down the line. Of course, it's all very easy to say that we need to keep things simple, but what precisely does this translate to when it comes to Power BI models? Well, this could be as simple as removing any unnecessary rows or columns from the imported data. So, when it comes to data analysis, having details such as customers' email addresses and phone numbers won't be particularly helpful, in which case they can simply be eliminated altogether. Another factor here is to make sure that data is not duplicated. This is similar to normalization adopted in relational databases, and the justifications for normalization also apply to Power BI. Duplication of data can lead to inconsistencies over time, where one copy of the data is updated and another one is not, which means that any visualizations built out of this data could just portray incorrect information. Furthermore, it helps to combine tables whenever this is possible. If your task is to analyze sales data, it is possible that your sources come from 12 different files, one for each month. When loading these files, by default, 12 different tables will get created, in which case you are best off combining them into a single unit. Another area where models can be simplified is relationships. It is best to minimize the total number of relationships between tables overall and also to lower the cardinality of each of them. So we should avoid using many-to-many relationships when a one-to-many relationship will suffice. And on the topic of relationships, we should definitely avoid circular relationships between tables. Another way to simplify data is to use measures in order to perform some summarization. For example, calculating the sum of sales or the average of prices and so on. Such aggregations can also be done at the visualization level. However, this does come at the cost of some performance, and it is better to push this back to the level of measures. Alright then, so now that we have an idea of some of the concrete steps which can be taken to improve performance in Power BI, let's take a look at some of the potential bottlenecks in performance. One very common source of this is the use of very complex visualizations. If you have way too many categories and you also have some slicers associated with your visuals, remember that each interaction with a visual or even a slicer does involve some computation work to be performed. Also, too many visualizations mean that a lot of queries need to be executed under the hood on the data. Even DAX queries could slow down performance if they have not been defined correctly. Just like with any code, it is possible to make DAX formulas needlessly complex with too many nested function calls, not using filters when they could help, and so on. Furthermore, relationships which are not properly defined can also slow things down. So if a relationship can be set as one-to-many, we should do so, given many-to-many relationships perform rather poorly. And there is also Power BI's automatic date time feature. This is one which auto-detects any date columns within your data and then applies date hierarchies to those columns. This can be a very cool feature and potentially very useful. But don't use it if you don't need it, especially since this is turned on by default. So, given these potential bottlenecks, what can we do to simplify things and improve performance overall? Well, when it comes to DAX formulas, if you happen to have a rather long and complex one, using variables can help. Much like with any programming language, you may use a variable to store a value which is the result of an operation. That variable can be used to reference the value multiple times in the formula, while the alternative is to simply perform the operation over and over again. Another important consideration is to do as little work on the data within Power BI as possible. So, if another team sends you a file with your source data, well, consider asking them to perform whatever aggregations, filtering, or trimming of data which you require before sending the file along. In which case, you can focus much more on generating visualizations from the data rather than perform pre-processing. And then I'll reiterate a point which I had touched upon earlier, where we need to keep relationships simple. Avoid connecting a table to multiple other tables unless necessary, and we should definitely avoid circular relationships, since these could seriously muddle a lot of aggregations. To help us identify bottlenecks and potentially fix them, we can make use of Power BI's Performance Analyzer utility. This can point us to the time taken for various operations and guide us towards any optimizations which need to be carried out. Moving along, let's take a look at some of the optimizations which can be performed in the context of DirectQuery. You will recall that DirectQuery is a storage mode where the data is not cached by the Power BI service, but instead is queried from the underlying source when required. Since the data is retrieved as needed, this ensures that we always get the latest data. Of course, this means that the underlying data source needs to be queried each time we ask for the data. Such a query could be triggered by us simply interacting with a visualization or loading a new report. When we are sending queries to the underlying source, very often a relational database, well, the performance of that source becomes a huge factor. If the database is slow, then querying that data will take some time, which means that our visualizations will take much longer to load. If that database is located on a different machine in the network, well, network latency also plays a role in performance. So, if your database is located in a different corner of the world, well, perhaps direct query is not the best storage mode. So, if your visuals are performing poorly and you do have data which is retrieved using direct query, you should look into this as a source of your bottleneck. However, in case you're unsure, you could always make use of the Performance Analyzer utility. Now, if the freshness of the data is absolutely crucial, then you will need to use direct query, in which case it helps to know how exactly such models can be optimized. Well, first of all, make sure that the source of the data itself is running in an optimal manner. If this happens to be a relational database, make sure that you use indexes for the queried fields so that you don't need to perform a full table scan. Furthermore, make sure that you only query for the data which you really need so that the quantity of data sent over the network is minimized, which in turn will reduce any network latency. Beyond that, we need to consider the fact that interactions with visualizations can be rather compute intensive. even when querying data which has been cached. However, for visuals built on DirectQuery data, well, we should try to minimize interactions as much as possible. Now, when it comes to visualizations, it is possible for us to apply filters and slicers in order to get summaries for just a subset of the data. In case you haven't used slicers before, each time you interact with it, it triggers a query on the underlying data. To avoid queries based on accidental interactions, you could include an apply button where you will interact with the slicer and then trigger a query only when that apply button is hit. So this concludes the theory portion of this learning path, and it's time to move on to the demos where we implement what we have just covered. Moving on now to the demos of this learning path, I assume that you already have Power BI Desktop installed and set up on your system, and that you have taken up the learning path, prepare and process data in Power BI, or at least are familiar with the topics which it covers, since we will now be building upon it. On the screen in front of you, Power BI Desktop is up, and specifically, I am in the Reports view, which you can navigate to by clicking on the top of the three icons in the left menu. In this demo, we will start off by creating a new table by combining the contents of two tables already loaded into Power BI Desktop. First, however, I'm going to create a PBIX file where all of the work which we perform within Power BI Desktop can be saved. For that, we can head over to the File menu and then head over to Save As. And then we can just give a name to the Power BI file. I'll call it Table Union to point to exactly what we will be accomplishing in this demo, and then navigate to a location on my file system where this can be saved, and then save it down. Once that is done, towards the top you can see the name of the PBIX file, and as the demo goes along, I'll periodically be saving things down to this PBIX file by using the keyboard shortcut of Ctrl S. Looking now at the Fields menu on the right, you'll observe that I have not loaded any data into this particular PBIX file. And before we get to that, well, let me pull up the dataset itself. So this is an Excel file with the name Honey Production. And as implied by the name, it contains details about the production of honey across various states in the United States over a 2-year period. And in fact, the data for these 2 years is split across two worksheets in this Excel file called 2011 and 2012. So you now know what the 2-year period is. This honey production file is part of the course materials. Alternatively, you can download it from this URL on kaggle.com. Before we load this into Power BI Desktop, let's quickly take stock of what exactly this file contains. So you'll observe that in the 2011 worksheet, there is the first column called State, which contains the 2-character code for the specific state in the United States. And then there is a year column, followed by statistics with regards to honey production in the corresponding state. There are the number of columns of honey, the yield per column, the total production, and so on. Significantly, row number 1 of this particular worksheet contains the header for what can be a table when loaded into Power BI. And scrolling further along, we can confirm that there are a total of 41 rows including the header, so there are details for 40 states in total. So when this data is loaded into Power BI, we will have a total of 40 rows and 8 columns. And when switching over to the 2012 worksheet, well, you see that this will contain the same 8 columns, and the headers are exactly the same and in the same order. This is significant because when we load this Excel file into Power BI Desktop, 2 separate tables will be created, one for each worksheet. And in order for us to combine the contents of the 2 tables into a single unit, we will need the columns to match. So now that we know the columns are identical, we can scroll along and confirm that in the 2012 sheet, even the number of rows are the same, though this is not quite needed. Before we pull the information into Power BI Desktop, I'll draw your attention to one more detail about the 2 worksheets. So in here, it is only column A which contains text data, and all of the other columns can be treated as containing numeric data. Alright then, let's switch over to Power BI Desktop, and to load the Excel file, we can head over to Get Data and choose Excel Workbook. Though we could also make use of the Excel Workbook shortcut present right next to Get Data. So once this selection is made, let's navigate over in our file systems to the Honey production dataset. Once the selection is made, and then we choose to open within Power BI Desktop, well, as you'd expect, the navigator shows up, and then we can select which of the two worksheets in this Excel file we would like to load into Power BI. I'll first select the 2011 worksheet and quickly glance at the contents to make sure that everything looks in order, and will then select the 2012 sheet. So once these selections have been made, let's stick with the default load settings and then hit the load button. So we won't be performing any explicit transformations just yet. Once we do that, well, in a few moments, you will observe in the Fields menu that there are two separate tables which have been created. And these correspond to the names of the two worksheets in our Excel file. So there is a 2011 table and a 2012 table. Let's do a quick sanity check to ensure that the data has loaded correctly by switching from the Reports view over to the Data view. And then we can head over to the Fields menu and then expand the 2011 table. In fact, that has already been loaded, and on the left we can confirm that the data does seem to correspond to what was present in the files. So far so good then. Another important factor is in the Fields menu, where you'll observe that aside from the State column, all of the others have the capital sigma sign next to it, pointing to the fact that these values can be summarized, hence they are of some numeric form. Just quickly scrolling along, we can see that there are a total of 40 rows. And then when we expand the 2012 table and pull that into view, sure enough, this also contains 7 numeric columns and a text column for state, and a total of 40 rows. Alright then, now comes the time for us to combine the contents of the 2011 table and the 2012 table into a single table. So this is where the modeling of data comes into the picture, where we have already loaded the contents which we need from one or more sources over to Power BI Desktop, and we then structure the data in a form so that we can later use it when creating visualizations. In the case of the 2011 and 2012 tables, well, consider the case where we would like to visualize data not just for each of the individual years of 2011 and 2012, but also in aggregate. In such a case, it helps to have all of the contents in a single table, and that is precisely what we will now do by first clicking on the New Table option. The moment we do that, well, you will observe that it is now possible for us to define a DAX formula in this space. You'll observe that by default, there is already an incomplete expression in here, table is equal to, and in fact, this is the full syntax we can apply when creating a new table. So the DAX expression here is table name is equal to followed by an expression. So this formula which has now popped up here points to the fact that the name of the new table is table. However, let's give it a more descriptive name. I'm going to call this union table, followed by an equal to symbol, and then we can define an expression. At this point, Power BI's autocomplete has kicked in, and you can see that it is possible for us to define the union table as being equal to one of the other tables already loaded. At least in my case, there are just the 2011 and 2012 tables, but beyond that, there are also a whole host of DAX functions which we can use in order to define an expression. Well, the one we are looking for in order to combine the contents of the 2011 and 2012 tables is the union function. So I have just typed in UN, and then the autocomplete suggests the union function, and there is also a description of this function here, that this will return the union of tables whose columns match each other. So this definitely applies to our 2011 and 2012 tables. So let's select this function, and then autocomplete helps us with the arguments for the union function as well. So the first argument here is a table, So let's just add in the 2011 table, and then we specify comma followed by another table. Of course, we could make use of some of the DAX functions in order to define a table in the form of an expression, but let's just select the 2012 table in its entirety here, and this is the result. So you can see the full DAX expression in the formula bar and the contents of the newly created union table below. At the top left, you can see that the name of this table is visible, and this is something which can be edited. Furthermore, in this union operation, we only passed along two tables as arguments. However, as the formula message indicated, it is possible for us to combine the contents of multiple tables as long as their columns match. In the Fields menu scrolling along, we can confirm that there is indeed a new union table, and then heading back over to our grid view, well, scrolling down here shows us that this table contains a total of 80 rows. So it does look like it has the combined data from the 2011 and 2012 tables. So we have now successfully performed our first modeling operation using a DAX expression. And we now have a single table containing all of the data which we need. So if you'd like to build a visualization conveying the aggregate information across the honey production datasets for 2011 and 2012, well, we can just reference this union table. In the next video, we will take a look at how we can use the DAX language in order to create a new calculated column in a table. In the previous video, we saw how we could create a new table by performing a DAX union operation on two existing tables in Power BI Desktop. Now, the purpose of modeling data is to represent it in a form which can be used for visualizations. And this is not quite the case with the raw data. Now, the raw data in this union table does contain all of the information which we need. In that, it contains the honey production data for both 2011 and 2012. And then you'll observe that the last column here, called prod value, points to the value of the honey produced for the corresponding state. Looking at row number 1, which represents the state of Alabama, the value of honey produced is about 1.13 million. And you can see that this is simply a product of two of the other columns, total prod and price per pound, with a little bit of rounding. Now, this is a value represented in US dollars, but just a little later, we will see how this value can be expressed in a different currency, which may be useful for analysis. Before we add a new column, however, let's model the ones we already have in place over here, starting with price per pound. So let's select this column first so that we can view some of its properties. And towards the top left, you can see that there is the name property. And then we can also set the data type, which has automatically been set to a decimal number. This is definitely the most accurate type for this particular column, so I'm going to leave it at that. However, there is also a format setting. By default, this has been set to general, but when we hover over it, you'll observe that this is a property which allows us to configure how exactly this value will be displayed. Given that price per pound represents a value in dollars, it does make sense for us to convey the fact. In fact, if you are working in a global organization with offices in many different parts of the world, if you are displaying some value in a currency, it is best practice to make it explicit what that currency is. When we expand this format dropdown, you'll observe that it is possible for us to set a value as a currency. Keep in mind that this in no way changes the actual value represented by the data. It only affects how it is displayed. So we can set this value to a currency. We can also set it to appear as a decimal number and also a whole number. Alternatively, if a column conveys a value as a percentage, well, we can format it as such. Once again, I will emphasize that this merely changes the formatting of the data and does not change the data itself. So when we select this option of currency, well, you can see that a dollar symbol appears before each value. And this is because In my operating system, I have set the region to United States, which is why it has auto-detected dollar as a currency. But if the value in your dataset represents a different currency, well, you can head over to this currency menu, and then, well, there are a whole host of currencies which you can configure for your column. So this includes the US dollar, of course, as well as the British pound. You'll observe that there are two different representations of euro values, where the euro symbol precedes the number, and then one where it follows it. And then scrolling along, you will notice that nearly every currency in the world is represented here, and different languages as well. So there is the Indian rupee symbol as well as the Indonesian rupiah. So now that you have an idea of how currency symbols can be represented, let's just explicitly select the United States dollar here. And following that, we may as well rename the column so that the currency becomes even clearer. So when we right click on the column, we can choose the option to rename. And I'm just going to call this price per LB or pound in dollars. Alright then, we have now successfully modeled this table so that any reference to the price per pound column will convey that this represents a value in US dollars. Now you will observe that the prod value column should also be represented as US dollars. So let's just repeat the steps which we performed for price per pound by selecting prod value. So you can see here that the data type is whole number, as is the format. Next, we head over to the format options, select currency once again, and as expected, the default US dollar symbol pops up. And now, let's just rename this column as well and convey that this represents the production value in dollars. Alright then, we have now successfully applied formatting to two different columns, but now it's time for us to add in a brand new column. For argument's sake, let's just say the company performing the analysis on this data happens to be located in the United Kingdom. While it is possible for them to get a sense of the total honey production when expressed in terms of US dollars, it may be a little more intuitive for them if the value is expressed in their own local currency of British pounds. And for that, well, we can create a new column which conveys the price per pound of honey in British pounds. This can be obtained by multiplying the price per pound in dollars column with the current exchange rate. Well, for that, let's head over to the home menu, and in order to create a new calculated column based on one or more existing columns, we can just choose the option of new column and then set the calculations in terms of a DAX expression. To demonstrate how, let's just go ahead and click. However, make sure that it is the union table which is currently the active one, since this new column will be created in the currently active table. And as we saw with the definition of our union table, the DAX formula bar pops up, allowing us to specify a DAX expression for this new column. Before we get into the DAX expression itself, I'll draw your attention to the fact that a new column now appears towards the extreme right of the table. By default, this has been given a header of column, and this also appears as the name of the column in our DAX expression. So similar to what we saw with the DAX table expression, in order to define a new column, this is the syntax which we can apply. So rather than the rather nondescript name of column, let's give a more meaningful name of price per pound in pounds, since this will convey the production value in British pounds. Then to complete the expression, we will reference the price per pound in dollars and then apply an exchange rate to it. So I have just searched for PRI, and from the autocomplete options, you will observe that there are a handful of DAX formulas, but significantly also a reference to price per pound in dollars in the union table. So in a DAX formula, it is not just references to tables or functions which are permissible, but in fact, we can reference individual fields within our tables as well. Now make note of how exactly we can reference a specific field or column in a Power BI table. So the syntax here is, within single quotes, we reference the name of the table, which is union table in this case, and then specify the name of the column within square brackets. Here it is price per pound in dollars. So once this selection has been made, well, let's just complete the formula by multiplying the price per pound in dollars by an exchange rate, which I'm just going to hard code in this formula. So we'll add in the asterisk or multiply symbol followed by 0.71, which is the prevailing exchange rate at the time of this recording. And immediately, you will see that this new column has been created and it has been populated with the calculated values. When we scroll along, we can confirm that all of the values have been filled in. And then I'll draw your attention to the fields menu on the right, where under union table, you'll observe that price per pound in pounds now also shows up. Significantly, the symbol next to it contains a calculator icon pointing to the fact that this is a calculated column. You will notice that this icon also contains a capital sigma sign to point to the fact that this is a value which can be summarized. Alright then, it's now time for us to apply some formatting to this column, given that it represents a currency value. So let's select this column, head over to column tools, and then from the currency symbol menu, we can make the selection of the British pound symbol. Before clicking, however, I'll point out that the values in this column are currently not rounded to any decimal places. And this is because the precision has been set to auto, as you can see just above this menu. However, once we make this currency symbol selection for pounds, well, the values have all been rounded to 2 decimal places, and then in the currency precision field at the top, you'll see the number 2 which now shows up. This is a precision value automatically chosen by Power BI for a currency column. So we now know how to create a calculated column using the DAX formula language in Power BI. So a calculated column effectively performs a row by row calculation in order to derive a value. In the next video though, we will take a look at how the contents of multiple rows can be summarized when we define a measure. In this demo, we will create a measure in Power BI. A measure is effectively a calculation performed on a table, but unlike a calculated column, which we covered in the previous video, we will see that a measure can be calculated across multiple rows in the same table. Before we create a measure, well, I'll draw your attention to the dataset itself, specifically to the row corresponding to the state of California, represented by the symbol of CA. This is because California happens to be one of the top 3 states in terms of total value of honey produced, with the other states being North Dakota and South Dakota, represented by the symbols of ND and SD respectively. We will now generate a measure which will compute the total value of honey produced by those 3 states in this 2-year period. Well, for that, let's head over to the Home menu, and under the Calculation subgroup, you'll observe that we have already used the new table and new column options, but now there are 2 different options as far as creating a measure is concerned. Choosing the new measure option will allow us to define a measure by means of a DAX formula directly. However, if you'd like some help in configuring a formula and you'd like to make use of a user interface in order to construct the measure, well, there is the quick measure option. In fact, that is what we will now explore, and we'll see how it automatically generates a DAX expression based on our selections from the user interface. And before we make use of this interface, our goal is to compute the total value of honey produced across the 3 states of California, North Dakota, and South Dakota over the years of 2011 and 2012. To do this, we can select the type of calculation from this drop-down menu, and you'll observe that there are a handful of options available here. We can perform an aggregation based on a category, So we can compute the average, variance, and so on. So from this menu, we can select the type of aggregation, following which we will need to specify the fields from which the categories can be obtained. Scrolling further along, you'll observe that there are a whole host of calculations which are possible, but what we are interested in is a filtered value. This is because we want to filter through only those rows in our dataset which correspond to the states of California, North Dakota, and South Dakota. So once we make the selection for this calculation, well, there are two additional details which we will need to supply: a base value and a filter. The base value corresponds to the value which we would like to include when we apply the filter. So in our case, since it is the production value in US dollars which we would like to portray, that is what we can fill in here. However, the prod value in dollars is available in each of the three tables imported into our Power BI desktops. However, since we would like to aggregate the values across 2011 and 2012, well, it is just the union table which contains the data we are looking for. So let's just expand that and then drag over the prod value in dollars. And you can see that by default, it is the sum of this production value in dollars which will be computed. So this is the default aggregation for any field in Power BI. However, if you'd like to change the aggregation type, just expand the More Options menu, and then we can apply an average, minimum, maximum, and a few other types of aggregations. Let's just stick with sum, however, and then we move on to the filter. So while the base value points to the column in our dataset which we would like to perform an aggregation on, when it comes to the filter, we define which rows in the dataset should be included when the aggregation is performed. To include only those rows where the value of state is equal to California, North Dakota, or South Dakota, well, we will need to drag over the state field over to the filter, since this is the column on which the filtering will be performed. Following which we can specify the values which apply to our filter. Here, all of the distinct values in the state column appear, and then we can select California first, scroll along and select ND for North Dakota, and then a little further along, SD for South Dakota. So with these three selections done, well, I'm just going to go ahead and hit OK, but note that that button does not quite fit into my screen, given that Power BI is meant to work with a higher screen resolution. Apologies for that, but you can just go ahead and hit the OK button, and soon enough, our quick measure has been created. And you can see the DAX formula which has been generated automatically for that. So much like the syntax for a calculated column or a new table, the syntax for a measure is the name of the measure followed by an equal to sign and then an expression. In this case, Power BI has automatically chosen the name of prod value in dollars for CA, ND, or SD as the name of the measure, and we will soon modify this to be a little more concise. And then the expression which has been generated for this, well, this makes use of the DAX calculate function. Now, in the context of the DA-100 certification exam, the calculate function is quite important because it also happens to be one of the most useful ones in Power BI. It effectively allows us to perform a calculation in a filter context. What exactly does this mean? Well, you can think of it as applying a filter on the data and then performing an operation on the filtered data. So let's take a look at how exactly this calculate function works. You can see here that this is defined between lines 2 and 5 of this expression, and it takes in two arguments: an expression to be evaluated, and then the second one is a filter. Let's first take a look at the filter argument here, defined on line number 4, as it will help us understand exactly how the calculate function works. So our goal, you will recall, is to sum up the production value in US dollars for the states California, North Dakota, and South Dakota, which means we are only interested in those rows of the union table where the value of state is either CA, ND, or SD. And that is precisely what this filter does. It says that we only need to include the rows in the union table where the value of the state column is in, followed by an array containing the valid values for the column, at least for our filter. So these are CA, ND, and SD. And note that given that these are text values, we specify them within double quotes. And also, this entire array of values is defined within curly braces. Also make note of the in operator in here. If you have constructed SQL queries before, you should be quite familiar with how it works. So just in case you're not, this effectively ensures that only those rows from the union table will be selected where the value of state is one of CA, ND, or SD. Alright then, now that we're down to those specific rows corresponding to the states, we have defined our filter context. So within this context, what exactly is the calculation which we need to perform? Well, this brings us to the first argument to the calculate function. Since we want to just sum up all of the values of production value corresponding to these states, well, we make use of the DAX sum function and then point this to the prod value in dollars column of union table. Once again, make note of the syntax when referencing specific fields within Power BI Desktop, where we have the name of the table within single quotes and then the name of the column inside square brackets following the table name. So just to summarize, this calculate function will effectively filter through those rows in our union table where the value of state is either CA, ND, or SD. And following that, well, the contents of the prod value in dollars column will be summed up. What is returned by this particular measure is a single scalar value. To see what exactly that value is, we will need to head over to the report view and then create a visualization which renders that value. But before we get to that, I'll draw your attention to this new measure which now appears within the union table in the fields view. So you can see prod value in dollars now has the original column and there is also a new measure. The icon to its left points to a calculator, conveying that this is a calculated measure. However, this is different from a calculated column, which is the price per pound in pounds. So while our calculated column has a little sigma sign next to it, our measure does not. And the crucial reason for this is that the calculated column can be summarized, but the measure by default is a summary. To elaborate on what I mean, I'll draw your attention to the fact that the calculated column, price per pound in pounds, is a calculation performed for each row in our dataset. Pointing to row number 1, you will see that the value of 1.78 pounds is simply the product of the price per pound in dollars, which is $2.51, and the hard-coded exchange rate which we supplied of 0.71. And similarly, we can compute the price per pound in pounds for each of the other rows. And given that there is one value here for each row, well, we can summarize the value, perhaps compute an average of the price per pound in pounds. However, given that our new measure does return a single value, there is nothing to summarize. And this is a crucial difference between a measure and a calculated column. And make sure to remember that for the certification exam. Now the name of this measure, prod value in dollars for CA, ND, or SD, was set automatically by Power BI. Of course, we have the option to give it a more meaningful name. For that, we can just head over to the More Options menu right next to the measure and then choose the option to rename. Now, let's just call this prod value for top 3 states. And then I'll just click outside in order for this to take effect. And now we have the newly renamed measure. And now for us to see exactly what value is returned by this measure, let's head over to the report view. And then I'm just going to select this prod value for top 3 states measure, and a visualization has automatically been selected. You'll notice that this is a clustered column chart with just a single bar, given that this represents just a single value. But to get an idea of what the value is, Let's just switch to focus mode for this visual. And now we have a clearer idea. So we can see that prod value for top 3 states now appears in the values property for this visualization. And from the chart itself, well, the height conveys that this represents a value of a little over 200 million, just a shade under 230 million to be precise. In the next video, we will build upon this visualization and also explore a table visual. In the previous video, we defined our first measure using the quick measure feature in Power BI, and with its help, we were able to compute the total value of honey produced in 3 different states in the United States across the years of 2011 and 2012. So when plotting the measure using a clustered column chart, we can see that this represents a value of a little over $200 million. But now, let's put this value into context. How does this compare with the total value of honey produced across all the states in our dataset? Well, for that, all we need to do is to head over to the Fields menu and then select the prod value in dollars field. This will automatically get added to the values property for the visual, and here we have it. So the light blue bar represents the production value for the top 3 states, and the dark blue one points to the overall honey production. Of course, it is important to note that the overall honey production does include the production from the top 3 states as well. So the total value is always going to be greater than the sum of honey production for the top 3 states. You'll also notice from the y-axis that the scale of values has now also changed. Previously, it represented values in millions, and now it points to values in billions. And then the total honey production is a shade over 500 million here. However, to get the exact values corresponding to each bar, let's just hover over them, starting with the overall honey production. So this corresponds to $539 million across the 2-year period. As for the top 3 states, well, they raked in a total of just a shade under 230 million over the same period. So with a quick mental calculation, we can see that all of the other states outside of the top 3 generated a total of $310 million worth of honey. Also notice how the 2 different bars which we have in this chart represent slightly different types of calculations. The light blue one, of course, corresponds to the measure, which returns a single numeric value, whereas in the case of the dark blue bar pointing to the overall honey production, this has been computed by summarizing the contents of the prod value in dollars field. Alright then, let's move on now from a quick measure over to a table visualization. While visualizations are not the focus in this learning path, we will be using them extensively when we define a whole host of measures using the DAX language and then plotting their values. So now, to clear out our report view, let's just cancel out the prod value in dollars column and also the prod value in the top 3 states, and then switch over to a table visualization. In a table, we can display some of the raw data in our datasets and can also display the results of aggregate operations. We will now use a table visualization in order to view the aggregate value of honey produced in each of the states over the 2-year period. So once the visual has been selected, well, we can decide what values it should convey. Since we would like to see the honey production numbers from each state, let's just drag and drop state into the values menu, and immediately you will see in the report view that there is a single state column which now appears in our table. Note that in here there is a single row for each distinct value of state within the union table, and then to sum up the production value in dollars for each of the states, well, as you might expect, we just need to select or drag and drop the prod value in dollars column. And here we have it. We can see that the first of the states, that is Alabama, produced a total of a little over $2 million worth of honey, and given that the prod value in dollars has been summarized for the entire dataset, This is across the 2 years of 2011 and 2012. So there are 2 occurrences of Alabama within the dataset, and the production value in dollars column has been summed up over those 2 occurrences. This also applies to each of the other states represented in this table. Here we can confirm that the state of North Dakota is far and away the top honey producer with a total value of $118 million of honey produced, and South Dakota is in second place at just over half that quantity. Furthermore, right at the bottom, there is a total computation where there is a single value returned for the prod value in dollars. This also represents a default behavior for Power BI tables, where a total row appears summarizing the contents of the numeric columns. Now, I will emphasize that these values represent a sum of the production numbers for both 2011 and 2012, because this is how Power BI tables work by default. When you select one column, such as state, which has categorical or discrete values, and then add in a numeric column, well, the contents of the numeric column will be summed up for each distinct category. However, if you'd like to modify this default behavior, well, let's just head over to the values pane and then expand the options for prod value in dollars. Here, you will see that by default, a sum operation is performed in order to aggregate. Alternatively, we can display the average honey production within our dataset for each state, the minimum or maximum values, and other aggregations as well. And then there is also the option to not aggregate at all, for which we can select Don't Summarize. And this is the result. Looking at the top 2 rows, you will notice that now there are 2 occurrences of Alabama here, corresponding to the 2 rows for that state in the union table. The prod value in dollars corresponding to Alabama of a little over 1 million in each case points to the total value of honey produced in 2011 and 2012. So we now have an idea of how table visualizations work in Power BI, and as mentioned earlier, we will use this extensively throughout the demos in this learning path. So now that we know how to define measures and then portray them in a visualization, in the next video, we will see how we can define a measure which translates the numeric values in a column to a star rating. Previously in this course, when creating a quick measure, I did point out that generally quick measures return a single value which is a summary of multiple rows in a dataset, as opposed to calculated columns such as price per pound in pounds in our union table, which perform a row-by-row operation. However, it is not strictly the case that a measure will combine values across multiple rows. And now we will see how a measure can be used to transform the contents of a numeric column to a star rating for each row in a dataset. And for this, let me draw your attention to the 4th column here in this table, yield per call. So this points to the quantity of honey extracted from each bee colony. The higher the value, the more efficient a particular state is in extracting honey from the available bees. So we could say that the state of Mississippi, represented by the abbreviation MS, with an yield per colony of 115, is more efficient at getting honey as compared to, say, the state of Idaho, represented by the symbol ID, where the value in yield per colony is at 36. Of course, the value in this column is continuous in nature, means that we go through an entire range. However, what if in our analysis, we are not quite interested in the specific number as much as whether the yield is high or low, or rather, we would like to rate the yield on a 5-star scale rather than looking at the raw numbers. Well, for that, we can create a measure which converts a particular numeric column into a star rating based on a given range. If things still seem a little abstract, well, just follow along with me, and from the home menu, when in the data tab, let's create a new quick measure. As we saw previously, this will prompt us for a type of calculation which we need to perform, So from the menu, I'm going to scroll all the way down to the bottom under the text category and then choose the option of a star rating. It is interesting that this has been categorized as text, as you will soon see that this does not quite fit into that description, though you might consider that it falls into a category all on its own. Once this selection is made, well, there are 4 additional details which need to be provided, starting with the base value. So this is the value on which the star rating will be based. Then we can also specify the number of stars in our rating scale. By default, this has been set to a scale of 5 stars, but this is something which can be configured. And given that the star rating will be applied to a numeric column, well, we can specify the range of the values based on which the star rating will be calculated. So by default, the minimum value of the range is set to 0 with the upper bound set at 100. Alright then, since we want the star rating to be based on the value for yield per colony, let's expand the union table and then select that field by dragging it over to the base value. And then for the number of stars, well, let's just leave it at 5 stars. In our dataset, this will mean that for a state where the yield per colony is low, the number of stars will also be low. And anything with a high yield per colony, well, that should have a higher star rating. Alright then, let's head over to the value for the lowest star rating. So you can see that this defines the threshold at which a 0 star rating will apply. Anything below the specified value in the base value column will be translated to a 0 star rating. So let's just set this to a value of 15. And at least in the case of our dataset, there is no value for yield per colony which falls below this threshold. So there should be nothing with a 0 star rating. And then we can specify the upper bound. Now the upper bound in our dataset is 118. If we set a value of 95 here, well, we ensure that there will at least be a handful of rows with a 5-star rating. So this is how we can effectively make the yield per colony column discrete. Of course, intuitively, it makes more sense for us to apply a star rating to, let's just say, the score assigned to a movie out of 100 or maybe even a restaurant. However, there will also be instances where you would like to apply a star rating based on some other numeric column to distinguish between the better and poorer performers without having to look at the raw values. Alright then, to see exactly how star ratings work, let's go ahead and hit OK. And when that is done, well, I'll draw your attention to the fields pane on the right. Right at the bottom, there is the yield per colony star rating measure. And then, towards the middle of the screen, we can see its entire DAX formula. So this formula definition takes over 23 lines in all. And you can see from the use of multiple functions and also variables, as well as nested functions, that it is all a little complex. And this is where a quick measure can save us a lot of trouble, where we don't need to go through the pains of defining a measure entirely on our own from scratch, and instead get Power BI to build the formula for us. Before we take a look at the formula in a little more detail, or edit it in order to tweak some of the settings, well, let's see how exactly the star rating applies to our own dataset. Now, if we try to take a look at the full union table, you'll observe that this is not where we can view the star rating. And just like with the other measure which we have defined, we will need to generate it in a visualization. So let's head over to the report view. And now that we have a table which points to the production value in dollars from each state, well, let's just add in a new column. First, let's just drag along the yield per colony so we can see the raw value. And once we have a 3-column table, let's pull in the star rating measure as well. So just by checking this becomes the new 4th column in our table, and we can perform a direct comparison between the raw value for yield per colony and its star rating. Let's zoom in then on rows 3 and 4 corresponding to the honey production in the state of Arkansas. So the raw values of 64 and 63 translate to 3-star ratings. And then for the next 2 rows corresponding to the honey production in Arizona, the values of 46 and 53 both translate to 2 stars, And then for California, well, we see a change in star rating for the 2 different years. In 2011, with an yield per colony of 35, this was a 1-star rated year, but things improved significantly in the next year to jump to 2 stars with an yield per colony of 48. While Hawaii recorded 4-star rated yields, well, to get the 5-star ratings, let's just head over to the M's. So we can see that in the case of Mississippi, both the years correspond to 5-star ratings, and 2012 in the case of Montana also yielded 5 stars. Significantly though, in this particular table, you will notice that there is not a single occurrence of 0 stars, which means that we are only using 5 of the possible 6 values for the star ratings based on the current configurations. In order to give a better spread, we will need to modify the yield per colony star rating measure, for which let's just select it from the Fields menu, and automatically its DAX formula bar pops up. And now we can actually go ahead and edit this formula in order to configure it to our liking. Before we get to that, however, let me draw your attention to the use of variables in DAX formulas. So the occurrences of the var keyword, which you can see between lines 2 and 6, all correspond to variable declarations. Variables are especially useful when there are complex DAX formulas to be computed and allow us to define a value which can later be referenced within the same formula definition. As with variables in any programming language, this not only makes the code easier to read, it is also more computationally efficient. For that, consider the variable whose definition starts on line number 6, and this is the normalized base value. This is a variable whose value is computed by using this complex series of functions, min, max, divide, and so on. So you can imagine that computing the normalized base value will require a few CPU ticks. However, on line number 17, you will see that this variable is referenced and passed as an argument to the round function. In this case, the value which was computed for normalized base value can simply be used as is, and all of the min, max, and divide operations need not be performed once again. Alright then, now that you're familiar with variables in the DAX language, let's head back to what we came here for. We would like to modify the range of values over which the star ratings are computed so that there are at least some instances where the yield per colony translates to a 0-star rating. Well, for that, we can just change the min rated value variable. Instead of 15, let's set this to a value of 30. This means that any value which is less than 30 will automatically be assigned a 0-star. However, even some values just above that will also translate to 0 stars. Then let's go ahead and increase the max rated value a little bit to 100, and then hit enter on your keyboard for this to take effect. Following which, let's just close out of the formula view. And now when we view the table, well, you can see that the change has in fact modified the table. So the yields for Arkansas, which were previously 3 stars, have now dropped to 2, and significantly, the first of the California entries here, with an yield per colony of 35, now translates to 0 stars, as do the 2 entries for Idaho, with the state code of ID a little further down. Significantly though, the yields for Mississippi are still at a very robust 5 stars. So this is how we can effectively translate a numeric column to a discrete star rating. So one thing to keep in mind, as we have seen, is that the range which we define for the star ratings can affect what stars are actually assigned, which is why it is best to apply a star rating to a column whose values are bounded. For example, the scores out of 100 for an exam, or any value which represents a percentage. If the range is not really known, or is something which can vary wildly, well, the star rating will not be as meaningful. We will now focus on defining a new measure entirely on our own by using a DAX formula, where we will also explore the use of the COUNT-AX DAX function. So we have already created 2 measures previously in this course. These include prod value for the top 3 states and also yield per colony star rating. This is where we defined what we wanted by using Power BI's UI for a quick measure. However, in many cases, it may be a little simpler for us to define the formula from scratch, and this might also give us a little more flexibility than what a quick measure offers. So in order to define our own measure, we can head over to the Home menu and then choose the option to create a new measure. When we do this, well, there is no UI as such. All we need to do is to populate this formula bar with a formula for our measure, starting of course with the name of our new measure. And in this case, well, let's just say we wanted to count the number of occurrences in our dataset where the yield per colony is greater than 50. So we have a total of 80 rows in here, corresponding to the honey production in 40 states over 2 years. And to get the number of occurrences out of these 80 rows where the yield was greater than 50 per colony, well, let's set the name of this new measure as yield more than 50. This of course is followed by an equal to sign. And then, well, let's just see exactly what we need to do to compute this number. Well, what we need is for a value of 1 to be assigned to a row if the yield per colony is greater than 50 for that row and 0 otherwise. And then we can just sum up the number of ones computed. And for that, well, there is a DAX function called COUNT-AX. So I'll just type in COU and then use the autocomplete. And let's just see exactly how COUNT-AX can be defined. So there are two arguments here. The first of these is a table on which the calculation will be performed, followed by an expression. Well, in our case, we would like the calculation to be performed on the union table. So I'll just type in that and use the autocomplete again to help me out. And then let's get to the expression. As indicated by the description here, this is an expression which will be applied for each row in the given table. So what we would like here is for a value of 1 to be computed for each row where the yield per colony is greater than 50. So for that, we can make use of the if function. If you have used any programming language or even Excel formulas before, you should be quite familiar with how exactly this works. So let me just use this here. And in the case of Power BI's DAX, this is how an if statement can be defined. The first argument to the if function is a condition which will be evaluated. So this is the logical test. The second argument is the value to be returned if that test evaluates to true. And then the third argument, which is optional, is the value to return if the test evaluates to false. So in our case, we want to test whether the value in the yield per colony column in the union table is greater than 50. So in the autocomplete, I'm just going to navigate over to the yield per colony column and select that. And then we'll check whether this is greater than 50. So this takes care of the logical test. And then let's return 1 if this evaluates to true. And given that we don't really care about the rows where the yield per colony is less than or equal to 50, let's not return anything if the condition evaluates to false. So when we close this parenthesis, our if statement is complete. And then we can just close down the entire COUNT-AX formula as well. So let's quickly summarize what exactly this COUNT-AX formula does. The first argument points to the union table. So this is the table on which a count operation will be performed. As for what exactly that count operation is, well, it will count the number of times our if statement returns a true or a non-zero value for each row in the union table. In our case, for each row where the yield per colony is greater than 50. Now the value which is returned by the COUNT-AX function is a scalar quantity. More precisely, this will be an integer value, given that a count can only return an integer. Now to see this in action, well, we will need to apply this measure in a visualization. For that, we head over to the report tab. And now we can take a look at a new type of visual. This is one which is simply called card, and all it does is display a specific value. Conveniently enough, our new measure, which counts the number of instances where the yield is greater than 50, also returns a specific value. So let's now see what exactly this looks like in our card visual. So we can pull it up and I'll just expand it so that the number will be more clearly visible. And then we'll simply go ahead and select our new measure. And there you have it. Out of the 80 rows in our dataset, there are a total of 51 instances where the yield per colony is greater than 50. So you can clearly see here that the card visualization is very simple. So the question you might ask is, why exactly is this included at all? Well, this is usually not a visual which is used on its own, but is included alongside other visualizations in order to convey a rather important value, which may often attach some context to the other visuals. For example, consider the case where we have a bar chart displaying the honey production for different states. A card visualization like this one can point to the average honey production per state so that each of the individual bars can be evaluated in the context of the average honey production. Alright then, let's move on and explore one more feature of card visualizations, specifically that the values they display can change when the underlying formula is changed. So let's just select the yield more than 50 measure here. So the bar pops up where the formula can be edited. And rather than count the number of instances where the yield is greater than 50, let's say we wanted to compute the number of instances where the yield is greater than 75. So we can change the name of this measure, and then we also modify the condition in the if method. So the test to be performed is whether the yield per colony is greater than 75. And then when we hit enter, well, our card visualization has been updated to reflect the latest measure. So there are just 5 rows where the yield is greater than 75 per colony. Let's just quickly modify this to see how many instances there are of the yield being greater than 30. So we can change the name of the measure and also the formula. And then when we hit enter, well, this occurs in all but one instance, 79 out of the 80 rows. To see what exactly the odd row out is, let's head over to the data view. And a little further down in the page, you can see that in the state of main with the symbol ME, the yield was exactly 30 in 2011. This course served as an introduction to modeling data from a theoretical standpoint before delving into the implementation of some of the basic tasks in this domain using Power BI Desktop. You kick things off with what data modeling means in the context of Power BI, the different tasks involved in this phase of data analysis, along with an overview of the star and snowflake schemas for representing data. You also got a glimpse into how modeling data is important for the performance of visualizations built from that data. You then got hands-on with Power BI Desktop and covered the use of the DAX formula language for some fundamental modeling tasks, such as defining a calculated column and creating a measure. Here, you got to see how calculated columns are meant to compute a value for each row in a table, while measures can aggregate values to return a single scalar quantity. You also covered the implementation of a star rating measure to transform a numeric column into a categorical rating on a 0 to 5 scale. Finally, you use the DAX COUNT-AX function to count values based on an expression. Having completed this course, you have a high-level understanding of why data modeling is important in data analysis and the different options available in this regard in Power BI. This has set the groundwork for you to move on to other crucial topics on the subject so that you can build more insightful reports and also prepare for the DA-100 certification exam. Possibly, the most fundamental building block when it comes to data modeling in Power BI is the DAX formula language. While you have already made extensive use of this so far, in the next course, you get to dive deeper into its features, the breadth of options it offers, and how to best use DAX for an